We're going to start here, so we'll start in about the next minute or so. So please kind of wrap up your conversation, and we'll let Peter get started. So our next speaker is Peter Bram. Peter has founded a new company, Campaign Storage, and we're all familiar with his great efforts with Lustre over the years, and a big contributor in storage systems research, parallel file systems for HPC. So we're definitely very excited to hear about what you're up to, Peter. So yeah, there is, you want to use this one as a carry-on? Okay,
great. Good morning. Thank you for having me here, and thank you for all the attention that this conference is giving to campaign storage. So I was asked in this talk to give you a perspective of what campaign storage could be as a product in the market. How does it fit in with other storage technologies? What sort of features should be in there? And how would it be engineered? And so let's take a look at that. I think I'll start with some overview of what is happening in the market space of devices, because there are tremendous changes, and then we will move into the campaign storage applicability to that market. So campaign storage, as you've just heard, was actually invented at Los Alamos National Laboratory. And we visited there a few times, and Nathan Thompson and I founded a company to productize this and add some features. So I'm a great fan of what is called software-defined storage, and so I look forward to partnering with both suppliers of storage equipment, but also end users, depending on how they want to proceed with it. There are several other companies that are working on various aspects of campaign storage. So what you've probably learned this morning already is that campaign storage is a new tier, and there are several new tiers in storage. The burst buffers are one new tier. They are very fast flash or NVMe devices of another kind maybe, and there are probably different burst buffers coming with other kinds of memory. The parallel file system is still in there as a tier. It's an older one. Archives is an older tier, and campaign storage sort of fits between the faster tiers and the archive. Another new tier is the cloud. And so in the new world, there are now a lot of tiers, and what you see is that the bandwidths per tier decrease approximately in order of magnitude. Yeah, so that's quite a challenge to deal with the data transport between something that is 10 times faster or 10 times slower. So if you look at the deployment,
and I'll take that. Sorry to interrupt.
So what Dave has explained to you this morning is roughly the sort of deployment that I'm showing here in this slide. In a research computing environment, you might see some clusters, maybe doing simulations or analytics, and these clusters would typically have a set of compute nodes doing the math and the analysis, and then perhaps a clustered file system like the Hadoop file system or Lustre file system, but also a burst buffer these days with the highest bandwidths. Now, what we'll see in a minute is that storage is very expensive. And the way that people will gradually start to operate with this is by moving data in and out of the faster tiers to something that you could call campaign storage. Yeah, it could perhaps be offered by different storage systems. So campaign storage offers a lot of capacity and data movement. It's a fairly industry neutral tool because it is a file system, and so it can coexist with other tools that you may already have, like policy databases or data management tools, workflow managers, and that sort of thing. We think that this is quite a big challenge this is a sort of an open architecture for big, long-term storage. And so Los Alamos and we created a steering group for campaign storage. And the purpose really is to find open approaches to data management and make sure that customer needs are heard. And you're welcome to come and attend the first meeting tonight. It's in a hotel not very far from here. And if you don't like the talk about campaign storage, you can always drink or eat something there. Good. So the way that we look at campaign storage is that it is a product line. It is all derived from a core set of features that you could call the campaign storage file system, MARFS, and then there could be slightly different variations, for example, to use it for archiving, for burst buffers, or perhaps in the enterprise. Yeah, and so I think that there would be a couple of varieties of products in this space that each have slightly different opportunities, but they would, for 99%, leverage the same code base. Very important about campaign storage is that it is not an effort to build many things from the ground up. Yeah, it leverages existing object stores and existing parallel file systems for metadata storage. And this makes a huge difference because maturing a bottoms-up storage product is a very long process. And you can see all the gray hair on my head. It was all caused by work like that. Yeah. Good. So let's, for a moment, look at what is happening in the industry. So I think that this is an interesting set of numbers here. So I drew the sort of 1, 2, 3, 4, 5 tiers of memory here. And I put some numbers below that, namely what is the cost for bandwidth and what is the cost for capacity. And the cost for capacity you find in the newspaper every day. Yeah, so there's very little news there. And what you basically see is that the lowest cost is still tape for like $0.01 per gigabyte. And the highest cost is stuff like RAM for approximately $10 or so per gigabyte. What you see above that is that the cost for bandwidth increases with a same factor 10, but in the opposite direction. Yeah, so to achieve bandwidth with tape, for example, you would need to buy a tape drive, which is a horribly expensive thing. Yeah, and to achieve bandwidth with memory is ultimately the cheapest. We have 4 orders of magnitude in cost for capacity and in cost for bandwidth there. Yeah, and so this is not a small number. It's quite a technical challenge. So that is what we're talking about. Campaign storage targets the movement between 2 of these tiers, perhaps, yeah, or maybe 3 of these tiers. It's not a system that fits every possible application, but it is for managing tiers. By the way, in the enterprise storage, there is a similar problem or case for high cost and low cost. So in enterprises, very often expensive file servers are used. I'm not so sure exactly how, number-wise how much better they are, but they offer much better reliability and often very good performance. And so this is why people that, for example, run movie studios will buy NetApps or Isilon file servers to have very reliable systems. But these reliable systems are also very expensive, and so they are relatively small, and there is a need to move things in and out of these more expensive storage tiers to a cheaper tier. Yeah. So when you look at tiers, there are many considerations. So there are RAM tiers that are addressable, and they are primarily for computation. And so the idea here is that you would migrate a pointer in some program between one tier and another. For example, you would migrate it onto the chip to HBM, or you would migrate it from HBM maybe to RAM or NVRAM. So another thing that you see with tiers is that starting at flash, tiers are very, very sensitive to the size of I/O. So flash is already 5 times faster on big I/Os than on small I/Os. Yeah? And with disks, that number even becomes bigger. But this really means that there is a need to aggregate small IOs into big IOs when you go down the tiers. Yeah, you can't do the same thing at different tiers. Another important difference between very fast tiers and storage tiers is that the very fast tiers have a program internal format. That doesn't really work. You can't really find anything in somebody else's pointer. So that's why namespaces are very helpful. And so these could be file system namespaces or object namespaces with buckets and IDs, yeah, to organize your data. The last one is actually almost like a puzzle. So I think that NVRAM is clearly becoming very, very important. But personally, I haven't been able to think of any good application for NVRAM except as being there for the fastest storage applications. Yeah, it will be much faster than anything else, particularly than Flash even and so on. Yeah, but there is no magic like computing in NVRAM or stuff like that. I don't really know what that would exactly mean or what the benefit of the non-volatility would be. So we mentioned already the role of aggregation, and that really is handled by containers. Yeah? So fundamentally, it's unlikely that you're going to see the same behavior in different tiers of storage. You must aggregate, and containers are probably a must-have. So here's a picture of what I imagine will be the important functionality that a container would offer. And so this is a picture that is more or less similar to what you can find on the Docker website. And the application sees containers, maybe with a base layer and then some modifications on it. That could be implemented, for example, with ZFS. Yeah, maybe that's not the right technology, but it's a good example. And so they have things like snapshots and clones that allow you to incrementally modify the file system, but be very informed about what lives at what layer. In order for this to fit into a tier, it's very, very important that these containers can be serialized, that you can send the whole thing as a stream without looking what is inside. Yeah, there could be billions of files inside this thing. That you can't handle in a slower tier. You can handle a stream. You also want differentials, so that if you make a modification to a container, you can stream out the differential. Yeah, and ZFS containers happen to do this very well. A new thing that people want is analytics. So they won't just generate files. They will often generate some small databases with the files. And these are deemed to be very, very important for future analysis. You won't be able to recreate these databases in slower storage. They need to travel with your containers. Yeah? And so this is, I think, what is important for containers. So a big topic in tiers of storage is transparency. And transparency in RAM would basically mean that pointers can migrate between different memories where the compute is happening. Yeah, and this could be memory on the chip, like HBM, or memory just outside of the chip. So this is relatively easy if the pointers are not first-class objects. Yeah, you can promote them and rename them because the programming language will redirect you to the physical pointer. But low-level languages, they will need hardware or operating system support. Yeah, things like page table manipulation and so on. So these things are beginning to appear, and their transparency at the RAM level. For storage namespace, transparency is actually a fairly old thing that people have thought about for a long time. And the idea is that you have some form of location database that tells you, if I'm looking for this or that piece of data, be it a file or an object, where is it? And so you need some kind of location database that is distributed, but also it must offer callbacks to tell you if something starts moving from one place to another. The location database has to tell you, look somewhere else, it has moved. Yeah? But what is beautiful about this, that a single directory that can offer this transparency can be reused for many purposes. Yeah? And distributed log managers did that in the past, and things like Redis and so on are beginning to do that in the cloud frameworks. So from this, you can sort of see what the emerging exascale storage framework is like. In the cluster, you will see applications doing very fine-grained work with containers of data. And there will be a lot of features there that are growingly emerging in maybe parallel file systems, but particularly in the new I/O libraries like DEOS and HDA5. Things like transactions and often peer-to-peer communications for fast synchronization, some erasure codes. And what you see here is that multiple forms of data will be managed in the containers. Some data might be completely local, other data will be consistent in the cluster, but some data doesn't have to be 100% consistent in the cluster, it merely needs to be findable. Yeah? So if it might be handled by one node, but if that node dies, you will need to find its snapshot back, perhaps, yeah, or its checkpoint. So the migration to slower tiers will happen with mover software, yeah, and the mover software will take this to a long-term repository of some kind. That long-term repository has very different qualities, yeah. You need low cost for the capacity, probably hundreds of gigabytes per second of bandwidth, but not terabytes. And the capacity will be very large. The integrity is very important. Yeah, this data is going to stay here for a long time. It needs to be protected from bit rot and things. It also needs to be manageable because enormous volumes of data end up in these longer term archives. Yeah, and I think the faster parts, things like burst buffers and so on, they are going to be almost of a transient nature. A job will start, it will use it very intensively, and then the results from that job will migrate back out to make place for the next job. Just one or two comments about object storage. So object stores are, a very important development that has had an enormous time of evolution, but has really come to mature in the cloud. So they have massive scalability, excellent storage management. There's a simple API, you put and get objects, that's more or less what it's all about. And it runs on very cheap hardware. So it has been very, very successful, but it does have a few cons. It lacks data organization. Yeah, there is no namespace, and these buckets tend to get very large. And I know that people find that difficult. They need databases or namespaces to organize the data. The APIs don't allow for any concurrent access, not from one application, not from multiple nodes, yeah, and this is a problem for distributed applications if they can't work in a sort of process per file, file per process model. Performance can be disappointing, and it actually turned out that they are very difficult to reuse as a component for a storage system, and this is what Los Alamos kind of achieved with MARFS, is to say, we are going to go for it, yeah, and we are going to use object stores. We'll deal with the compromises as they gradually emerge. The attractive alternative seems to be still an open problem, namely build an object store that has normal read-write commands, more or less, yeah, similar to POSIX. It can maybe do non-overlapping distributed I/O, has 3-tier hierarchical redundancy in a box, in a rack, and in a data center, and it has a coarse transaction protocol, yeah? Pull a snapshot across all your I/O. If you have that, I think things would become a lot easier to integrate with other storage systems, and different applications could use these object stores. Okay, so let's have a look at campaign storage. I already showed you this picture where it sits, so let's see what it is, yeah? So it's a file system, but it's not a general purpose file system. Now, there are no general purpose file systems, yeah? Some file systems are maybe very good for performance, other file systems are very good for reliability, but there are always fairly big compromises, yeah? And campaign storage file system MARFS has its own compromises, but it's good for migrations, yeah? Staging and archiving, meaning bringing the data into a faster tier or getting it out of a faster tier, that's what it's built from. I mentioned before, it's built from existing storage components, yeah? So there is no aim to re-implement object stores or file systems. Low-cost hardware, very scalable. Roughly the bandwidth is 10 times lower than a burst buffer or a parallel file system, yeah? Maybe 10 to 100. But it's also maybe 10 to 100 times faster than a tape archive. Yeah, it sits sort of in the middle, and that's exactly what the target is. So if we look at the implementation, there is on the left side here the core storage system. So this is the operating system with a file system, and it's implemented with Fuse, and then MRFS is the particular driver that glues the objects and the namespace together. It's a very simple driver, but it does important things. We'll see a little bit more about it, but probably Dave has already told you more than I will. Then there is a management component. What can you do with data in campaign storage? So analytics and search are important. Yeah, how do you divvy up this data? Where is it stored? Who owns it? What kind of files are it? You need things like migration and containers, and these are a few of these things my company is working on, and a few of these things are actually opportunities, I think, for many companies to look at. Then there are data movers. So there's a very beautiful data mover that Dave probably told you about called PF Tool. It's an MPI data mover that's very fast. It looks like rsync, but then clustered. So you can run rsync in parallel on maybe like 10 or 100 nodes and achieve a lot of scalability with it. But other problems need slightly different movers. For example, hierarchical storage management usually does a bunch of extra things. Yeah, it preserves the namespace, it sets extended attributes and so on. So there might be movers needed for HSM, and we actually built one. Yeah, and there would be 2 families probably for Lustre and the other systems with the MAPI. Enterprise NAS would have a different mover again that would probably be very compliant with both things like Active Directory, but also the CIFS or SMB protocols or NFS. And many people have asked for Grid FTP already, which is sort of a standard parallel data mover that probably can be fit relatively easy onto campaign storage. So let me skip this picture, but remember there were clusters and campaign storage data moving back and forth. And let's see how these components could actually be deployed. Yeah? And so the picture on the right summary expands when you get when you look at what is running on a cluster. So let's start in the middle. And so there might be 3 different kinds of object repositories. Yeah, there might be a disk object store is maybe possibly the most likely one. This could be a commercial one or an open source one. MRFS already supports quite a few, and they're very easy to add. There could be archival ones. So we have had some luck with the Black Pearl object-based tape system that SpectraLogic built. It is just an object store, but I'll tell you in a little bit later that there are actually some special points about handling tapes that require a little bit of work to use it well. Some of these objects would really benefit from POSIX semantics. So perhaps people want to store sparse file in campaign storage. Yeah, sparse files are not supported by most object stores, maybe actually by none almost. And so those objects are perhaps best stored right in the campaign storage file system where POSIX is available. Yeah, it's not as scalable as using the object stores, but you have more features. So the metadata repository, it's in fact very flexible. All you need is a POSIX file system with extended attributes. Yeah, and many have been tried. Livermore is running, Los Alamos is running with GPFS. We have focused on Lustre over ZFS for a variety of reasons. And the beauty of it is that nothing special is used about the file systems. But different file systems maybe come with different utilities for data management. Yeah, and so there's an opportunity there to explore what works best and maybe make enhancements. So to move and manage stuff, you need mover nodes. Yeah, and the minimum number of mover nodes is 1. Yeah, and now how do these mover nodes actually get access to the data in the faster tier? And in the slower tier, in the campaign storage tier, they will typically just mount file systems from both tiers. Yeah, that's the simplest way to make connections. The mover software runs on these mover nodes. So it might be a cluster of mover nodes and a distributed application. It might be a single mover node that is driven by a single program. So the management will also run on mover nodes. So things like managing the search and analytics, which I will tell you a little more about in a few minutes, third-party data movement, but for example, to migrate data between different object stores, will be initiated from the mover nodes. So the mover nodes are really your interface with the campaign storage system. When we go one level down, we can see that the data layout of MARFS. And the data layout of MARFS is actually very, very simple. So on the left side of the dotted line, you see what is called the metadata repository. And the metadata repository is just the folder structure from this underlying file system that I've mentioned a few times. So you put your names and inodes in there, perhaps completely as normal, as you would normally do. But you use the extended attributes to indicate where the data resides. And so these extended attributes, they might point to a single object, which would then reside on one of the object stores. But there are a few other interesting things you can do in campaign storage. For example, you can pack multiple small objects into one big object. And this is actually quite important because the latency of these object stores is very, very high compared to the latency you would get for small file systems, small files in a fast file system or a burst buffer. So this one form of containerizing data is to pack them in an object. There are also very, very large objects in use now, petabytes in size, and these don't fit on one object store. They must be striped over multiple object stores. So a different layout would be to stripe them. And in that case, a little extend lookup table is needed, like what belongs where in the striping layout. Not so complicated, and also exactly what you would expect. If you were to sit down over a cup of coffee with a friend, you would draw this diagram, perhaps in exactly the same way. There is nothing magic about it. So let's look a little bit at search and policy management. So when I started this company, Campaign Storage, for the first sort of 6 to 9 months, I went around and talked to a lot of people to find out what are the archive technologies doing for you, and what are they doing well, and what are the sort of stumbling blocks. We did some testing in a lab, and we kind of found out that one of the big issues is what is called a database, a policy database. So often archival systems crawl your file systems and build a rich index in which you can perform searches and so on. What we found is that those crawls are very slow. The resulting searches are also quite slow. And for a very long time, I had already thought about a different kind of search system where you basically give every directory information what sits in its subtree. So for example, if you have a home directory of a user, you may wonder how many files are there in this home directory, and that could be a lot of files. And at the moment, the only way to find out is to run something like find on that home directory and add up how many files or how many bytes are there. What if you summarize that with a small database, and you capture, for example, how many bytes, how many files have this or that property, and that property could be it's a video file, or it could be it's a property of a geospatial location. How many files relate to this or that location on the planet? What file servers are used in this subtree? And so there are quite a lot of these histograms that are useful, and the histograms actually turned out to be the pivot of what people do their data management with. They often have this very big database sitting out there, and the first thing they're going to do is build histograms to get a feeling, what do I need to do to organize my data? How much old data is there? How much big data is there? And then they begin to apply some policy to move it somewhere else or remove it or something like that. It's, by the way, not at all a new idea. This idea has been around for, I think, maybe dozens of years. It may actually also relate to so-called multidimensional database tables. It computes more or less what the aggregates are. The beauty is you can added very easily to ZFS. And the reason is that ZFS has these snapshots that I already showed you, and they have beautiful change logs between them. And it helps building completely consistent databases with histograms to do some analytics. So the key properties of this system are that you generate it initially from a scan. Yeah, so you want to start early on so that you don't have so much to scan. Then you update it with change logs. Yeah, so you have to be careful. You have to design your histogram in such a way that you can apply the change log to it and update it. Yeah, if you put information in it that is too general, you will not be able to do that. Yeah, but there are a lot of cases for which you can do that very easily. You want to keep the database 100% consistent with the snapshots. I believe that this is very important because the normal policy databases are live objects. They keep tracking the file system. They're never completely in sync with it. And I think that limits their usefulness because when you actually apply a policy, you will often need to do a comprehensive operation that is 100% correct. For example, back up all the files from a particular user or with a particular property. And these live databases that follow changes in a file system are very difficult to use for that. Now, another very important thing is these histograms have a beautiful property of additivity. So if you put in a subtree, you can keep all your histograms and you just tell the parent, well, there's a new subtree, so increase all your numbers a little bit by what is in the subtree. Yeah, and so just with a few additions, you graft a whole subtree with a lot of information into the histogram tree. And this allows for the motion of containers with analytics and integration of these containers into the file system. So here's a simple example. Yeah, so the root histogram might tell you how many terabytes and files you have, and maybe some other properties. Yeah, so how many are on this or that particular file server, how many have never been opened, and then some user directory is actually a subset of what you see at the top. Yeah, it adds into it because the idea is you see everything in the subtree. If you build a multi-dimensional histogram, things like file type, file size, and maybe access time, then you get limited relational algebra on your searches. Yeah, so you can then combine how many files of this type and that size and this access property are there. Yeah. Without multi-dimensional tables, you will have limited search expressions. Yeah, but you can customize the histograms very easily, so you can get them to be right for your data management also, if you prefer that. Okay, just a few other things. Data movers. So the data movers that we have today are the LANL parallel rsync tool, PF tool. There's a Lustre HSM mover. This is a moderately involved thing I'll tell you about in a minute. And the beauty of the movers is that they can pack and stripe files. Yeah, so you can put small files together and big files on multiple object stores. So what I think will be coming is a DMAPI version of the HSM mover so that it can work with the other cluster file systems like Quantum and IBM's file systems. Grid FTP, as I mentioned. But the most important thing that would help and enable data movers is to increase the POSIX compliance of MARFS a little bit. At the moment, these data movers basically have to follow the sequential write to a single object model that the object stores offer. And if we make some changes on this object layout and allow overwriting of objects, for example, or writing them out of order, then many data movement utilities will just work out of the box. This may sound like a challenging project, but it's actually also fairly old. And for example, the entire Dropbox system is built in this way. Dropbox breaks up its large files into many objects, and each of these objects is of moderate size, like 4 megabytes, I think, or so. And so they allow overwriting and basically POSIX semantics on objects by breaking them up. And MARFS could do the same thing really quite easily. So on the front of metadata movement, today MARFS offers a standard metadata API across multiple file system namespaces. So its performance can scale very well provided you use the breadth of the tree. Yeah, if you go only very narrow and deep in the tree, you will basically be using a single file system at the moment. What is coming here is bulk integration and striping of metadata. Los Alamos has a couple of projects. I showed you what you can do with containers. Yeah, you can graft containers in a namespace, and that will allow much faster movement than you can get with individual operations. The accompanying analytics are also very important parts of moving the metadata. So here's a picture of the parallel file tool. I don't know if Dave already showed you this picture, but it's has a beautiful task queue model where some operations run over directory content, others run over attributes, and then there's data movement tasks. And so it's almost like a distributed job scheduler that makes work items available and then has workers attacking this and reporting the completion. Yeah, again, it's easy to draw this picture, but it's perhaps quite difficult to write a program that's correct and does it efficiently. By the way, one of the most beautiful features of PF tool is that it will restart very efficiently. That's one of the few frustrations with rsync, is that if you if you kill an rsync loop, it does have to scan the file system again. And PF has some clever tricks, PF tool, to pick up where it left off. It's much, much more usable because of that. The HSM mover that we build uses an object protocol that is very closely related to S3, but it has features for so-called bulk handling. So when you deal with tapes, it's very, very important that you don't keep moving the tape around. And so, for example, when you want multiple files out of an HSM, you would tell the tape, give me these 100 files back. And the tape device would organize for you in which order it will deliver the files. Now, this looked like quite a puzzle to me initially. I thought, boy, I've never seen that before. And then I realized that that's actually not really true. So this is really doing scatter, gather, I/O, but not for multiple extents in one file. It's scatter, gather, I/O across multiple files. Yeah, so you're basically saying, I need 100 files to move from here to there. You determine the order. Yeah, I only tell you what is the source and the destination. And so we built a rather nice little library that supports scatter, gather, I/O for a number of files. And it does very nice things. For example, it can pack small files into a big file. Yeah, because that tells you I have maybe 100 small files. Put them at this and this and this place in one destination file. So that's packing, yeah? And the other important application is that the system can reorder this. So it's a good example of some of the new features that can be explored in this space. Yeah, there's borders on what you perhaps would call, research. Could be a new system call. Yeah, and many system calls were added for vector I/O factorization. But this one is not there at the moment, yeah? And so I think it's a good question, do we need this one? It certainly looks like it's handy. So let's wrap up the talk with looking at a few of the use cases. So the high-performance computing, or research computing as people begin to call it, the important things that campaign storage can offer here is, first of all, what I would call support for the ecosystem. Yeah, so I think the fact that campaign storage is a file system is very important because it's not a proprietary interface with that, and many other utilities can leverage this. When you go to more basic use levels, you can say, okay, it can stage and destage, yeah, which Los Alamos is showing is working quite well. HSM, and HSM is quite a rich topic. about which we could talk for a long time. But for example, the model here is a little bit different than it might be with tape, because we would maybe want to build a metadata image of the file system first in these namespaces of campaign storage, build the analytics for the subtrees, and then start the policy manager. That's a little bit the opposite way around of what happened in traditional HSM systems, where these policy databases are built in the source file system, yeah, and not in the archival side of the storage. Campaign storage will probably want to support hot and colder locations, yeah, data that frequently needs to move back and forth between the burst buffers and the campaign storage will need to be made available in faster object stores. Many people have asked me about multi-site, and the answer is very simple, because most object stores support remote replication. ZFS supports remote replication using the same mechanisms as underlying the snapshots, and so this is an ideal system to build a remote replica of, particularly for disaster recovery. If you don't have to use it actively in two places, it's easy to build. Another interesting structure in object storage and in CFS are the containers, like buckets for objects and namespaces for the file system. And I think that this is a great opportunity to bring organization to data. For example, why not store a user's home directory or a particular project in a bucket with its own namespace? Because these buckets and namespaces are supported by very good data migration tools. And so, for example, you could extract a project to the cloud relatively easily with this by simply taking a small piece of this big CFS file system and say, well, that's actually what belongs with this project, yeah? Let's put that in the cloud together with a bucket of objects. Amazon has made it quite cheap to move buckets of objects into the cloud, because they will ship you a little appliance called a Snowball, and you can copy locally onto it with very high bandwidth and use UPS or FedEx to ship it back to their warehouse. Yeah, so the wide area networking, which is a real bottleneck for large volumes, is snowballed away by Amazon. So in the data center, you will see slightly different requirements for campaign storage. In that case, maybe there would be an offload of things like NAS file services from fast servers to campaign storage. Yeah, so you would want to export a NAS protocol from campaign storage. Again, the single project extraction is valid there. Also, perhaps to build a global namespace for all the file shares that are available. Yeah. Hot and cold locations we already talked about. Good. So I think that the future of this is to challenge the established, somewhat proprietary nature of data management. Yeah, I think what we would like to propose is, let's sort of go back to things like file system APIs and see how far we can get with those. And clearly, there is quite a bit missing in this space. For example, the file system people nor the data management community has ever agreed on a single view of where is data located. Yeah, what does a layout API or structure really look like? Similarly, many attributes are used by different data management tools, and there is no agreement on what these attributes really should be between one storage product and another storage product. So you get sort of a vendor lock-in at the data management level in areas like layouts and attributes. Similarly, everybody is building their own interfaces for workflows. Workflows are very often bulk operations on file systems, meaning moving lots of objects, moving lots of names, and the Unix APIs, which have been tremendously successful, unfortunately only work one object at a time. Yeah, one file at a time, one directory at a time. There are no calls to move whole subtrees, for example, in file systems. Yet, if you think about it, many storage applications, like Dropbox, for example, rely precisely on that. Yeah, how do I migrate all the changes that are made on a computer, in this case to the cloud? I think this is a great opportunity, and I'm particularly hopeful that the working group that we've created can maybe have good discussions. So the conclusions are, there's a lot of new hardware out there, and as a result, people have started to build new software, yeah? And campaign storage is one of these things. The other thing we saw is constructions of containers and the very fast I/O libraries that are needed. I think that the bulk aspect of data movement is perhaps one of the most interesting questions. Doing that for both data and for metadata, yeah, deal with lots of files and lots of data at the same time is a great challenge. I think I'm going to stop here. We have time for a few questions, I think.
Great. Thank you, Peter. Are there questions for Peter? He's pretty shy here. Okay.
So I'll ask the same question that I asked David. I've never heard of any other future-looking storage architects talk about the need for more POSIX and more file systems looking forward. Do you really expect file systems to be the path to the future, or is it just a stopgap?
I think this is a very good question because we don't really know the answer. So historically, and this is probably what Dave answered, is when more and more objects started to arise, people needed organization, yeah? And a file system tree is one form of organization. You could also store it in a database, yeah? It doesn't make a very essential difference in this case. What I've heard is that objects without a namespace are difficult to manage in organizations. Whether some replacement of file systems will come into play, I don't know. But I do want to point out that there is a challenge with a different organization, namely a different organization of the data will likely be proprietary. Yeah, and the big success of reusable applications has been possible only by having a reusable interface. And we begin to forget that things like Google Drives and Dropboxes and all these kind of things, they're actually totally locked up. Yeah, it's very difficult to run your storage applications on a Google Drive. Yeah, there is no rsync for Google Drives or Dropbox, I think. Yeah, that would have to be completely reconstructed for the new APIs. I think it's very costly. Yeah, I think there may very well still be a very good opportunity for data management to leverage standard APIs. But you never know what will happen in the future.
Okay, other questions? Okay, I guess we're all shy. Okay, again, thank you very much, Peter.
Thank you.
All right, our next speaker is Andy Klein with Backblaze. I'm gonna, as he's prepping, I'll make a few comments about Backblaze. We connected them to the conference. I think it was about 3 years ago, maybe possibly 4. Yeah. And their CEO, Gleb Budman, is very hands-on, a very dynamic group of people. So we invited Backblaze to speak and tell us about their systems, and we got their CEO. So Gleb came and gave us a great talk on. He kind of had a deep understanding of their technical architecture. And very interesting company, as many of you know. They basically open source their hardware designs. They've been very obviously aggressive about using disk as a long-term storage medium, so they've always been able to kind of bring to us a lot of very interesting information about leveraging disk technology in that kind of way. Historically, this conference, I think probably the majority of the folks, as the original, I guess, time frame of the conference, tape was viewed as kind of the only real long-term way, but people are using disk, and so Backblaze has brought a lot of interesting numbers. So today, Andy Klein is going to talk about the latest numbers that they've seen. They certainly have made news before, for example, with a lot of interesting numbers on the Seagate drives about 3 or 4 years ago. So we're looking forward to more news. This could be some some breaking news right out of the conference. So Andy, over to you.
Oh, sure. Tell me.
Which disk vendor needs to hang its head in shame? That's right.
Can you guys hear me okay? All right, thanks.
Oh, yeah.
That would be helpful. Is that better? Yeah. Here we go. All right, so normally, as he mentioned, Gleb does this. You guys may have seen him over the years. His wife took him to Spain. So I get the opportunity to stand in front of you. We're actually making him work, by the way, while he's over there. We're sending him over to a conference in the Netherlands to do a little presentation next week. So no vacation for him. Yeah. Today he's in Madrid, by the way. So he let me come up and do this one. I'm actually the one who does the drive stats. So if you guys are familiar with those, I'm the one who writes the blog posts and makes up all of the stories from the data that we have. And I'm going to walk you through how we get there a little bit about the drive stats that we produce. Love them or hate them, we do them each quarter. And I wanted to kind of give you a little bit of how we got there and like I said, what we do. We'll talk about the drive stats, the current ones, how we produce them, and what they kind of mean and what we think they mean. So we're all on the same page. And then there's a little bit at the end, and we'll see how much time we have with regards to smart stats, because we get all of that data too. So you'll be able to have some fun with that. I make no claims to whether or not you'll like this or not. Some people can't stand our numbers. Other people love them. But we tell the story, and we tell you what we have and what's going on. So a little bit about how we got there. So Backblaze as a company has been around 10 years. The state of Delaware thought it would be funny to incorporate us on 420. And if you don't know what that means, ask the guy next to you. So we just celebrated 10 years. We did a launch of the original product a long time ago, back in 2008. But we really started to get people to pay attention when we did our first storage pod. The storage pods were those big red boxes that we store everything on, right? And we not only published it and told the world about it, but we published the specs and said, hey, go build your own. As a matter of fact, I was talking to the folks over at Shutterfly just a little bit earlier, and they kind of embraced that. And they took off with that design, and I'm sure made lots of improvements, and we've done that over the years as well. We've grown a little bit from 10 petabytes back in 2010. We've crossed over 300. So that's what we have in management. I think we're over 350, although you didn't hear that from me yet. We like to publicize stuff, right? We did our first drive stats post back about in 2013. And that was done by Brian Beach, who some of you may know. And he published a lot of fun stuff. And being a marketing company a little bit, we went out and went, oh, this is the greatest thing ever. Look at this, drive reliability stats. Which drive do you think is the best one? And people just tore us up. Your environment's not the same as mine. Yeah, okay. So I wanted to make sure I'll couch that, okay? This is our environment. By the way, that's the very first storage pod, and yes, that is built out of plywood. All right, we prototyped these things a long time ago. For those of you who are students of storage pods, that's actually 15 drives across, and you can see there'd be 3 rows. It's all 45, right? We literally prototyped the first one in plywood, which, by the way, if you don't know how to weld, is a really good way to build a storage pod. We eventually moved to metal, by the way, before we started putting customer data on there. Anyway, the hard drive data, okay, that we publish, we just did one last week. We do them each quarter, like I said. We look for different insights and things of that nature that we have. Along the way, we've had lots of fun things that have given us data. We went through the, it's a little fuzzy, huh? The the Thailand drive crisis back in 2011, 2012, right? And we talked about that a lot. If anybody wants to have a really good read, go to our blog and look up drive farming, because that's actually what we did. When we talk about now having 300 petabytes of drives and having nearly 100,000 drives, out there, we were sitting there going around to Costco's and buying drives 2 at a time in order to get around this. And later on, we started doing things like building into vaults and all kinds of stuff like that. I won't go into what a backblaze vault is other than to say it's the way we store data these days. It's spread across 20 different devices and all of that, right? The end of it is like I said, we have about 300 petabytes of data, about 82,000 drives that I'm going to talk about today. Over the lifetime, we've had 95,000 or so drives that have come through our system in various ways. Some of the lower density ones, the 1.5, 2 terabyte ones are now long gone from our system. But this is what we currently have as of the 31st of March of this year in there. Mostly 4 terabytes, most of them Seagates. You'll see that in a few minutes. A fair number of HGST ones as well, by the way, or Hitachi, depending on your point of view. And then more recently, obviously, started adding 6s and 8s. Okay, so we have a good smattering in there. Sad day when we retired some of the 2 terabyte ones because they were just killers. They had numbers of sub 1% failure rates in our environment, which is you just cry when you have to take them out because they just go. You put them in there, you close the lid, push it in the rack, turn on the power, and walk away. And so, but you need the density, so you trade 2s for 8s. And it's been okay so far, and we'll see that in just a second. So hard drive failure rates, right? The basics. How do we do what we do? We use this magic tool called Smart Mon Tools, right? Everybody uses that. There's nothing magical about it, right? We used to collect the data. We collect it once a day, okay, from every single drive in our data centers, right? And we used to store it for about 30 days so we could get an idea of what was going on in the system, look for problems, all of the things you would typically do with these kinds of tools, that kind of tool, information. Back in April of 2013, we started to keep it. So that's when our data set begins, okay? And I'll give you the URL in a little bit. If you would like the data from all of our drives, we will give it to you. Just download it from our site, and I'll give you the URL in a minute, right? We don't hold it to ourselves. But it's mostly all of our drives every single day. There are a couple of holes in there where something went wrong with the system. You'll see them when you get there, particularly in 2013. It's all of the drives in our data centers. Every drive that we have, including boot drives and management drives and all of those kinds of things. And so, but when we report the stats, we pull out everything except customer data drives that are in use. Just so you know, you'll see, I'll talk about a number that's 82,000. We have roughly 85 or 86,000 drives that we kind of monitor. So we try to keep the set all the same, right? So, but if you're really interested, the data's in there. If you're curious about how our boot drives work, okay, and what's going on. So what we get is, and if you've never seen this before, that's just the output that you get. Every record is like that, right? It's going to be the date, serial number, so on and so forth. And then going to the, you're looking at it, right, will be all of the different attributes. And we record them that way. We record the normalized and raw for all of the different attributes that can get reported. As you all know, or should probably know, smart stats vary, drive model, manufacturer, and so on. HGST reports SmartStat 22 for the helium, amount of helium that's in a drive, and so on and so forth. All kinds of different things. They're different. They're supposed to be consistent within model. They're generally, sometimes they are, most times they're not, okay? So it makes for really interesting analysis sometimes. And then it goes down, and obviously there's just more records. And any given day, you'll get 82, 85,000 of the records in there for a given day. So if you wanted to start thinking about doing some analysis, that's the kind of challenge you have. The one thing that we add to all of this is that little failure column that currently has all zeros in it, right? If there's a 1 in that column, that means the drive failed. In other words, we removed it from our environment. All right? And that's the designation that says, hey, that thing will no longer be seen. And it actually disappears from the next day. So if there's a 1 on that very first one, the next day that record is not there anymore. That's how you look at it. We count, and I'll go into this in a minute, about something called drive days, and you'll see what that means. But that's the indication. How many days did that drive exist? All right? Again, the period is from April till the end of March. There's actually 95,000 different drives in there over that 4+ year period or nearly 4-year period, right? Some of them have migrated away. Some of them have failed. We've had 5,674 failures, right, over that time period. Drive days, the number of days a drive existed, it was operational, right? So if a drive is put into play on the 1st of January and goes in, and then comes out at the end of January, that's 31 drive days. That's the way we count, and it's the way we do all of our math. All right, we don't look at the number of hours or anything like that from that Smart Stats reports, and I'll get to that in a minute. But you can kind of see the different numbers that we have. So 62 million drive days we're doing analysis on. If you wanted to just do what a lot of folks like to do when they look at our math and say, hey, if I take the number of drives and divide it by the number of failures, or vice versa, excuse me, I get a failure rate of 5.97%. That's the failure rate. And we go, no, that's not the way we calculate it. We calculate something called an annualized failure rate. And the reason we do it that way is because sometimes the failure rate needs to be calculated over a 3-month period or a 6-month period or whatever, or a 4-year period. And so that's the little formula, okay? Just drive failures basically divided by drive days. Right? Drive days are the number of drives that system, we had that number of days that drive was in our system. That's the math we use. If you wanted to go look at Smart Stats and pull off the number of drive hours and then do some math and calculate drive days, you could do that. The one downside to that is if you end up using reconditioned drives at all, sometimes the Smart Stats don't get wiped out. And you put a drive in play that already has hours on it. And sometimes the drive number of hours, especially when a drive goes to fail, sometimes that number is really goofy. Like, I existed for the last 22 years. So we use the number of the Smart Stats to kind of sanity check us sometimes, but this is the best way to do it. Just count it if it's there and it's working. And that's the way you'll see it in our data. So if you want to do analysis, that's the way we did it. So what do we get when we start to do this kind of analysis? This is the one, the report. This is the quarterly report. So for the period of Q1 only, okay, of 2017, what did we see? Now, you can look down and say, 1, 2, 3, 4, 5, drive failures column. You can see there's some things there that have nothing. My goodness, they didn't fail. That's great, right? And then you can look at the Seagate one, 4 terabyte Seagates, and say 267. Oh my gosh, that's horrible. Well, no, because when you do the annualized failure rate, they start to change, right? Start to change a little bit. Some people looked at the one for Seagate and said 3588. My goodness, that's a horrible drive. I never should buy that, right? No. It's just we had a streak of bad luck with that particular drive in that particular quarter. This is only for the quarter. So when you look at the data, you have to look at it like that, right? Some of them didn't fail at all. Nice WDC, the Western Digital 4 terabyte ones, no failures at all, yay, all right? But they only have 4,000 drive days on them. that's too low a number to make any kind of decision with. We like to see, something that starts to look at 20,000 or so, 25,000 drive days before you really start to get to any conclusions. We use the quarterly ones, for trends. Is there anything funny going on? What happened since the last quarter and the last quarter before that? We actually track in our internal system that moving 3-month kind of window to see what's going on as a group. Because one of the funny things is they seem to behave very, very similar. If you have a drive that seems to perform really well and then about 3 years out suddenly hits the wall, you'll see it in the numbers. And it's usually about 15 minutes after the warranty expires. But this is the annualized numbers for all time. So for the lifetime period that we have the data for. So this is starting to get to be serious, and that's why we put things like confidence intervals on it and stuff, because you have a really decent amount of data at this point. And you can start to see, so that one Seagate drive that was at 3588 isn't really that bad. 7.5% is not great. That's probably not a good drive for our environment. But its companion right above it at 3% is cool, the 4 terabyte Seagate one. You can see some of the HGST ones / HDS. HDS is the old Hitachi Data Systems ones, and then they converted them over. You can see those guys are just cranking along. They really, really like running in our data center. Right? Going to be a sad day when we finally get rid of those 3 terabytes. Just about as sad as it was getting rid of the 2s. And just to put a plug in for Western Digital, we finally, they had 1 terabyte drives that we were using when we first started out, 1 terabyte Western Digital green drives. And those guys were running at around 2.5% failure rate at 6+ years. Okay, so that's pretty darn good. And we were checking them out, and we still have them, by the way, and we actually abuse them by putting them into racks, and when we burn in the hardware. We put in a bunch of drives, and we burn in all of the other hardware, so they get the tar beat out of them. And they're still there hanging out. Really nice. So we do this every quarter, okay? You can get a sense of what's going on and publish the kind of data that's out there. You can see in our environment, we're a little over 2% is the annualized failure rate. Now, the interesting thing about this is only the drives that are operational during the first quarter. So at the end of December, so if you go back and look at the 2016 results, we actually published it for all of the drives that ever existed in our data center. And that list was something like 50 some odd items long. And the annualized percentage rate was actually a little higher, because what would happen is we got a bad drive in there, all right, we would take it out. We couldn't live with a failure rate that was too high. Could, but it just made life a little miserable. All right? Now, one of the questions that comes up with folks is okay, I get it, I understand. What's a failure? What do you define as a failure? Right? So the first 2 are fairly obvious. Hey, I turned it on, it didn't work. The second one, I turned it on, it spun, but it just won't stay in my RAID array. Or it just won't stay working, it won't work well with friends, basically. The third one is the one that usually is kind of interesting. We use smart stats. We have a handful of smart stats, which I'll show you in a minute, which give us indicators that a drive is going south. Right? And it's not an exact science. I wish I could tell you that as soon as we saw this value here and this value here and this value here, that we could just pull the plug. It doesn't work that way. But I'll show you a little study that the folks over at IBM did, which kind of give us some interesting ways that maybe it does work that way. Right now, that third one there is like I said, is experience and automation combined. And we do a pretty good job. When we pull a drive out, by the way, we actually run it through a couple of batteries of tests, a local load test, and then a secondary one which does the whole, basically like you would sync it into a RAID array. And if it holds up after that, we'll actually put it on the side and keep it as a spare. But if it won't hold up, then it's failed and it's gone. So it's not quite a human being there. There are some other steps that go beyond it, but that's what we use for criteria. Now, what does that mean, okay? What have we seen? What kinds of interesting things have we seen for drive failures over time, right? So somebody produced this wonderful chart. I'm gonna go this way. On the left-hand side, all right, that's the bathtub curve, right? Oh my goodness, it's gonna be early infant mortality, and then the drives are gonna settle in, and then as they wear out, you're gonna get wear-out failure, right? Is that really true? And it kind of is. It's the same thing here, okay? There's an early infant mortality. There's a nice settling in of 1.4% failure rate. And then after about 3 years, it starts to increase. Now that number is actually pushed out. What we're starting to see over the last couple of years, especially with the larger drives, is the infant mortality rate is still fairly high. But that annual failure rate stretches a little bit longer. It stretches into like 4 years, 3.5, 4 years before you really start to see a fall off or an increase, if you want to say it that way, in survivability of drives. So the curve seems to hold up, right? It may not be as pretty as all of that. It has a little bit different bend to it. But all of the things we kind of suspected, which is early infant mortality works really great, gets good, and then as it wears out, it starts failing, we see it. I like to put this one up because it's fun. This is hard drive failure rates, right? Cumulative by year. So each year, we looked at them, and they're cumulative. And you can see we had a little trouble with some 3 terabyte drives, right? The rest of them seem to do okay. The 1.5s we never really had any success with. Just didn't fit right, right? Now, a lot of folks complain about and say, well, it's your environment, right? It's a data center. It's a fair thing. It's a data center. And so let me describe our environment, okay? We have those storage pods. And in that storage pods, the drives sit, and they sit vertically. They don't sit horizontally, which drives some people crazy, all right? Oh my goodness, they're not designed to sit like that. So they sit vertically. We put them in a container. It's got a top. It's enclosed. It's fan. It has a fan. We'll see later we actually monitor the temperature of the drives, right? But it's in an air-conditioned data center. They don't move very often. Matter of fact, some of the storage pods haven't moved in years, right? So that's the environment that they're in. Well-maintained. They get filtered electricity, all right? They don't have to worry about brownouts or anything like that. We don't have any cockroaches running around. There are no dust bunnies sitting around there. We don't drop them onto the floor too often. So it's actually a very interesting, the nice part about it is it's a nice environment, okay, and it's fairly stable, all right? So when we compare drives, some fit really well. Those are those little guys, those are those 2 terabyte ones down at the bottom. You can see that, right? Some of the 4s do really well. Some don't fit. It's as simple as that. And one of the things that really fascinates folks is that we use consumer drives. Yeah, we do. Right? That's what allowed us to go down to Costco and buy drives when we couldn't get them through our channel when we were doing drive farming. Right? We could just go down to the store and buy them because you could go down to the store and buy them. And they were consumer drives, right? For the most part. I'll talk a little bit about that later, right? And then some people say, well, have you ever compared them? I mean, gosh darn, those enterprise drives must be good, right? They got to be better. So, probably about 2 years, 3 years ago now, Brian did a little study. And we had a handful of enterprise drives that we used, not necessarily in the same way. We didn't use them as data storage. We used them as management drives and backup drives and so on. They were in the data center, but their use case was a little different. So it's not quite apples to apples, but he compared them, okay? And you can kind of see you don't really have a lot of years of service there. And he was soft on this. But when he went down and looked at the annualized failure rate at the time, consumer drives 4.1, enterprise drives 4.6, we kind of said, well, even if we're off by a lot, okay, is that really enough? Is it worth it to go spend money on an enterprise drive? Right? Interesting question. So we now have an experiment going on, okay, where we're doing this again. So we have 8 terabyte Seagates, and the M002 models are consumer drives. That's what they are. The M055s are enterprise drives by their classification, all right? And we put them into service. Now, the enterprise drives have only been in service for about a month and a half, 2 months, really, all right? So don't draw any conclusions yet, but maybe next year I'll come back and we'll talk about that and see if there's a real difference. This is apples and apples. These are in the same environment. They're sitting right next to each other in the data center. They're using for the same use case, right? You can probably say infant mortality up front, 2.38%. Oh, okay. What is it going to come down to, all right? So we have an ability to compare these now. Now, why does that matter? Well, these come with 2 years of warranty. Those come with 5 years of warranty. If you were to buy them on the street, okay, we got a really good deal because that model, by the way, is end-of-lifed, and we were able to get our hands on them. That was the only reason we were able to do it, because we wouldn't generally pay for an enterprise drive. One exception, we did buy 45 HGST helium drives about 2.5 years ago. It was the most expensive storage pod we ever built. And it was like the price of 3 of them. It was crazy. It was an experiment. We were giddy with money or something. We did it once. Their failure rate, by the way, sits right in between those 2 numbers over time. So it's about 2% for the HGSTs. So we'll look at this. We'll look and see. Because what's important, all right? What's important to us? This is us, not you, us, right? Cost per gigabyte, all right? The software we run in our data system doesn't care necessarily about drive failures. It's really not important. It's way down there. Failure rates are down there, all right? Yeah, you get 10 or 12%, you care a lot. The difference between 1% and 2% annualized failure rate is like 3 drives, all right? It's nothing for us. So it's money. It's cost per gigabyte, which currently runs about 2.5 to 3 cents for the prices that we kind of get. All right, that's what matters, all right, to us. What we see, by the way, now, there used to be this wonderful curve where the price came down, 17, 15, 12, 11, so on and so forth. And then we had the island drive crisis, and it went like this for a while. And then it started to settle out and continue down. And it got down to about 4 cents. And it started to flatten out. And then it got down to 3.5, and then 2, 2.5. And now what happens is when a model gets down to about 2.5 cents a gigabyte, the model goes away. They don't add the size. Sometimes they add the size. Sometimes they just change the model number, and it goes back up to about 4.5 cents, and then it comes back down again. And then maybe they'll jump from 6 to 8, and then it jumps back up to 6 cents, and then it drops back down, and then you get a couple of model reservations. So I don't know where the floor is, but right now it feels like 2.5 cents, maybe 2 cents a gigabyte. Okay, I'm sure some of the larger companies like Google and those guys can get that number lower, but we're buying them in chunks of 5 to 10,000 a piece, so that's the kind of numbers we can see. What's just as important as cost? Power. Man, there ain't nothing worse. We put those 8 terabyte Seagate enterprise drives in, right? And they lit up like a Christmas tree, the power they use, all right? We have a rack, and a rack uses, I think it's 30 amps. 30 amps you power each device in the rack, right? But your limit is 24 by spec. So when we put 60 of those in a pod and we stashed it in, it literally blew the circuit, okay? It just too much power draw. The 8 terabyte consumer drives were right on the cusp. They run like 23.8 or so when you put 60 of them in. So we talked to Seagate, and Seagate actually gave us a setting. There's a power setting on an enterprise drive, which is really cool. We'd never seen one like that before. There's a little firmware setting you flip, and it actually reduces the power that you use. They didn't tell us exactly what it does to reduce the power, but when we did, it was actually able to bring the power down to be roughly equivalent to the power of a consumer drive, which is really kind of cool. And we still got performance out of it. So we load these drives up. When we load these drives up, the way it is a storage pod comes in, it becomes available on the internet, and people can load data on it, right? And we load it, that and all of its friends, until we get to about 80% full. And then after that, we just limit it, the amount of stuff that goes in. And those things typically run about 95% full, right? That's the way they normally run. So we measure that. We see how quickly those drives load and all of that, because it's all fair. And what we did, we compared the 8 terabyte Seagate consumer drives to the enterprise drives. The enterprise drives load about 40% faster, which makes sense. The spindle speed is a lot faster. The RPMs are a lot faster, right? So it makes perfectly good sense. But that was even after we lowered the power. So pretty cool. They loaded data faster. Now, in our environment, that's not interesting, because all that means is they just get online more often for data. Okay? In your environment, that may be something that's quite interesting for you to do that. The other thing is fitting our usage. So they were talking a little bit earlier about SMR drives. We tried SMR drives in our environment. We tried it in what we call a mini vault in our lab. And think about the model I just explained to you. We write a bunch of data out to something. That works really, really cool. But then what happens is over time, that data, some of that data needs to get deleted, okay? Customer goes away. A customer deletes their files. Certainly perfectly legitimate thing to do, right? And so with SMR files, that's a pain, okay? And then add in, we want to recover the space and reuse it, which is a double, triple pain. And so I think he was talking about kilobyte speeds, and yeah, kind of. That's exactly. We saw like a five times performance hit for SMR drives in our environment. So they just won't work for us. Not to, they're perfect for certain types of applications, but as soon as you have to lift up and erase or lift up and rewrite in a particular zone, everything comes to a complete halt for us. So it wasn't a good fit for our environment. We tried them. People asked, hey, how would they work? The answer is they don't work for us. They may work for you. This is the type of place. And to their credit, the drive manufacturers are not overselling them. They're saying, look, they're really good for this kind of thing. Write once and store it away, because if you ever have to do anything else with it, it's going to hurt. Failure rates, right? That's where it starts to get important. And usually when you get to see big numbers. So a number, 10% failure rate, 8% failure rate, yeah, okay, interesting. A 2% failure rate versus a 1% failure rate, not interesting at all. Warranty, we don't care. Right? We don't care. We do not have the time to go running around filling out stupid forms and tracking numbers and all of this kind of stuff for a drive failure. Sometimes, if you get in a bunch of them at the beginning and we put them in and 4 of them fail, on load testing or something like that, maybe we'll call up the place we bought them from, the reseller or whatever, and say, hey, 5 of these failed. And he'll just swap them out or something like that. But when you try to replace something under warranty, what do you get back? You don't get a new drive back. you get a refurb back, right? And I'd rather not have them in my data center, thank you. Somebody else's problem. So don't really care. You know, it's an interesting thing that some are 2 years and some are 5 years. What was amazing was, for example, during the Thailand drive crisis, is the warranty went from the same drive. Well, 1 week was 3 years, and then the next week was 1 year. Now, how did that happen? Right? And then finally, speed. I talked a little bit about that. Like I said, we put a box on the internet. Actually, we put a whole bunch of drives on the internet. There's always extra capacity for people sending us data. That's not the issue, ever the issue. So I don't care whether it spins at 5,400 RPMs or 72 or 1,500 or 15,000. They all work for us. So that's our environment. A little bit, I got a few more minutes here, talk about smart stats and SICK drives, and can you figure all of that out? Can you use smart stats to do that? So we use these 5 right now, okay? And you can see most of them apply, 3 of them apply to all of them apply to Seagate, and then a couple of them for other manufacturers, all right? Those are the 5 we kind of pay attention to. All right. What have we found when you analyze our data? All right. If a drive is SmartStat 5, pick a number, right? Reallocated sectors, right? This is a value greater than 0, with the raw value being greater than 0 in there. So when you look at the SmartStat and you say, hey, how many of the operational drives have that? 1.1% of them. How many of the failed drives had that attribute? Right? And you can see 42.2% and so on. So no single attribute is particularly good at picking it out, right? There's nothing there that jumps out and goes, wow, my goodness, 80% of the drives had SmartStat, the failed drives had SmartStat 188. Holy mackerel, that's a great indicator. It's not that simple. It's not that simple. Not that simple at all. Right? The other little trick, that thing you got to know, is that some of these, right, 180, there's 197. What happens is you may have a current sector count. So it says, oh, I'm having trouble, and that number starts to bump up. 1, 2, 3, 7, 10, blah, blah, blah. And then all of a sudden the drive says, I figured it out. Wait a minute, and it goes back down to 0. And so it depends on when you take your data snap to. Other ones, by the way, never do that. They just continue to add. So it's 1, it's 2, it's 3. We'll see in a second. High-fly writes do that. They just go and they go 1, 2, 3, 4, and so on, kind of a thing. But what we did is if you combine them all together, all right, and you say, look, if one or more of the attributes of those 5 attributes, right, triggers is greater than 0, percentage of operational drives that happens in is 4.2%. Percentage of failed drives is 76, well, it's 0.7%. All right? Does it matter? Okay? What we're doing when we look and that human being jumps in the thing, starts to look at the data and say, hey, I see one of them triggered. Well, I see there's a second one. Usually there's something else going on at that point with the drive too, right? And the drive gets pulled and checked, right? So can you decide, can you use those numbers? I don't know if that feels good enough to do that with. So a couple of years ago, some folks over at IBM over in Switzerland apparently had nothing to do. And they did a nice study, and they took all of the data that we have up to that point, and they analyzed it, and they did a lot of math that I don't understand. But you can look at the paper. There it is. If you look, predicting disk drive replacement, if you search for that, you'll probably see it. It's an IBM Switzerland paper, but there's the URL for it. You may also be able to find it on Marella Batatsu. But this is what they found. They created a set of rules and a predictability based on all of the drive stats, not just our little 5, right? Really cool, right? So we had 197 was one of ours, and they said, look, if that raw value is greater than or equal to 2, just throw the drive out, it's going to fail. That's pretty powerful. Right? And you can see the other combinations. How about, but look, if it's less than 2, and some of the other values are certain ranges and so on and so forth, it's a healthy drive. Don't replace it. All right? Now, that's starting to get to be pretty interesting. And we've seen a couple of other folks who have sent us data as well and said, hey, we have looked at it. And the only question they ever come up with is that, remember I said smart stats number earlier on? So these guys have decided that they went and said, could we use smart stats to predict failure? Now, one of the things that we're going to do over the next 3 to 6 months, depending on how much time I have, is their data stopped at the end of 2015. So let's see if they're right for 2016. Let's see if I have a drive with a raw value of greater than 2, did it fail? Right? I mean, they said 100% confidence interval. That's easy. That's a 1 or a 0, right? So it'll be kind of fun to see. They also did the same thing for HGST and Hitachi drives. The previous one was for Seagate drives, by the way. And they did the same thing for them. And the other vendors, we just don't have enough drives for that they could do the analysis on. But these two here, right? And as you notice, slightly different numbers. If the smart value, 197, is greater than 1, and smart 3 raw is greater than 626, and I don't know what that one is off the top of my head. I don't have it memorized, all 254 of them. Replace the drive. 100% confidence interval. So what we'll do is we'll test this, okay, against our data for 2016 and potentially up as much of it as we have in 2017 and see how well it was at good at predicting. Yes?
What's the time limit? I mean, all drives fail eventually.
Yeah, they do. That's a really good question because somebody else did an analysis of this from what they called what's the survivability rate? This is a failure rate. They looked at it from the other side, which is what's the survivability of trimes, and so when does it go to 0? And from the data, they were out at 12 or 14 years, but of course they didn't have the data, so you're just drawing a fake line at that point. But I think they had the data. Their forecast was like someplace in the 12 to 14-year range. Every drive should fail. Now, in this room, there's going to be somebody who says, well, I've had a drive for 17 years and it still works. So, so it's a possibility. But the real issue is what's your confidence of, what's a good number for you? If it's 95%, if you had 100 drives and 95 failure rate, you're going to start, and you want to be at 95, they may only be 3 or 4 years. As to what you want to do. There have been implementations, the folks at Netflix, for example, did this a long time ago where they took our pod design and they did a lot of fun stuff with it. But what they did is that they stored data, their movies on these storage pods, their own design, again, but on the drives. And they would store them all out there and close it up and send it out to various places around the country, so it was closer to where people were downloading from. And the reason that, and then what would happen is, of course, is over time, the drives would fail, but they needed about 3 to 4 years worth of that. What they figured if every drive in there could fail after 4 years, and they didn't care, because most of the time people weren't going to watch those movies anymore. And so, right? And if they were, they would only be the only person watching that movie, and so streaming it from a central data center was not a problem. So it was a pretty good model. And I've seen that model taken care of. So I don't know if there's a real hard number that says after 12 years everything ends or something like that, but we have seen that model before. I don't remember which one. One of the a couple of the different quarterly reports that I've done, I've called out that model. There's a guy over in New Zealand who did the analysis. Catch me, if you want to know about that analysis, catch me and I'll find it for you. I don't have the reference right off the top of my head. All right? And just for fun, what other things that we look at is, I mentioned earlier, high fly rights. Right? That's when the head flies out, its parameters. Let's just go with that, or its normal range of operation, right? You'd think that would be a pretty good one. Right? If your drive heads are starting to wander a little bit on you, maybe you got some problems coming up. Well, the trouble we had with that one was it did a good job of predicting failure, but it also did a good job of, it happened a lot in operational drives. Right? So it wasn't particularly useful. But one of the things we observed was there's a clustering that goes on. So if you get high fly rights that occur in a short period of time, you have a problem. Right? Getting 52 high fly rights, one a week, is not an interesting thing. Getting 52 of them in an hour is a very interesting thing. And our system isn't particularly good, quite honestly, at monitoring at that level. That's not something that was built into our system. So it's a really interesting stat if you want to go chase it down. But you have to have that time component in there because generally that's what's going on. Another one was spin retries. So, hey, I just turned on the system. How many times does it take to try to spin this thing up, right? We don't turn off our systems very much. Hence, that's the problem with this one. So we couldn't get any data out of it, right? But you would think it makes perfectly good sense if you just apply a little logic and say, well, if I turn on the system and it doesn't spin up right away, it takes a couple of times, maybe something's going on with that drive. Maybe the lube is starting to get a little dry, or whatever the case may be, right? The spindle's not working. Whatever, the servo's, the motor's not kicking in right away, any number of different things. Maybe that's a problem, but we couldn't find it in ours just because we don't spin them up very often. We don't turn them off and turn them on. But in your environment, that may be a very interesting thing. If you're turning off your drive every day and turning it back on, that may be something to pay attention to. The other one that's always everyone's favorite is power cycling, right? Do I turn my computer off at the end of the day, or do I just leave the drive running? And I know there's things that take the drives down and shut them off and all of those kinds of pieces of software, especially in consumer drives, right? But we turn all of that off. So this is all I can tell you. Okay, one, we don't turn our drives off very often. I just said that. Okay, but for the drives that failed, right, they had a lot more power cycling going on. Right, we were turning them off and on for whatever reason, the pods that they were in. Right, and this is lifetime. So we may turn off a storage pod once a year, right? Maybe twice a year, something like that. So drives that we were turning off a little more often failed a little more often. Okay. Does that mean you should just leave everything running? I didn't say that because we really don't have enough cycles in there. I mean, to do it. But that's where the data kind of goes. Last little bit, temperature. Just for fun. I know Google did this a few years ago, and we got carried away with it. Again, one of the funny things we found is that failed drives are a little colder than drives that are operational, right? Which was really kind of weird because we didn't expect that. This is what happens. This is what it looks like in our data center, right? For all of the drives we have, the average temperature is roughly 78 degrees, 79 degrees Fahrenheit, right, 26 degrees Celsius. That's where most of the drives are, right? And with what I call a 30-day look back. So this isn't just at a given day. This is the average temperature over the previous 30 days. And that's important when you look at the next one, which is failures. Right? This is failures by manufacturer. Right? And so it's got that 30-day back. So one of the reasons why you need the 30-day backs is because if a drive fails, it probably doesn't produce much heat. Okay? It's just kind of sitting there. So you want to go look back and make sure you're seeing that. So the funny thing about it is that there's no, sometimes way down here, they'll heat up a little bit. That's probably some type of heat problem. But generally, drives don't seem to throw off a lot of heat. And this is, by the way, we're measuring the internal temperature of the drive with SmartStat 194. So that's inside the drive. That's not like the flow-through or anything like that, or the room temperature or anything like that. That's the temperature the drive's reporting. One of the coolest things is that the orange one, the Western Digital one, kind of looks like Batman's helmet. I just look at that and I go, that's what it is. It's either that or the guy from SpongeBob. Anyway. So interesting, our friends at HGST, right? Heat doesn't seem to be a particularly interesting. It can fail anywhere along the lines, right? Seagate seems to have a little point where they fail, and the Western Digital ones. That could be an anomaly based on the fact that we don't have a lot of Western Digital drives, hence we don't have a lot of Western Digital failures. So maybe that Batman cows kind of evens out a little bit. But it does look like it heats up a little bit before it fails. The Western Digital drives may give you a little bit of indication. If you start to see the temperature climb internally, they may be starting to go towards failure. If you remember, most of them were at 77, 78 degrees Fahrenheit, kind of a thing. All right, so that's what we do for a living, right? We actually do backup and cloud storage and all kinds of fun stuff like that for a living, and then my night job is playing around with this kind of data. We do record it. If you want it, let's see, I'll put it up there. That's the URL. You can go there, you can download it, you can play with it. We also listed all of the different reports we've done, so you can go look at all of the different reports there. It's all on that page, all right, and go play with it. I encourage you to do it. Now, the files are getting big, really, really big, so bring a good network connection, and you'll have to download them in pieces, but go play with them, have some fun. If you have some fun data that you'd like us to take a look at some point, let me know.
Okay, very good. Thanks, Andy. I'm sure there's questions, so yeah.
Is your pattern of use mostly write once, and how often do you maybe write multiple times to disk, and how often do you read roughly?
So the model is that predominantly mostly writes initially, and then once a drive settles into that about 95% full range, it's going to be read, write, mostly reads at that point, deletes at some point. We run what's called cleanup jobs every so often. It's one of those things we kind of batch up and run through, and then we delete files, and that makes the space available. And we write back to it until we get about 95, 98% again, and then it goes into that read cycle. So,
is the read cycle much less frequent than writing?
No. People want their data back, and so we give it to them, which is a good thing. But yeah, it's not as intense, and so we'll fill up, for example, a hard drive, an 8-terabyte hard drive will take, in a whole setup, will take something in the order of 45 to 60 days, just depends, and then it'll go into service for as long, just doing what I described. So, yeah. Yes, Tom.
So Andy, you've got mostly consumer hard disk drives.
Yeah.
And there's different ratings for these drives, but you do seem to observe what might be wear out. Do you see that correlating at all with like the warranty terms they typically have for those drives, like how many terabytes you can write on them, that sort of thing? I'm just wondering if you are seeing any real correlations.
It's a good question. So the correlation that we saw is When we had the drive crisis and warranties went from 3 years down to 1 year on consumer drives in particular, the drive failure rates went up substantially on those drives. You can relate that to the fact that it was difficult to get parts, hard to manufacture drives, all of those interesting things related to the Thailand drive crisis. But that was the only correlation that we ever really saw, specifically to warranty and so on and so forth. And to be honest, it's a fun thing to go and look at, but it has no effect on our business, so we don't spend a lot of time with it. Yes.
So are these all 54 and 7200 SATAs?
54s, there's some 59s in there, and they're all SATAs, yeah. And
They're all
then
SATAs.
yeah.
Have you guys looked at any, do you do drive firmware updates? Have you looked at firmware revs of drives and whether that correlates to failures? Have you looked at SATA control, specifics of SATA controllers and SATA controller firmware? Because it seems like a lot of that stuff might actually be a fairly significant secondary effect.
It is. So to answer the questions as we go, the other components certainly can contribute to failure as well, although certainly they contribute, let's just say, equally. Do we update firmware? When we get firmware updates from the suppliers, the manufacturers, we usually talk to them about what the nature of that is and see if it's something that's going to affect us or not. And then we can update the farm if we need to. So for example, the Seagate drives were an excellent example of that. We had 1,200 of them installed. We brought them up. We said, oh my goodness, look how much power they're using. Seagate said, well, here's a nice setting you can go to. It took a few minutes to go through and update the firmware setting on all of those things and go from there. Not normal behavior for us. We don't spend all day doing those kinds of things, but we do it. As it relates to other components, we're relatively consistent with the manufacturers we bought from. We buy generally from all of our backplanes and all of our SATA cards and cables and so on come from the same manufacturer. I suppose we could map them to lot numbers and all kinds of things like that. We've never done something like that. They might have different firmware as well. And the thing about it is we'll bring up a farm of drives, let's say, a 1,200 drives and they'll be Seagate. Then the next 1,200 drives in a vault will be a different manufacturer, HGST or whatever the case may be. So we've never done that breakdown. That's an interesting breakdown to do that.
For your outlier on the Seagate,
Yeah.
X drive with all those failures, that to me speaks of.
Could be. And I don't know the answer, if that's truly the case or not. Yes.
Two questions for you. First, with the number of spinning drives you guys have in the environment, have you witnessed any gyroscopic effect, macro or micro? And second, performance-wise, are you seeing it mainly in terms of faster RPM speed, or is it also a function of cache on the drives as well that drives that?
So, so the first answer, I believe, is no. Okay. The second one, the speed thing, again, that's not an important factor for us because we're just going to fill them up. Whether they fill in 45 days or 51 days, not an interesting thing because there's always another farm right behind it ready to take their place. We count something called it's basically a time in the future where we'll run out of space. If we deploy no more environment, when are we going to run out of space? And so we try to keep that number at least 90 days and preferably something over in the order of 180 days. So if we never deployed another drive, okay, we'd have 180 days worth of space. So we always back that up with another vault. In this case, we don't do pods anymore. We group the pods into a vault, and that's 1,200 drives going into play. So we just don't care as to how quickly or how slowly they fill, other than if it was something ridiculous like it took 180 days to fill. Yeah, okay, we'll probably never buy them again. But every drive we put in their environment goes through the mini lab first. And so we test them all, make sure they're right. we go through, we do load testing and everything like that, because if they're going to fall apart, I don't want them. The SMR drives are a great example, okay? They might have performed really well, although we kind of figured they wouldn't, but let's give them a chance. And when they didn't, I don't need to put them in my stats and yell at them at that point. I just need to say, we tried them, they didn't work our environment, good luck, you know, but they may work in yours. So, yeah.
Great. I also have two questions.
Yeah.
One, if you could please classify or describe how you classify an operational drive in your data set. Like, do you filter out all possible drives that have never failed? Or do you group them by like a large number of device days that they've been online? And second, do you currently remove drives from your data centers that have these abnormal smart values? Or do you actually wait for them to actually fail?
So we do, I'll get to the second one first. We have been known to remove them when they have the abnormal smarts values. It usually is in combination with, like I said, the human being, you just get a feel for them. My goodness, that had 0 yesterday, it now is 6. Okay, that's weird. What else is going on? Oh, look, I'm getting errors across the bus on it, you know, and so you take that drive out at that point. It actually doesn't get marked as a failure until it goes through the other tests and fails out. But that's the way we do it. And the first question was, now I forgot.
Operational drive.
Okay, so a drive is either failed or operational or in that quasi state of trying to decide if it is. But you won't, in our records, it'll look legitimate. It'll look like it stopped, but it won't have a 1. Okay, it'll just be a 0, and it'll stop recording drive days because we took it out of the environment. We test it out, it fails. Oh, my goodness, it failed, we give it a 1. Oh, it's still good. Okay, we'll put that out, we'll hold it for a spare. The reason we hold it for a spare is, quite honestly, we like to have all of the drives in a storage pod to be the same model. Just makes kind of sense. So if I have 45 or 60 drives of the same model, and I can't get that model anymore, I'd like to have a few spares in case something goes out and I substitute out, and we hold it. And if it comes back in, and you'll see that in the data sometimes, where something will be there, it'll be running, all of a sudden it'll just disappear. It'll be gone for 6 months, and then it'll show back up. Okay, and that's why we count drive days. So those 6 months don't count, okay, and then it goes and it runs, and let's say it fails 3 months later, then it has a failure, and all of those things become part of the record.
So the drives that you have failed every day previous to that was considered an operational drive.
That's correct, yes.
Do you consider those in your operational stats?
Absolutely, yeah. Yeah, that makes up makes up the data of all of the drive days that drive model, in that case, was operational, so yeah.
So hopefully this is an easy one. So as your drives are running, do you adjust the power parameters for them at all? Do you prevent them from spinning down, or is just out of the box running?
So it all depends. We talk to the drive manufacturer to see what they do when they shut the drives down. So for example, green drives, the newer green drives, were really a pain because they like to shut down. And our environment is a fairly active environment, even if it's just a read or something like that. So we generally don't like to spin the drives down, especially completely. Now, some of them have a mode where they'll kind of go a little bit asleep, but not really. And so we talk to the drive manufacturers about what they think the best way to do it is and change the firmware appropriately, if it's appropriate. We generally don't have to, but sometimes we found that if we shut off that mode entirely, so it just stays spinning, it's just better for the drive and its performance all the way around. And so they may not last 5 years, they may only last 4 years, but they're not going to be doing this kind of a thing and having trouble because they were failed and jerked back up and failed. They're not failed. They slow down, they come back up, slow down. There's nothing worse than doing that to a drive and just keep, up and down and up and down. So.
Okay. And then slightly related to that, you ever had a power outage at your data centers? And did you have any
So
drop
we
off
had
from
one back when one of our earlier data centers was in Oakland, and the janitorial crew hit the big red button. Can't tell you why. It wasn't just us, it was everybody in the data center. And yes, we had a data center, and Everybody in the company at that time literally got up and went to work at 2 o'clock in the morning down at the data center, so we could bring up the pods individually and bring them online. It took us about 4 or 5 hours to get all of that done. There's even a blog post about it with our CEO, Gleb, standing there, looking very tired, standing next to one of the little machines there. But yes, it has happened. The new place that we're in, the new places that we're in are multi-power. So the one that we were in initially wasn't. So it only has a single source of power. So not that we observed. The things just kind of, they just shut down. It's losing power. I mean, it's just like pulling a plug on a darn thing. It's not particularly elegant. It's a little problematic with the data. And so that was the hardest part of getting the things to getting the drives to FS check and make sure you knew where they were, and then reporting back. In that particular case, they were reporting back to an application on a Mac or a PC and comparing notes about where they left off. And so everything was fine. It just took a little while to catch up.
You brought up that SMR drives don't work in your environment, possibly due to the shingling, but it seems that the disk drive guys are starting to stretch their technology now, trying to get to HAMR, bit pattern media, and things like that. As those new technologies come out, do you foresee error rates going up? Do you foresee, I mean, that's one of the things you have to forward predict your costs. So as they stretch that technology, what are you seeing?
So the good part about where we are right now is that at least we get talked to by the manufacturers. we buy enough drives now so that we have a good relationship with most of the different manufacturers, and they'll clue us in as to what they're thinking about planning. The HAMR drives is a good example. We'll get an early sample of some of them. We'll try them out. We'll see what's going on. And again, for us, it's just about failure rates, because the software just covers all of that. I mean, it's not failure rates. The software covers the failure rates. And as long as the drives stay within a reasonable set of parameters of 2, 3, 4, 5% or something like that, we're fine. The SMR drives just didn't work because of the speed. If the HAMR drives don't work for some other attribute, the thing we worry about the most is we do use consumer drives. We pay a consumer drive price for those. How large are those going to get? Are they really going to make 16 terabyte consumer drives, for example? It's a good question. So that's more of a worry than a particular technology, because we have some visibility into that. So, all right.
Any other questions?
Thank you.
So a lunch is here. So what we're going to do is lunch is scheduled for 12:30. We're going to start lunch early, and then
There's a slight delay. All right. So please forgive me for the delay in the video image up there. The reason we are standing down here is because this is an unscheduled little mini talk we'll be giving in the middle of the conference today. Now, I'm not sure if you guys can sympathize with this, but sometimes my students are incredulous when I tell them, once upon a time, we operated computers with switches. I guess I'm getting old. But what we're doing here in the conference is we're looking forward. We're looking at where the state of technology and science is heading. But I introduced myself at the beginning of this conference. My name is Ahmed Amer. I'm with the Computer Engineering Department here at Santa Clara University. It has been our pleasure to host MassStore for these last 3 iterations. And there's a fact about the university that you might not know. We are, in fact, the oldest operating institute of higher education in California. Those of you who are fans of University of the Pacific, yes, I do know they were founded 2 years before us or so, but they didn't actually start operating till 3 years after they were founded, so technically we were first. Also, you might notice that you are here a part of MassStore. MassStore is in its 33rd iteration. It has been running for over approximately 40 years, if I'm not mistaken. It's one of the longest running storage conferences there are. So you are in one of the oldest campuses in the state. Actually, we've been a campus longer than it's been a state. And you are in one of the longest running conferences dealing with data storage. Now, what we're going to do here today is this was going to be my opportunity to thank Linda Kempster for her wonderful gift of donating this incredible collection to the university. Well, Linda is indeed a member of the Explorers Club. Some people seek glory and are recognized for it. Some people just make a difference and are recognized for the difference they've made. And to tell a little bit about her story, it's my immense pleasure to hand over this part of the mini talk to Linda Kempster and to thank her for her wonderful generosity and the incredible stories she was kind enough to share with me, and some of which she will share with you now. Thank you, Linda.
Thank you. Thank you. I think I'm going to be live on this microphone. Can you hear me okay? All right. Has anybody in this room heard me speak before over the years? A few people. That's great. There's a country song that says, I was country before country was cool. Well, I was storage before storage was cool. We were on paper. We didn't have PCs. We were going to conferences because we didn't have Google, and Wikipedia did not exist. And at that time, I started getting interested in storage media. I don't know exactly what caught my eye, but it changed my life. I started with view graphs, and then we advanced to 35 millimeter slides, and it wasn't until the last couple of presentations I even made that we used this kind of technology. We were so new back then that we didn't even know how to spell disk. There was an argument, is it D-I-S-C or D-I-S-K? And we decided that the D-I-S-C was for audio and video. And the D-I-S-K, because it was replicating hard disk at the time, was a D-I-S-K. That's how long ago we were. We were long ago enough that I had a friend that was 6'8", Leonard Lobb, and he would say, it's a gigadisk. And I said, I don't care how you pronounce it, it's a gigadisk. So these are some basic things that were going on way back when, before you guys ever got started with some of this. Technology, when I started, had to be simplified. I remember one time, I had 60 slides at one point in time, and I was speaking to librarians, and I was trying to get them to understand how I was going to get a piece of paper onto a piece of media. And they were clueless, because all they knew was about books. And they wanted to understand this, and I explained it. I said, you take a piece of paper, and you take a piece of screen door, like a screen from a door, and lay it on top. And you save the black, and you throw away the white. And that's how we digitize something. We put all the black stuff on the computer, on the media, but we remember where the white stuff was, okay? And they understood that. And then I was trying to explain compression to them, and they didn't understand that. And I said, if you have a cup of coffee, and I don't have a cup of coffee, you want to have a cup of coffee and you want to store it, you store the coffee. We call that freeze-dried coffee. And when you want it back, you put the hot water back in, and you have coffee again. And they understood compression, because that, again, was taking out the white and it's only storing the black. I got through 6 slides of my 60 slides, and those people left so knowledgeable and so excited about what they understood about this new technology, this new digital optical disc technology that I was talking about at the time. And that really taught me that it was important to make examples so that people could understand the relativity of what you were talking about. And before you leave here today, I might even teach you some relativity type of things. The last time I spoke at an IEEE Mass Storage Symposium was in 1986. And you guys weren't talking about exabytes then. We were just barely touching on terabytes and petabytes at the time. But I looked in my book, and I have a copy of, I wrote a book that was all my storage presentation, basically in paper. If you take an exabyte, and 1,000 exabytes is what? What's 1,000 exabytes? No, it's a zettabyte, okay? And 1,000 zettabytes is a yottabyte, and a yottabyte is a trillion bytes. And I had a guy in the Navy, now this is for you guys to know, this might hit this level. A guy in the Navy said when it gets really, really big, it's a brontobyte. So you just store that, because that's going to be something you may eventually run into, is what do we do with all these bytes and what do we call them next? So that was just kind of funny. I heard about optical storage in 1983 because in 1982 I was working at Northrop Corporation, and I was assigned to get all of these files out of this room and put them someplace. And so I got all the storage vendors to come to Northrop and tell me about their systems. And it was Kodak, and it was 3M, and it was microfilm. It was microfilm and microfiche, and that's what we had at the time. And that wasn't really exciting at the time. But the next year, somebody came from a company called Integrated Automation, and they had just gotten a gigadisk from Saudi Arabia, and it held 1 gigabyte. And it was amazing. It was I mean, you couldn't even explain it. You couldn't even understand it, because we were talking about paper and tons of paper and how much this would actually actually hold at the time. So it came out, and it was invented, it was used by Integrated Automation, which was here in Berkeley, California. I got to come up and see them in 1984. In 1983, though, still in 83, I went to a company called FileNet, and they were creating the jukebox to hold that 12-inch platter. So I walk in to see this, and here, now this is back before PCs or anything, they had this square box, cardboard box, and they had 2 black lines on it, and that represented a PC with 4 different screens, okay? And they had this little piece of string coming out, and this little serial box, like individual serials, with they drew 3 circles on it, and that was going to be the mouse, okay? And that was going to control this optical disc system and this jukebox. So that's where we were. We were inventing technology that we didn't even know how to use yet, but they were inventing a jukebox for that kind of piece of media. In summer of '84, I went to Kodak up in Rochester. They were creating jukebox for 5 1/4-inch drives. Now, 5 1/4 drives like this, when they came out, they only read them on one side. There was no way of doing it on both sides. So it was cheaper to make a whole bunch of drives and just have a whole bunch of these in there than to figure out how to flip these over or have two-sided drives. So Kodak was very proud of their jukebox that they were going to build for their Kodak information system, and it was a great big cardboard box, and it had all these little black squares on it. So this was the original type of prototype that we were in way back in the 80s, which was just kind of interesting at the time. But they were trying to help me visualize what they were actually trying to do. Optical disc was not accepted very readily. I showed that to my data processing guy at Northrop, and he told me, he said, "You aren't putting my data on that shiny blue thing." He had tape. He had 9-track tape, and that's what he trusted. And it was hard for people to understand where this was going from, or going to. In 1981, Sony had a great big meeting, big dinner party. All the managers were there, and they had like a U-shaped table, and Dr. Toshi Doi, one of their head engineers, was late, and he finally made his entrance. He walked in from the back of the room, he had a white lab coat on, went to the front, sat down without saying anything. There was a bowl there, and it had salad in there. And he put every kind of dressing that was on the table in the salad bowl, and then he proceeded to cut it up very, very small with a knife and fork. He was acting completely out of character. And then he reached into the bottom of that salad bowl, he pulled out this little round disc, wiped it off on his white lab coat, put it into a drive, and introduced CD audio to Sony in 1981. It's very cool. Dr. Toshi Doi, you can find him on Wikipedia. He died about 2 or 3 years ago, and I just felt sort of a personal sadness because he was always so part of the creation of CDs. Now, one of the things that was a problem with trying to go from microfilm to a digital storage like the 12-inch optical is that if you had a piece of microfilm, you could hold that up to the light and say, well, this is my document, the fourth one over, third one down, that's my document. But you couldn't take that optical disc and hold it up to the light and say, oh yeah, there's my document right there. But when the CD audio came out, people put it in their player and it played music. And nobody said, oh, I don't see the notes, it's not going to play. So once they understood that the notes were on the CD, then they started to believe that maybe their documents were on either the 12-inch or the 5 1/4-inch disc. And it was the acceptance of the CD-ROM, the CD audio, that I really believe took the whole optical disc system forward. When I moved from I don't want to skip anything here, when I moved back to Washington, D.C., I could actually spell optical disc. And Goddard Space Flight Center hired me in 1980, probably 1986, and I started working there with their storage. And they were having a problem because the market for the market for their tape systems was going down as the NASA budgets was going down because the flight systems and the Apollo missions and all of that stuff was being reduced. So they were looking for a new market. Oh, I got to go back and tell you these other stories too. They were looking for a new market. And so they really got interested in what we were trying to do with optical disc. And I'll get back to that for a second because you have to know about this part. This is a really good part. Dr. Toshi Doi, just to get back to where I was saying, invented this disc. How long was it? How much music did he make it? You know, because he's inventing this. How are you going to determine how much data went on it? He made it just the right length of time to hold the manager of Sony's favorite version of Beethoven's Ninth. And that's why it came out with the minutes that it had. So speaking of music, which is where I was going, this is out of a quote from Stan Kalthoff. This is where music really comes in. In Germany, the BASF invented magnetic tape in 1929. Been around a long time. Telefunken built a magnetic tape recorder called the magnetophone, but Adolf Hitler learned about the development and kept it a state secret. It was Bing Crosby who was shown one of the magnetophones as a war was coming to an end and realized its value. And he invested in Ampex Corporation to commercialize the tape recorder for the US. And that was in Office Systems 1991. So he wanted to record music. The reason he wanted to record music is because he wanted to record his music, get it just perfect, and then when the Philips radio hour came on, he had a perfect recording to play for everybody listening to the radio instead of having to sing, and he could go play golf while the Philips radio station was playing. And it turned out Ampex, who he invested in, was one of the companies that tried to go and take video or put video, live video, on tape. And there was Ampex, Sarnoff Labs, and RCA, and they were having this fight. So the World's Fair was coming up, April 1956, and The guy that finally had the tape with the first video images on it ran across the tarmac. You can imagine this with the security today. Ran across the tarmac and threw it through the window to the pilot of the plane that was flying to New York. They get to New York, they load this little VHS up. It was probably about like this. They loaded that thing up. They put it in a great big theater full of people that had these little teeny TVs around the edge, and they played the first ever video movie off of a recorder. This is 1956, that wasn't long ago. And here it came, and they said, well, what is it? It was a Tom Mix cowboy movie. And somebody in the audience says, well, which one's Tom Mix and which one's the horse? Does that tell you how hard that was to watch? They couldn't even tell the cowboy from the horse, but it was the first time video had ever been seen, had ever been recorded. And what happened from there is that they said, you know, that's such a great market. What if we can record that at home? Hey, VCR, right? The cartridge recorder came out, and you had this big battle between Japan's JVC's VHS and the Sony Betamax. Now, Sony, and I was told this by a Circuit City guy who sold these, Sony, they had the high quality, good quality picture, good quality sound. You put it in, you record it, ta-da, you got a great recording off the TV, watch it anytime you want to, right? That was the big deal. VHS was a little bit more inexpensive, less quality picture, less quality sound, put it in and watch it later. So what happened? The football players on Sunday afternoon would put that Betamax into their Beta and go play golf. Remember Bing Crosby and the golf? Now these football players playing golf, or the football fans playing golf, come back from their golf game, play the movie, and it would stop in the middle of the fourth quarter. Not a good idea. They took the Betas back to the store, bought the VHS, lousier picture, lousier sound, got the whole football game, they didn't care. So that's why the VHS became a more commercial, viable unit than the Sony Betamax. It, of course, is very, oh, hush up. It's very popular in the professional world, but the VHS won out because of the football games and playing golf. So you just never can tell. Anyway, I was getting back to NASA losing funding for their tapes, and they started looking for a new market. And when the 12-inch disc came out, my last presentation I really gave was in 2011, give or take, so I'm not well practiced. But when this came out, these were $1,600. 12 inches, 1 gigabyte, $1,600. You really didn't want to buy two of them to back this one up. So Honeywell saw a real opportunity. They took their VHS tape, they converted to digital, and they were able to put 5 gigabytes on a VHS tape, a VCR tape, that kind of style, and get 5 gigabytes for $35. And in 1990, at an AIM conference in Washington, D.C., which is the Association for Information Image Management, that VCR recorder, which held 600 tapes, you couldn't get down the aisle. So many people were excited about tape that was digital, that you could back up this optical stuff with, that it really changed the market. So Honeywell changed first, and then the other tape vendors changed following that period of time. And that really changed their market. That gave them a market. So now you've got optical coming out, you've got tape starting to replace the optical, and of course the obvious thing is saying, well, now that we've got this optical stuff, let's do the next thing with it. And of course, as the industry is, you have the same volume, now let's make it smaller. Let's put that same 1 gigabyte on something smaller. So out comes the 5¼ inch disc, like I mentioned before. And there was a guy that was trying to explain what was going on inside this optical platter, because nobody really could understand that. And again, it's a matter of trying to make it relevant. And this, Sam Coleman, is for you. There was a guy by the name of Olofsson who tried to help the reader visualize the technology behind the optical disc system. And he drew the following comparison between airplanes and optical disc drives. He said the dimensions are so small, now he's talking about this cartridge, are so small and the movements are so quick that they are unimaginable in terms of direct experience. If the whole apparatus were scaled up to a more familiar dimensions, an average optical drive reading a disc would be the equivalent of a Boeing 747 cruising at an altitude of 3 miles, never deviating by more than 12 feet, while accurately following a flight line 16 feet wide at an unvarying speed of 123 million miles an hour. Okay, that's what was going on. That's for you. I think he would win those races, right? 123 million miles an hour. Holy bucket. So that's really amazing. So what happened now is, now that you've got this laser, and when lasers first came out to do the recording, we had another argument. Are you going to create pits or bubbles? Okay, you burn a pit, it might fill up and smooth out. Oh, well, what if you make a bubble, you make a blister? You know, you hit the laser and it goes like this. Well, over time, that might smooth out. So which way are you going to go? Are you going to create a pit or a bubble? And I think, if I recall correctly, they decided on the bubble because the surface density of this circle here that was created by the bubble was more stable than the top of a hole. And so they created that. And that's which way they went with that. So now companies were excited about the laser technology, and then here comes tape. Tape says, well, let's see if we can get back into this game. So ICI Image Data over in Europe created this wonderful optical tape, which in 1986 held 1.012 terabytes in 1986. The drive for this cost $350,000. The tape itself costs $15,000, and it weighs 10 pounds in the morning. At night, by the time you carry it around, it weighs about 15 pounds, but it weighs 10 pounds, and it was a remarkable piece of ingenuity. And what happened with that, there actually ended up being 35 installations of that, and it ended up in numerous synthetic aperture radar facilities, which collected data from space. So it came down at a constant rate. It was filled up on that. And just to let you know, how many people have a terabyte on your PC, right? It's like nothing, right? It's 1 terabyte. You don't think about it being 999,999,999,999 plus 1. You think of it as being 1 terabyte. And so there it is. But to let you know, kind of give you a relative, that replaced 5,560 9-track tapes, which was a big standard. NARA used it for years and might still use it today. It can replace 1,481 of your music CDs, which means you could play 24/7 for 76 days and get barely to the end of that thing. Or you could you would hold it would hold 1,500,000 books. 500-page book is about 1.5 inches wide, and that would take up 125,000 feet of shelf space to hold 1 million books versus the optical tape. And in fact, 1 inch of that tape would hold 28.5 books. So it's interesting. The librarians would just love that stuff, wouldn't they? And one of these document images from here images on here would take up 2,000 file cabinets, which would cover 15,400 square feet and require 100 tons of paper to print from 1,700 trees. And it was an amazing technology when it came out. Now, where we were going to use it in the government, because I was in the government, was at the IRS. The IRS was going to record their document processing system. The IRS was going to record all of our tax reports on a 14-inch optical disc. This is the largest optical disc ever made, and it held 14.74 gigabytes, and that's on both sides. So you had that, and they would put that in a jukebox that held 100 of those platters. So you would record on that and back up on the tape. So you would back up on the tape an entire jukebox of optical platters, and that was exciting. And then the government said, no, and they pulled back the funding, and the project didn't go through, and basically Kodak never produced, never went any further with the disc. They were actually testing 50 and 75 gigabytes in the lab at the time that they got the call that it wasn't going to go through. The optical tape basically created the last one in 1987, came off the manufacturing, and ICI said no more. But what was being worked at the time by STK and IBM was to put that tape in a 3480 cassette. And as a lot of people know, this is the real workhorse of the tape world. I mean, you can put this in all those great big silos. I have all the pictures. You know more about them than I do. But at that time, it would hold 100 gigabytes. And in 1996, that was a lot in one place, 100 gigabytes. Nothing today from what I've seen, but it was a lot back then. And so it was interesting that the tape, the optical followed the tape followed the optical. Everything was determined by golf and music, so that was kind of interesting at the time also. Fast forward to today. I wrote this version of my book in April 1997, and somebody was trying to talk about how fast technology was improving. There was a friend of mine by the name of David Miles, and he said the first tape reel he ever saw was the Datamatic 1000. He recalled it weighed 25 pounds, so I'm thinking 2.5 times that. And it was 2 feet in diameter, what's that, like yay, give or take, and 3 inches across and held 150 kilobytes. Wahoo, right? And so this Dr. Paul Sappho was trying to relate that came out in the 40s or 50s to where we were at the time in 97. And he said that he was talking about the long-term social impact of information technology, and he said, if the automobile industry since 1945 followed information technology trends, today the average family car would cruise 100,000 miles an hour. It would get 500,000 miles of gas, or gallons of gas. It would get 500 miles to the gallon. It would ride more comfortably than a Rolls Royce and be so inexpensive that when you drove into the city, you'd just leave it at the curb. And that's where he was trying to relate the changes over time. I can't even relate those changes from 97 to 20 years later, where we stand today and what you're listening to. My first paper that I wrote was published in May of 1987 in a Goddard Mass Storage Symposium book. And at that time, it was so exciting, it was so big, and what you guys were doing was so important. And now I look at the problems that you're solving, and they've just got more zeros behind them. You're still working with some of the laboratories that we worked with at the time. So it's been very interesting. I never had a job doing this. This was my hobby. I did it because I loved it. I got excited about it. I stayed up all kinds of crazy hours. I got home from work, and this is what I worked on. I love traveling around the world talking about it. I spoke in Brazil 5 times, and in fact, my book was translated into Portuguese because they wanted to, at the time I spoke down there, they were only using microfilm. And I came in with this. I was like the Walmart of storage media, and all of a sudden they were going to be able to make choices. And I'll tell you what, all of the CDs were made in Brazil. I went to the factory. They took these plastic beads and they put them in these great big funnels like this, and as they melted, then they came down, they went in front of this fan, and they were blown onto a spinning disc. Where am I getting something close to something? They were blown onto a spinning disc to get it just the right thickness and just the even amount. So all of these little discs, and I'm sure that's where I got this blank one from. Where are you going to get a blank one? I got it from the factory in Brazil. But it was so interesting. Everything was so interesting going on around, and it was a hobby. I did it because what if you were asked by your boss, where do I put all this stuff? And you say, well, I know about A and B. But I come in and I say, I never worked for any of these people. A, B, C, D, E, F, and G. Now, where are you going to put your stuff? Here's all the choices. Where's it going in the future? Because the engineers kept me up to date. The engineers and the labs always kept me up to date because I was the one in front of the audience, not selling anything, telling you about all of the different companies, what they could do, the history of where they were, and the future of where they were going as far as the engineer in the labs knew. And so I just had a good time with it. I presented to Admiral Tuttle at the Pentagon, and that was very cool. I presented to the president of SAIC, and he's saying, yeah, stop talking, you're running out of time. And he was the only one that attended the presentation. I think he had so many questions, he didn't want everybody else to know that he had the questions. And he asked a lot of questions. And who knows where that information went. It was very interesting at the time. I presented to the FBI because they had 46 million fingerprint cards that would fill 123 Washington monuments if you stacked them all up. And I had a team with me, and they said, okay, now you show them that media, and we're going to watch their eyes. And if their eyes blink, we'll know that they're interested in that one, because they never say anything at these presentations. And so I started handing this stuff out and told them all my stories and everything. They started laughing and throwing this stuff around, and they were just having a great old time, the FBI was. And these people that were there to watch their eyes and see if they responded to anything, they left the room. We were just having a great time with the FBI and just talking to them and really getting a kick out of that stuff. And like I'd said, I changed the magnetic tape world from analog to digital because I needed to. So I'm a member of the club with John Glenn and Buzz Aldrin and some of those great people. And all I did was set out to help people. But in my wake, I beat Bill Gates in a survey by 14 points on who is most influential in the information technology industry. If I'd set out and somebody told me in 15 years, we want you to be more famous than Bill Gates, I would have quit right then. But you know what? All I wanted to do was help people. And I took a hobby and I helped people, and I did the best I could to represent this crazy industry called storage that I just thought was a lot of fun to talk about. So I leave you with this, and I have to tell you, my little tapes, I wore these little tapes, they held 615 megabytes, and in Brazil they called me, I was the famous Linda Kempster with the little tiny tapes. So my takeaway though is, how many have like 128 gigabytes in your phone? Little chips, right? Sure. Just to translate that, 1 gigabyte is 20,000 documents, 200 pounds of paper, and if you do the math, that 128 gigabytes represents 12.8 tons of paper. 12.8. 128 gigabyte, 12.8 tons. So whatever you have in your phone, that's how many, you could do the math and how many tons of paper that represents. And now you can go tell somebody else something very cool, and they'll go, wow, that's really cool. Thank you for your time. If you want to come over and look at any of this stuff, I'll be here all day. Appreciate your time. Thank you.
The sessions will start in about 15 minutes. Is Greg Tucker from Intel here? Greg Tucker?
and software together. So if you're familiar with Spark processors, we've introduced a number of processors over the years. Currently, we're shipping 2 processors, M7 and S7. They execute the Spark ISA, and what we introduced with them was software and silicon in the areas of security and in the areas of SQL acceleration for our database. And we've also worked with our Java teams and other teams that we can actually use the analytics acceleration for items outside the database. So that's what I'll specifically talk about today. As a background, our processor itself, and I'll just use M7 as an example, is a 32-core processor. Cores, are anyone familiar with multi-threaded processors? These are multi-threaded cores, 8 threads per core. On this block diagram on the right, you'll see there's a multi-level cache hierarchy, and the 3rd level cache there in gold is interesting from the standpoint that it's a shared cache, but it's partitioned to the point that it brings data that specific processor cores are using closer to those processors. So it's somewhat of a NUCA cache, and it allows us to migrate hot data to where it's needed. Another important thing about processor development, any type of processing, is being able to move information in and out of the processor. So one of the things we really focused on was memory bandwidth and I/O bandwidth. Anything to do with storage, anything to do with database in memory is how much information can you move in and out. So what we have is we have a up to 2 terabyte memory subsystem that supports over 170 gigabytes per second aggregate memory bandwidth, which is significantly higher than what you can find in most processors out there today. The thing I will address today is this notion of data analytics acceleration. So this is hardware specifically developed with our software teams. That's domain specific. Low power, very high performance, and I'll show you some examples. These processors, these systems, the software is all shipping today. And at the end of this presentation, I'll even give you some links to Oracle Cloud Development that you can all just sign up into and you can try out for yourself and experiment and test yourself and see these results. We have SMP scalability, so getting over 400 gigabytes per second in and out of the processor to other processors, and significantly also high I/O bandwidth for PCI adapters. Specifically, it is the world's fastest conventional microprocessor. This was introduced in 2015. It holds a number of world records, CPU-intensive throughput, Java, database, ERP. What I'm going to focus on, though, is the left-hand side of this slide, which is on top of that is what we brought by working together, forward with hardware-software co-engineering with our database and our Java teams. So the first thing I'll talk about is security in silicon. And you see the red highlights there is it didn't take a significant amount of die area on the die. That's a die microphotograph. But it's very high performance and very low power. And what we're able to do is put 32 of these cryptographic accelerators on the die. There's a very wide range from SHA to RSA to ECC to AES that is supported by each of those units. They all run independently. As you can see, they can do public key encryption, they can do bulk encryption. You can see the hash functions that are in there. It's extremely comprehensive, and there's actually some competitive comparisons here to some other reasonably contemporary processors. So as an examples of what we get out of that from a performance standpoint is here at AES 128 CBC, basically 83 gigabytes per second, which is so many times faster than, from a bandwidth standpoint, than what we see on our other processors out there. Same thing for SHA-512. We're basically running about half what the memory bandwidth can provide with those 32 cores. So, we're basically looking at order of magnitude improvements versus what we can get on other processors. And this is by just designing custom silicon to perform these functions. Same thing, looking at this on a per core basis, not just on an overall throughput basis. AES CFB, AES 256 there, and SHA 512 again. We're looking at on a core basis 2 times, 7 times. And again, it's by just developing custom silicon and custom functions to perform these operations. What it brings to systems is that the overhead of performing encryption in the data center becomes very small, almost negligible. So today people hold back from deploying, encryption and all in their data center because the performance overhead is too high. This is an example, if any of you are familiar with a Java multi-tier application database benchmark. This here is Spec J Enterprise. And what it is there's application server and a database server. So we encrypted all of the network, you can see at the bottom, and we encrypted all the data on the Oracle database using TDE. And the performance difference when we ran that benchmark was 2%. So the enablement is now basically you want security throughout your data center, throughout your cluster, throughout all your users. Another thing I'll talk about is then query acceleration and capacity in silicon, which is some of our decompression capability. So in the middle of the die there on the ends, we have 4 blocks of hardware accelerators. And you can see, again, not a very large investment in die area, not a large investment in power. But by developing domain-specific hardware, we can actually optimize the hardware for the operations and the functions we're trying to perform. So we have 32 of these analytics pipelines built on the die in those 4 blocks. So it's somewhat like I said, we have a 32-core processor. It's somewhat like adding 32 additional processors. They can actually operate up to 170 billion rows per second. And what they do is not only do they perform operations, but they run concurrently with the other cores on the die. So in this case here, of course, could be running OLTP operations while the analytics accelerators are running low-level operations for data analytics. Another thing they do is, again, this is domain-specific, so they actually are aware of how data is compressed. And they decompress it on the fly and feed it into their pipeline without writing it back to memory. So there's a memory bandwidth savings, there's a power savings with that. So it's almost like adding a number of specialized cores because we're not doing a decompress into memory, pull back out, and then operate on it. So we call that a fused operation. So if you look at the pipeline on that processor, at the very bottom of the block diagram here, there's a set of input queues, and they are sitting on that on-chip network. So they have full access to all of the memory bandwidth, just like any of the cores. Okay. The first step they do is they perform decompression, and then you'll see through the rest of it, they do a set of operations that are programmed to do. Then they reformat the results, and they push the information back out. They run concurrently. They can run asynchronous and concurrent with the cores, or they can run synchronously. And what we did is we developed a user-level fine-grained synchronization primitive to maintain very low overhead between the cores synchronizing with these accelerators. So what we end up with is very high performance at low power. And again, it gets to utilize, it can maximize all of the memory bandwidth of the processor. So the first thing that these accelerators can do is they understand how information is encrypted. We use a combination of dictionary encoding and run length encoding and some specific proprietary compression on top of that. And they recognize that, and the accelerators, each accelerator can sit there and take the stream, decompress it, and operate it specifically on the decompressed information as it's encoded. So, and again, it does that without writing back to memory. So here's a behind the scenes. So again, each of those, what they do is, each of those accelerators at the very top of the block diagram here, they can pull information from another one of the pipelines. So we can actually pipeline from one to another. They can pull the information from an L3 cache that any core had been working on. They can pull the information from DRAM anywhere on the die or anywhere in the SMP. They then perform inline the decompression operation. They take that, they unpack the input, and there's a set of functions that they can perform, whether it's lookups or predicate evaluations or filtering. They then apply the run length on top of that, set up the outputs, and can then pass that on to another pipeline, back into an L3 cache, that's specific to a core, which we can tell it specifically which L3 cache partition to put to send it back to, or into DRAM. And each one of those 32 pipelines before that operation. The operations include scans here, selects, translations, and extracts. So we can do single value range comparisons, each pipeline can. So it's good for searches, searches on range and values, key value pairs, even things beyond SQL. It's also used, and you'll see here, in some XML and JSON processing. We can do selections, filtering functions. We can do lookups to do translations, and of course we can do, and of course the accelerator also does extractions, which is a decompression operation. So it's not only used for the database, which is one of our initial uses for it. We work closely with the Oracle database team. It can actually be used with domain-specific languages. For instance, like Java streams, that's one example you'll see here, as well as some others. It's accessed, and all those applications can access it coming down to the hardware. The basic library that everyone uses is called libdax. Okay. So the database comes down and uses that. User applications can use that, or they can use a higher level API. And we have two different libvector libraries that provide higher level functions for applications. And this is actually available for use in the Oracle Cloud, which I'll make sure I'll show you we have links to. So the libdax library is a very low level C interface, and it does all the DAX functions that I talked about. It's thread safe, and it supports multiple different clients. libvector is a higher level package, performs higher level functions. It's used many times with Java streams and Java vectors. So as an example here, if you look at the very low level performance, all right, if we just compare running the low level scans, the low level filters, DAX to running the cores. We took an example here of 15 million lines, and we had 12 different columns of different types of data, but 8, 16, and 32 bits. And you can see the performance advantage between running with the accelerator offload versus running with the cores. And 8-bit operations is significant, and as the elements get wider, the limitation ends up becoming memory bandwidth. But again, we're looking at, many times, 5, 10, 15 times performance improvement for those operations. And again, at very low power, because there's very small silicon invested in doing that. We've actually integrated this with Java streams. All right. It's actually out there in the community. The library is available, and a number of different Java streams functions we're seeing anywhere from 3 to 20 times improvements as well. This is all out there today in the community. It's even being used in other ways. There's other users in the community using it for machine learning, from other types of scans, from other types of streams. And again, they're seeing multiple times performance improvements over using cores alone. So again, they're using the APIs and they're running applications and leveraging the libraries and finding some significant performance improvements. So this is all available in the Silicon Developer Cloud. All right. It's available to universities, researchers, customers, partners. You basically sign up. There's a click-through license agreement. It uses its access through Solaris and Solaris zones. There's APIs. There's use cases. There's code examples. All right. There's pre-built templates. And again, it's a way of trying out and experimenting with your own applications and exploiting the capability we have there. And again, lastly, so this is some more resources here. There's the cloud itself at the bottom, and there's actually a whole bunch of different write-ups on using our libraries and our stream processing in our Spark microprocessors. Okay, thank you.
Yeah, I'll pull this around.
I was just wondering, does your crypto support include tamper-resistant root of trust stuff, or is it just purely an accelerator for the algorithms?
The crypto units themselves, all right, don't, root of trust is different from the crypto units themselves.
If you could ask, maybe come out to the aisle, there's a couple of questions. Go ahead, John.
So your mention of machine learning in 4 to 5 times faster in comparison to Broadwell, or in comparison to what?
Oh, this was comparison to running with our cores. They basically ran the applications with our cores, and then they used the library, much like I showed the database applications here. So if we back up, these are all based on them running on those M7, right? And running their code on the cores, right? And then leveraging the libraries and refactoring their code for the libraries and the performance speed-ups they got. So this is a spark-to-spark improvement.
Okay.
What is the main bus that brings the data in and out of the chip?
I'm sorry?
What is the main bus that?
Oh, the main bus? Okay. So what we have here is, let me get back here. So there's a number of buses, all right? On the right and left-hand side of the buses, these are serial links. They run at, let me think long back, 16 gigabits per second, I believe, no, 12.8, I believe. And all those links run serial, and they're wide. They're so many lanes wide, and they run to these ASICs that are interfaces to our memory DIMMs. And the collection of the SerDes bandwidth there is way over 170 gigabytes per second, but 170 gigabytes per second is the actual data we can pull in and out of DRAMs. From the SMP standpoint, if you look at the top and bottom, there's something called coherence and scalability links. Those run at slightly over 18 gigabits per second per link, and there are you can do the division, but it's over 444 gigabytes per second at the pins of the chip without that's payload. That's without CRC or any link level overheads. So that's the amount of actual information we can move in and out of the chip to other processors. So that's over a whole set of links running at 18 gigabits per second. Then the third set of links are these I/O links that are called ILs. If you can see those connect to an I/O ASIC, and those are also running at 18 gigabits per second, and they can sustain they can actually achieve maximum from a PCI standpoint, 127 gigabytes per second. So there's a significant amount of data that we can push in and out of the processor because we're at a relatively high core count, relatively high thread count.
So the interconnect between the cores, are they like a crossbar or?
The on-chip network, okay. The on-chip network is actually 3 networks. It is a data mesh. The data network is a mesh, all right? It's roughly, if I remember this, half a terabyte per direction, all right? On top of that, it resides a set of request rings, all right? So all requests are sent over a set of rings. And then there's a direct point-to-point response network. So there's actually 3 networks that make up that on-chip network.
Interesting. And the ring, is it a token type of based ring? Or
No, it's not token. It is very low latency. Everything's flying by, and we're snarfing it. Every partition, every one of these partitions here, L3 cache partitions, we're snarfing data off, filtering it, whether that partition needs to see it or not, dumping whatever it doesn't need to keep up. So it's extremely low latency. There's no store and forward at all there.
Okay, thank you.
Thank you. One more question.
Great. So for each of your different encryption algorithms that you're running, do you have dedicated ASICs for each one?
I'm sorry?
Do you have a dedicated ASIC for each one of the encryption algorithms that you're running on the chip?
Oh, okay. So the inside the core, and you can see those blocks. See the size of that block? The core is roughly, there's basically 4 cores where you see 4 of those small blocks, there's 4 cores in there. So there's actually a set of functional units that are tailored, maybe not specifically to each algorithm, right?
Yep.
And some of them can be shared, I mean, some of them can be multi-use, right?
Gotcha.
But we actually, what we do is we look across all the algorithms and architect that crypto unit.
Gotcha.
Across all.
So are you doing it in hardware though, or do you have a specialized instruction set that's just dedicated to the crypto
We
algorithm?
have
or-
a specialized instruction set for it.
Gotcha. Gotcha. Okay, cool. One last kind of part around the crypto. Do you just work with kind of Oracle, whatever your encryption, key management, or authorization acquisition is, or do you fall under utilize a standard authorization acquisition or key management technology?
I can't answer that. I believe it's the latter. But I think Michael Palmetter will be here. He's probably the right guy to ask.
Cool.
Right.
All right. Thank you.
Thanks a lot. All right, let's thank our speaker. All right. Thanks very much, Steve. Thank you. All right, our next speaker is Greg Tucker from Intel, and he'll be schooling us in, again, the similar issue of what Intel's doing in this area. So help him bring up his. Oh, did we? Did you want to use just? Do you want to have the handheld or the? Do you want the hanging mic? Do you have a preference?
Sure. A hanging mic.
A hanging mic. Okay, great. And then turn that off.
Try to change to
Okay.
this to doing the presentation.
Oh, I see. Okay, so you're going to use that?
Yeah.
Okay, got it. Okay. Okay, I'm looking for the hanging mic and I'm not seeing it. I'll go get you another one while she's working on that.
How do I change slides? Hit the down button.
Are you using HDMI? You can't use HDMI because we record, we take the signal from VGA.
Change back to VGA. Okay. Just a moment, magic. You can just use this because this is very sensitive. You just
we only put them in the library if they hit these points. And like I said, it favors, you know, there's something we can do with hand-coded assembly that'll make it run faster. And it's mostly about, not that compilers aren't great, but there's just some things they'll never do. So the functions are in a couple categories. Data protection, data integrity, we have RAID and erasure code functions, and a number of different CRCs, you know, everything from 16-bit to 64-bit CRCs, and a number of different polynomials. We have cryptographic hashing, which is the multi-buffer variety. I'll describe that more later. We have encryption, but not a complete crypto library. We've done just what storage really cares about, is the block ciphers. So we have fast block ciphers, and that's it. We try to keep it simple and not try to redo a whole other crypto library. And lastly, we have a special compression that we put in because it's well suited for storage applications. So I'll go into more of these in detail, but I wasn't going to talk too much about the CRCs and the crypto, just because I didn't want to, I guess. But you should know that, you know, we can do CRCs as one of these ones that's with hand-coded optimization. You can do you can run very fast. I think we run the latest is 0.18 cycles per byte. So small fractional cycles per byte. And we can do the CRC64 as fast as we can do many of the other 32-bit polynomials. And in crypto, again, we've optimized them down to many of them are single cycles per byte or fractional cycles per byte. So where is it used? There's actually a whole lot of integrations. Since we've gone open source, there's a lot of open source integrations, including HDFS has been integrated, Ceph, Swift, and you know, many other open source projects. I hear about new ones, you know, every week, really. Streaming encryption ones, Netflix has a paper where they talked about and using ISA-L functions. And so if you're using Netflix, you're already using ISA-L, I guess. Other dedupe and file systems, distributed file systems, enterprise file systems, and a whole lot of other proprietary projects. And because we're under a flexible BSD license, you can do open source projects or integrate into your proprietary projects. So next, compression. So what we have is a special fast deflate in the library. It's deflate RFC 1951. It's an old standard. It's been around forever. It's built into lots of different other standards, PNG, web standards. You know, there's a whole lot. It's everywhere. It's a lossless compression algorithm, and zlib is the famous library that uses it. So we're compatible with zlib streams, but we want to work on the go fast side, the -1, because this is an application of storage. Storage either seems to want the go as fast as you can in a reasonable compression ratio, or the compresses as hard as you can. And so they're used at different times. Usually the offline compression, they don't care so much about how long it takes. Just, you know, make it as small as possible, and every bit of compression ratio counts. And then, but when you're doing streaming, you're trying to do it inline or on the fly, then speed counts, and you need to keep up with the data. You have to run fast as possible, and it's just get as good a reasonable compression ratio. And so that's what we did with with our fast deflate. I should say the history. If you haven't tried it recently, we've made some recent improvements. We put a lot of time into this compression recently. Last year we had something we thought was great. It was about 12 cycles per byte, and it was a static Huffman compress, and it had pretty good deployment. And we thought that was as fast as we could go, really. And then we took another look at it, and we found we could make even more improvement. And so now it's down to, I think, 6.8 cycles per byte, and that's the static Huffman. And then we added a fully dynamic a Huffman that's comparable in compression ratio to zlib-1, and I think that's at 7.2 cycles per byte, so it's not too much slower. And with this, put us in another category, really. We're as fast or about as fast as other protocols that are built for speed. Snappy and LZ4 were made to go fast, and there's some limit on compression ratio. And in many cases, we're in line with faster than Snappy, and this is Calgary Corpa, but even on other Corpa, we're in line with the speeds of LZ4. But we have the compression ratio of other standards, even standards that were built after zlib that have become popular now. Brotli is by Google more recently, and Z-Standard by Facebook. And we're in line with their compression ratios, but much faster. So we're now up to about 5 times faster than zlib-1, and we're sort of the only one in this category, this upper right corner, which is go fast and have reasonable compression ratio. And we also have a decompress. It's about 2.5 times faster than zlib. So, and then what else we have that's unique is cryptographic hashing. And this is used in a lot of storage systems, of course, for either for data integrity or for dedupe. And it's something that is a traditionally high cycle per byte operation. And so if you're streaming gigabytes per second through your storage system and you're hashing every block for dedupe, you can quickly consume your machine with doing nothing but hashing. And so for that case, customers were looking for better throughput. And so the multi-buffer hashing is basically vectorized cryptographic hashes. So how it works is you have to have a bunch of independent hash jobs, and like you do in a storage system. And then you can put them together and then run them together in a vectorized instruction. And so MD5, SHA-1, SHA-256, SHA-512, we do various. And then the only downside is you have this something of an asynchronous interface. You have to submit to fill the lanes, and the lanes could be 4 to 32, depending on your hash and your architecture. But once you fill it, there's a little bit of an animation. You run them together in parallel. And then when they're done, you get all 4 to 32 hashes out at the same time. And so by doing this, it's inconvenient a bit for going from a synchronous interface to this asynchronous interface and having, queuing up these hash jobs. I'm not going to say it's easy, but if you can, the throughput is much higher. It can be 5 to 8 times the throughput of the single buffer hashes. And so for that reason, it's worth it for customers to implement the multi-buffer hash. But in addition, we have something else called multi-cache. And what this is tries to get the best of both worlds of this synchronous interface and the throughput of multi-buffer hashing. And what it does, it takes advantage of storage customers when they do cryptographic hashes, especially for dedupe. They don't care so much about all the properties of the cryptographic hash, mostly about collision probabilities. And so for that reason, they don't really care what the hash is, just that it has similar collision probabilities. So what we've done is we've taken the multi-buffer hashing basically, and we run it all together on one buffer. So you have 16 independent interleaved pieces of your block. We run them all together at the throughputs of multi-buffer hash, and then at the end you have a number of hashes and we hash them all together. So you get one digest basically that's similar characteristics of your cryptographic hash, but now it's synchronous and has a throughput of multi-buffer hashing. When what you get out is not exactly a SHA-1 or a SHA-256, of course, but like I said, storage customers, it's worth it when they can't do the asynchronous interface of the multi-buffer hashes. So it also, the multi-buffer hashing pairs pretty well with dedupe. And so as an example, you're streaming a bunch of data through your system. You have something that cuts it up into blocks typically. This could be a variable length chunker or a constant block chunker. And then as you get the chunks, decide the chunk boundaries, you pass them, you submit them to the multi-buffer hash. And so when you've queued up enough, filled the lanes, then it all runs together and you get all the hashes in at the same time. And then this can be your decision for your dedupe process, whether to keep the chunks. And so another good feature of this multi-buffer hash is we have a built-in scheduler. So this way, if you submit hashes, jobs with a variable length, they get fit together like a Tetris problem. So it keeps all the lanes full all the time. And so because it's vectorized, gen-to-gen hardware sees big benefits from this. So going from processors SSE to AVX, you can see quite a big jump in performance. And you can imagine when you're going to AVX 512, you'll see another jump. So finally, we have erasure codes too. So erasure codes are becoming pervasive in storage systems, and it seems everyone's implementing them. All the clouds and distributed storage ones are either have some or planning them. Hadoop, HDFS, Swift, Ceph, and other hyperscalers are also implementing them. And the reason why it's just the economics are irresistible. And it pairs well also with other storage systems that are doing replication by real replication. Other storage systems that have multiple copies of the data at the same time just make a policy of keep around at least 3, for instance, copies of the data so that they keep the replication. So this works great when it's hot, but in a tiered storage, when it gets warm or even cold, you don't want to keep 3 copies of the data. That's not the best way to utilize your storage. So erasure codes allows you to trade off your redundancy limits and just fractional increases in the storage footprint. So why weren't they using them before? Previously, it was thought to be expensive. The traditional way to do erasure codes is to read Solomon, and doing the general purpose Galois multiply was not native, and they were very slow. But we found a way to vectorize them, and they're now very fast. And so there's really no reason not to use them now. And just at one point, we can do block erasure codes like a 10.4 in fractional cycles per byte. I think it's 0.4 on a modern processor. And that corresponds to gigabytes per second, multiple gigabytes per second. So, and also, as we implemented the erasure codes, we picked, we can do any general Reed-Solomon erasure code. That means you can pick any matrix, encoding matrix you want. And the performance doesn't depend on the coefficients of the matrix you pick. So that keeps them very flexible, and you can do just about any, and there's millions of ways you can do Reed-Solomon erasure codes. You can match the parity and the sources, and Reed-Solomon erasure codes are optimal in the sense that they're maximum distance separable, and there's a very easy way, if you pick the right encoding matrix, to tell how many erasures you can support before you can't recover the data. And because they're fast, they really make other erasure code methods irrelevant. There's lots of different other erasure code systems out there. A lot of them were designed when it was slow to do general purpose multiplies, and so they replaced multiplies with a whole lot of XORs or other operations. And that's inherently just limiting your coefficient matrix to only special coefficient matrix. And then there's other ones. I know the system's based on fountain codes, and Mojet transform uses one, but they all have different downsides. They're not MDS, and they're usually not as fast. So I really can't think of any reason why you wouldn't. If you have fast Reed-Solomon erasure codes, you wouldn't. If you're designing a new system, you wouldn't use Reed-Solomon. So as I said, it's an open source project. It's available. It's split into two repos: the non-crypto part and the crypto part. And it's in a number of standard distros. It's in FreeBSD ports. It's in Clear Linux, Debian, Ubuntu. If you do apt-get libicel 2, I think, or libicel devel, you get the library package. And that's all I have. I have some performance matrix. I wasn't going to bore you with them, but quickly you can see the list. And it's really, we can do most operations now at single-digit cycles per byte or fractional cycles per byte. The multi-buffer hashes are down to just a couple cycles per byte. And like I said, these are 5 to 8 times faster than the single buffer versions. We can do block ciphers at 1 cycle per byte or less. And then RAID are so fast that they're almost immeasurable. And CRC, we can do 60, like I said, it's 64 as fast as we can do other polynomials. And in erasure codes are gigabytes per second, fractional cycles per byte. So that's it. Great. Yeah.
Question, please step up here.
So how does this library interface with some of the hardware accelerated features on Intel processors for like compression and cryptography?
That's a good question. So Intel does have other hardware assist, but this is completely separate.
Just totally
This is completely separate. This is the software-only library that we want, that will run on standard servers. There's other ways to get the hardware offload, but yeah, and they're very fast. But we found that when they go in the hardware offload, the algorithms go, there's even more demand for the software. People still want the optimized software versions.
All right.
Okay.
I'd like to introduce our next speaker, who's Per Simonsen, who's the CEO at MemoScale. And so Per was kind enough to come here all the way from Norway, so very much appreciated. His company, he'll talk to you about what they're doing. But again, they're leveraging these technologies within Intel and, in this case, ARM coprocessors. So we wanted to make sure we got ARM into the mix as well. So again, Per, thank you for coming, and over to you.
Yes, thank you. Yes, so hello, everyone. As Matthew mentioned, I'm the CEO of MemoScale, and today I'm going to talk to you about the status of erasure coding libraries and what performance improvements that have been achieved on both with software optimizations, but also with the development of new algorithms. So first, I'm going to talk to you a little bit about our company. So it's a quite small company, so it may be that you haven't heard about it before. Then I'm going to take a very brief introduction on erasure coding, and then I'm going to talk a little bit about erasure codes that we have developed. And towards the end, I will compare the performance of our library to some of these alternative libraries. So the MemoScale company. We are a startup. It's a spin-off company from the Norwegian University of Science and Technology. It was started in 2015, and it was a result of a research project in algorithm development within network coding, but also algorithms for data storage. This spring, we raised capital, and that was in order to commercialize this C library that we have, but also some plugins for open source storage systems. So the team consists of 6 people, so not a very large team, but it's a very hardcore tech team. We have some professors and PhD, and I myself have a background in both computer science and also some business. And our core competencies in our company is algorithm development and also optimizations. And some of our previous, or some of the team's previous accomplishments are providing the fastest unbroken SHA-3 candidate, which is called the Blue Midnight Wish. And then we also, as far as we know, have optimized an implementation of traditional type of read Solomon to become the fastest available today. So I'm not going to talk very much about what erasure coding is. I assume most people here know what it is, and also Greg had a good introduction on that. So I'm just going to flip quite fast through these slides. So this is replication, making copies of data. This configuration can tolerate 2 losses before you lose any data. With erasure coding, we take the data and we split it into fragments, and then we add some recovery fragments. And if we add 2 recovery fragments, this configuration will also be able to tolerate 2 losses. And the advantage of erasure coding, you can see that here. With the replication, we have 200% overhead. With erasure coding, we have 50% overhead. And that means that you can store twice as much in your storage system. Like in a real storage system, you will usually use more redundancy fragments than this. So this is a bit simplified example. So in many cases, erasure coding can actually improve the performance of the storage system compared to replication. But there are also some challenges, and these are especially when you recover lost data. And you might see very high network traffic and IOs. And also, when you calculate these redundancy fragments, it can be quite computationally intensive. And at MemoScale, we have worked at solving these challenges with erasure coding. And we do have some solutions to each of these. And if you implement this in your storage systems, you may see improved performance, you will also be able to achieve higher levels of cost savings by reducing the overhead. And also it can provide better protection against data loss. So I'm going to go a bit more into detail on a few of these. First, we have the reduced network traffic. And when I say recovery traffic, I mean the amount of data that you need to read and transfer over the network in order to recover any lost data. So if you reduce the recovery traffic, you can potentially have faster recovery because you need to move less data in your storage system. And if you have faster recovery, you will also achieve a better protection level for your data because the system recovers faster. And also you can potentially have more network capacity available in your system, which you can use for other purposes. And one of them is that you can potentially start to stretch your erasure coding configurations in order to reduce the overhead even more. So I'm going to show you how erasure coding increases the network traffic. So with replication, if something gets lost, you simply copy the data from one location to another one. With erasure coding, it's a bit more complicated because there are dependencies between the fragments that you stored. And that means that you need to get hold of at least as many fragments as you use data fragments in your erasure coding configuration. And that means that the amount of data that you need to read and transfer to recover a lost drive equals the lost data times how many data fragments you used in your erasure coding configuration. And that's with the normal Reed-Solomon erasure coding. We have developed some algorithms to solve this particular problem. And with these new algorithms, we are able to recover the data with only reading 1/3 of the data that you need to read and transfer with Reed-Solomon erasure coding. And this can significantly improve the recovery mechanisms in your erasure coded system. So I'm going to talk a little bit more about reducing the compute. So at MemScale, we have 3 erasure codes currently in our library. We have the code that reduced the network traffic, and then we have an optimized version of Reed-Solomon. And then we have also made a new code which is optimized for fast compute. And this new code, it has many of the same properties that Reed-Solomon does, so it's MDS. And these compute optimizations that we have done in our library, they are mostly for challenging compute scenarios when you have extremely low latency in your storage system, or you need to have very high throughput. And also for low-end processors, these can be useful. So since we are an independent company, we do optimize for all types of processors. And currently we have optimized for the Intel processor. We have some ARM optimizations. And we have also started optimizing for AMD. And we can also potentially optimize for other types of processors. So we have done some performance benchmarks and compared the performance of our library to 2 of the other ones on the market. One you have heard about earlier here, it's the Intel ISA library. And then also the J erasure library. Both of those are very good libraries and are commonly used today. So this is the test configuration. It's with 10 data blocks, 4 redundancy blocks, and then a block size of 4 megabytes, which means that the data will not, or the data, it's in memory tests where you read the data from the memory. So we have 1 core, and we measure how much data you are able to encode, excluding the redundancies. So we tested this Reed Solomon and also the MemoScale compute-optimized code. So first out, we have the Intel processor. And for this one, we saw that with the J-ratio, we were able to get 2 gigabytes per second in encoding speed. With the Intel ISA library, it was about 4 gigabytes per second. And we were able to double that up to 8 gigabytes with a Reed Solomon implementation. And then we also have results for this compute-optimized code, where we are approaching 13 gigabytes per second per core. And then we have got some requests to optimize for the ARM library, ARM processors. And so we did for this ARM A53 processor. And to be fair with ARM, this is a very low-end processor. It's being used in some of the low-end mobile phones. It's quite tiny compared to the Intel processor, and also it costs much less and has much less energy consumption. So, but still, it's interesting to see what is it possible to get done on this one. And here we have 200 gigabytes per second, 200 megabytes per second with the J-ratio library. With our Reed Solomon implementation, we reached about 500 megabytes. And then with our compute-optimized code, we are at about 1 gigabyte per second. Many of you have probably heard about these new processors that are coming out from ARM, now from AMD. They are based on the Zen architecture. So far, the Ryzen processor has been released, but there is also a server, or the Ryzen processor is the consumer version. There's also a Naples processor coming, and we have so far only gotten hold of a Ryzen processor, and we did some optimization for that, and we thought that we could share the results in case you were also interested in that. So here are the results for the Ryzen. It's a bit over 2 gigabytes for the J-ratio. With the MemoScale Reed Solomon, we are at 8, and with the compute-optimized code, we are at 13, approaching 14. So we will, of course, also optimize for the Naples processor when that arrives, and I think it's supposed to arrive later this quarter. So, in case someone wants to use this ratio code, we do have a MemoScale C library. It is for integration into storage systems, and it currently supports these 3 erasure codes that I mentioned before. We do provide support and updates, and also quality assurance is very important for us. So we do exhaustive tests of failures in the scenarios for these libraries in order to make sure that the libraries are bulletproof. So we also have some plugins for some open source storage systems. Currently we have a Swift plugin and a Ceph plugin. Both of those are for the Reed Solomon code and the compute optimized code. But soon also the Ceph plugin will support the code which reduces the network traffic. We have a beta version of a plugin for Hadoop. It works very well, but currently we need a general plugin architecture to be in place in HDFS before we can release that product. So that's all I have now.
Questions for Per? Blood sugar levels are dropping or something here. Okay.
question. Does your custom code support same configuration as Reed Solomon, meaning all number of data shards, number of parity?
Yeah, it does.
Okay. Which or what is the size of Galois field it works for?
I think it's best that my technical guy, which is with me here today, can answer those questions. So if you contact me afterwards, we can discuss that.
Thanks.
Any other questions? Okay, thank you again, Per. All right, great. We'll take a 15-minute break and then start the panel session at 3. So I see Peter. test. It worked. All right. You guys ready? Sure. Okay, we'll keep it, like I said. Okay, so we are going to have a panel now. We entitled it Limits of Open Source and Extreme Scale Storage Systems Design. It includes a bunch of very distinguished colleagues and accomplished experts in this field. Peter Brahm, who spoke earlier this morning, developer of Lustre, and now working in the campaign storage area with his new startup. Sean Roberts, who's worked with OpenStack Consortium and a bunch of other very advanced open source projects for doing clouds and other big systems. And then, of course, our other speaker, David Bonney, this morning with Los Alamos. So the genesis of this particular panel was the program committee met, this was about 3 or 4 months ago, and we were discussing various topics, and Ellen Salmon was on, and so Ellen, you should jump in here too at some point, but basically the question was, well, you know, these extreme scale systems are, you know, they require a lot of complex development. You don't find architects the caliber of the folks on this panel just randomly walking around the street. They're kind of few in number. They usually have to make a living. So expecting like some kind of like small nutshell of a project to balloon, although, you know, David's proof that it doesn't take a lot of people to make some very interesting things happen. So, this is sort of a loose panel, but the basic idea is how far can we go in terms of building system, you know, extreme scale systems with open source? Do we want to just use it as a set of components? Do we want to make sure that the entire design is open source? And if the entire design is open source, that then begs the question, is there a business model? Because we're extreme scales, typically a small number of systems. So then it might require some kind of funding. We have folks from the various parts of the federal government here tell us about, you know, can they long-term fund things like that? So that's the general gist. So is that enough to get you guys started? And if you want to throw some other thoughts in as well. So we could start with, anybody want to start, or I could start at the end with Sean? Do you have any opening statements?
I'm happy to take that.
Okay, go ahead, Peter.
Yeah, regarding the setting of this discussion, I think the first thing that came to my mind thinking about is that when you ask for a limit, you're looking at a boundary, and there are boundaries, I think, between open source and business, but there are also boundaries between storage software in particular and open source. And I think that is the area where I want to go first. I think it's, you know, the enormous success of Linux has not at all been achieved for storage software that is open source. Yet this valley is littered with proprietary companies, proprietary products that have never made it into Linux. And I think that this is a big tragedy somehow, that I say that not as a business person, but as somebody who loves open source. It's a big tragedy that the openness has not gone very far with the software. The flip side of that is to look at the limits for the business side. And I think that may explain perhaps also why many things have not been made open source. The problem is money. Developing software is extremely expensive, and somehow wallets open for hardware. They do not open for software development. Yeah, it is very, very difficult to get somebody to fund an open source project and do that at a level that can generate something that is of lasting value. And so I think it's something I cannot answer, but these are sort of my two key observations, is that I think there's a barrier with what money is available to do it. And sadly, there is, you know, a big limit to the results that have been achieved.
So I would generally agree. Invariably, the problem ends up being that the hardware side of storage isn't well understood by software developers and vice versa. Good software projects have a tendency to die because of misconfigured hardware. and lack of understanding how to build and implement. That being said, I think in the last few years, last maybe 6, 7 years, there have been some commercial open source projects that have been relatively successful, Ceph and Swift being two of the most notable. Full disclosure, I happen to know the founders of both those organizations, so I have a little bit of personal bias there, but they have been, the technology was acquired by Red Hat and put alongside Gluster and has been relatively well sold and successful, and Swift is a independently operating and profitable company its software is all open source as well, but still without well-configured hardware, both of those software storage systems do not work well. And generally the complaints you hear from people that complain either one of those products or open software-defined storage in general is bad. It's generally lack of knowledge of how to properly configure the hardware itself.
David, do you want? Before David, and I'd also like to, there's the mic up there, and so I really encourage people, feel free to jump up anytime during the panel, so just consider yourselves all part of the panel. If you have something, if you'd like to add an initial briefing, whatever, just feel free to jump up. But use that mic in the middle, please. Go ahead.
Well, I would say I mirror Peter's thoughts on this, and that it's very hard to find funding to get software developed at a scale of this sort, where a minor mistake early on could cost you the viability of the project when you scale it up. I mean, it's been pulling teeth trying to get funding to build MARFS to what it is now, and even that was only 2.5 people worth of time for the past couple of years. So it ends up being a small project, even at something that's as big scale as this. So it's tough.
Cool.
Yeah, I think that the technical difficulties that you mentioned, they are definitely there, But it's also very surprising. So why can the Linux kernel support 100 different CPU models and not several hardware enclosures and get the performance right, get the LEDs to blink, offer these cozy enclosure services? Yeah, none of it is really there.
Well, I think it comes down to the model for Linux is sort of there's sort of an oligarchy around Linux, and that's partly driven by interest level of people that want to be involved with it, and then Linus's judgment about those particular people, and then it's just, this actually gets to my first point that I wanted to make, which is that Peter Levine actually wrote, he's a VC at Andreessen Horowitz, and he wrote a blog that I wish I would have wrote, because I fully agree with it, but he was actually the CEO at ZenSource. Before that, he was the CEO and helped drive Veritas to great heights. But the net of what he basically said is the issue with open source is it doesn't have kind of a regular product management sort of infrastructure, except in some exceptions. And so, in general, it's a somewhat diffuse pool. This is speaking about Linux in particular. It's kind of a diffuse pool of developers that I think, as long as you're kind of right down the mainstream of how people use it, number one, and you're sort of in the zone of like this is supporting POSIX. This is a well-established, decades-long framework. It basically works. But when you want to innovate way outside the box, and that in a way that's not interesting to that core group, it's even difficult to sometimes get that technology into the kernel or around it. So what's your thought about that?
I actually think that the kernel community is very open-minded. So I got experimental file systems into the kernel twice, and they added new little pieces to the VFS and so on for me very, very quickly. I think it comes down to, building a reasonable relationship and being responsible about it. I somehow don't think that they're the obstacle, honestly. I think the core of this problem lies somewhere else.
I would say, so I used to work on PVFS and OrangeFS now, and getting that source code into the kernel was a very, very long road. And perhaps that's because it was viewed as an academic sort of testing file system, but it took on the order of 5 years to get into the Linux kernel. So I think there's just that if there's not a use case for the common user, there is a lot of resistance into getting it into the kernel at that point.
Yeah, I think, so Peter, I think I wouldn't actually disagree with you. I think it's just that it's sort of, some people have different experiences. So in your case, it's, I think certainly you came at it from a technical, obviously somebody they respect, and then it must, lined up. But I've seen the same thing, like two different topics. One might slide in, one and another might not. I can say for a fact, though, I'm not going to name names or anything, but there are specific innovations that happened in the storage system software stack in Linux that got bottlenecked going up through kind of the layer of kernel people below Linux that should never, in my personal opinion, shouldn't have gotten bottled up. The people that were working on them were very talented and I think well respected, but the thing, one of the things that is missing is in a normal software development, say commercial software development project, there's something called product management, and product management's driven by the sales guys yelling at, not directly at the engineers, they yell at product management, and then product management goes to engineering and says, hey, you need to do this. So that's why everybody hates product management, by the way. It's like one of the toughest jobs in a company. But in Linux, it's if somebody, if there's something that needed, commercially needed that you just mentioned, there really is no, not even in Red Hat. I worked at Red Hat. There truly isn't, even product management at Red Hat can't force the developers to do something even if it's really deeply needed by customers. So, John, do you want to add? Go ahead.
So a couple comments. I guess the first one is with the title of this talk, you're obviously trying to avoid controversy. My second comment is you're talking about Linux, which is great. I love Linux, but I think the fundamental problem with open source storage systems, especially those at extreme scale, have less to do with the kernel and more to do with the operational parameters under which those systems are operating, how they're tested, how they're verified, and how they're run in production. Storage is hard. Everyone in this room probably realizes that, right? And it takes a long time and a lot of effort to develop a system where someone can put their data, that they're going to trust it, and it's not going to corrupt their data or have problems with their data. If you put a Linux kernel on a compute node, and you play with that kernel and you run into some scheduling issues or something, oh, I'll just reboot the compute node and life goes on. You don't have that luxury in a lot of storage systems. Going back or rebooting or if something goes bad, people get sensitive if you corrupt their data or if it becomes unavailable. So that's part of the problem as well. So I don't think it's Linux. You can talk about a variety of different open source kernels, Linux being one of them. Obviously, there's a lot of different distros. You could talk about BSD. But I really think there's something fundamentally different about storage, and specifically storage at scale. And I don't think it's necessarily an open source problem, but I think open source has aggravated this situation. And I'll tell you what I mean. For a lot of companies, they look at open source projects and they go, well, I'll just take A, B, and C. I'll take some tape and some wire and we'll wrap it up and we'll call the system and we'll go out and sell it. And there's some companies that do that. And A, B, and C were never really intended to run together really well. Now you have an issue. And everyone wants something, but they don't want to put the effort in. So a lot of companies, not going to point fingers in the room, a lot of companies want to be able to use open source projects to build products to sell to customers. The national labs want to do what the national labs want to do. They want to do production computing or they want to do their research computing. They want to write papers. So everyone wants to do their little thing, but very few people want to fund the people like Dave to go off and do the really hard work or to sit there and do regression testing after regression testing, many man-months worth of effort to make sure the systems are reliable.
So I think, so your point is that it's not just the software that could be developed by the team, but actually the funding around like the actual, full-scale testing and hardening and
it's the hardening, it's the production use, it's everything that goes in it. And Peter should be well aware of this, having gone through, his gray hair period with Lustre. It's the exact same thing. Right? There's a lot of Lustre systems where if you run Lustre at 250 nodes, it's perfectly fine. But if you get up to a certain scale and you're doing something funny, you're off on the rough corner or the rough edge, maybe it's not going to work as well.
Although if the attitude about open source is right, that's potentially a good thing, right? Because that's the whole point. As Peter did releases of Lustre, they were going across multiple labs. You had,
well,
you know,
but open
that's part
source,
of how it's supposed to work, right?
But open source open source in that methodology only works for if it's someone in their bedroom at night that comes home and does some coding.
So I don't buy this at all. If Linux can run on billions of Android phones, which rarely ever get corrupted data, yeah, on the entire internet, what's in the cloud, is basically running Linux. Their storage systems are pretty darn good. And I, in fact, I think that an even greater failure than the open source development of storage software is the company's software.
But you're confusing the end use, aren't you? Me using my phone to store my contacts is different than Los Alamos running nuclear weapons code.
It's actually not different from the Veritas file system, for example. Yeah, it's the same kind of local sort of recovery that is extremely well developed. So I don't really think that commercial software can lay a claim to being a lot better. Yeah.
I don't believe that. I don't know if David would believe it. I've worked in DOE. The applications that people write are not nearly as well behaved as you'd like them to believe them to be. And the science that's used at these extreme scales, whether it's bioinformatics, fusion energy research, plasma dynamics, computational fluid dynamics, finite elements codes, all these codes can push file systems in some very extreme ways. And those are the sorts of things you're not going to find on your Android phone. And that's all I'll say.
So I think your points are well taken, but I think you confused a few things, and let me explain what I mean. So the experience of running at scale a few very huge clusters as opposed to millions of phones, radically different experience. So putting that aside, we're talking about a small number of really large clusters of storage systems. And that operational experience, historically, most of the organizations tend to jump towards, when they're going to make a spend of millions of dollars, they're going to jump towards somebody that can give them support. So over time, more organizations have gotten more experience with different non-commercial sources, like Ceph was installed. It is basically running all of the image processing and storage at Yahoo for probably the last 4 years. And that's many hundreds of petabytes of data, and it runs just fine. So historically, before that, there was all NetApp. This is just one example. And the reason why they did that is for no other reason other than they had a really strong relationship with NetApp. It wasn't that Yahoo wasn't using a lot of open source already. It was the strength of the support relationship with NetApp was stronger than the desire to try out something that was cheaper and maybe even more scalable. So once that friction became low enough, they went with the cheapest, most viable option they could, which happened to be Ceph at the time. So I think all organizations have the same experience, and if you can have a few people that develop enough experience or are smart enough to be able to support Ceph the same way they support EMC or NetApp or any of the other commercial versions or any of the IBM versions or traditional Linux operating system or file systems, then that's what you'll go with. So there's just been a lot of inertia for many, many years to support commercial versions because that's what the institutional knowledge was. That's the operational experience. So I don't think open source had as much to do with it, personally.
So I'll just add to that. I mean, there's the common saying, no one ever got fired for buying IBM. I mean, that exists because somebody won a some entity to point a finger at. And I think that's something that gets lost in translation between the people working on a problem and the managers sometimes, is the managers want to be able to point a finger at somebody that isn't someone that works for them. I will admit I don't have that opinion. I like being pointed at and said, you screwed it up, go fix it. But I am an outlier in that aspect. So I can see why having an open source system that you have to self-support could be a problem for a lot of companies, because you have people that just don't understand, why is the thing broken? It's just supposed to work. I paid so much money for all these developers and so much money for all this hardware. Why is it broken? And then you have to go point at your own local people.
So do you think that the aggregate cost of that support is actually higher or lower than doing the right kind of product development and finishing these kind of configuration issues off and management issues off so that the product is really widely usable? Because I think that that's the common theme in our discussion, is perhaps that that's where the boundary is of the usability. Yeah, so it doesn't become usable enough perhaps to spread really very far in many cases.
Right, so it's like, especially in the MARFS case, I know it has some rough edges in terms of configuration and stand-up, and we have only really qualified it on the systems that we've built it for. So as you expand that out, having that support is difficult, and I think it's good for growing people, but it's not great for growing revenue if you're trying to sell it.
I thought I'd share my experience with trying to, at NASA Goddard, I personally have been working on a entirely open source large-scale storage project that uses MD80M RAID extensively and simple JBOD. So there's no hardware incompatibilities with what I'm doing. You know, we just have JBODs presenting a bunch of disk. We started out with using Gluster, and that seemed plenty promising for until we got with, you know, when we had 15, 20 users maybe. Once the base started growing, we started incurring, you know, oddball problems that involved it. I'm not shy about poking around under the hood. There were a number of Gluster problems I fixed, poking around, you know, varlib, glusterd, et cetera, and manipulating content and values, that sort of thing to fix the files. The problem is that there's very little tolerance for, unlike other fields, which was pointed out earlier, there's very little tolerance for risk in data storage, particularly within the agency. You know, if we try a new technology for our compute systems and they're down for a day, well, we lost a day of wall time. You lose data, you know, years of somebody's work could be down the drain. So there's just very little tolerance for that. And eventually we shifted over to make use of GPFS as a function of that with all the same underlying technology. And that has scaled seamlessly up to about 15 petabytes today. So it's kind of my feeling that a lot of open source developers don't have the means to test their implementation at scale without support of customers. And so the customers end up becoming a lab of sorts for that. And, you know, I work out as much tolerance as I can for allocating hardware and testing that sort of thing, but there are limitations.
So do you think it would be a better world if customers somehow were more supportive of the finishing touches on the open source, more complex software products that we're talking about?
Maybe it's a tough problem to solve. You know, there's money behind. There are financial issues behind trying to test to scale like that, and it's really difficult to test every kind of scenario you might run into. You know, one problem we had with Gluster was semaphore handling. If user X runs the same makedir command on 20 nodes, well, it's going to work on one of them, and it's going to return a non-zero on 19 of those. And we have a lot of lazy developers who, you know, expect that kind of functionality to not yield errors. And there's, you know, 1,000 cases like that I can mention. And I don't know how you test everything that can happen to data at a data center in a lab environment, honestly. I realize I'm not throwing out solutions. It's just, you know.
Well, I think Okay, so we certainly can agree that something like Linux, it's very broadly used. It has a kind of a base. It has a base level of, high level of development. There's other components, rsync, or just many, fairly whatever moderate sized pieces of software. But so what I think we're hearing multiple times from you and from John is that once you get into these potentially large scale situations, then it becomes, okay, how do you maybe collaboratively test across multiple organizations so that that helps you move the ball forward. And I think you've had more experience. What's your thoughts there? Because you've had more experience than all of us. And then,
so
Sean,
first of all, I think that the portrait that you are sketching of Luster is actually completely wrong. Like
Gluster,
today,
not Luster, Gluster, G-L-U-S-T.
G-L-U-S-T. So I know very little about that. Yeah.
Okay.
So I think that to some degree, you see, Ceph and Luster have benefited sufficiently to become very widely accepted. By the way, Swift probably too. Yeah, these are what you would call probably success stories. Yeah, but I think for any of these success stories, there are many other systems that somehow didn't make it. Yeah, as I mentioned this morning, there is actually a need for a different kind of object store. Yeah, that the labs have been asking for, and probably many people would use it if it was available. And so I think it's not a few systems. It's, why are there hundreds and hundreds of successful companies that get acquired for, hundreds of millions or billions of dollars, yeah, for, a library of deduplication software, or some, many RAID companies got bought and so on. What would have happened if that money had been given back in some organized form of open source development, which, by the way, maybe OpenStack has much more the right kind of model for than the current storage development for Linux. Yeah, I'm quite open to say.
Some of the Linux storage development doesn't suit our needs very well because there seems to be a shift away from POSIX file systems with Swift and Ceph. And I know there is support for POSIX, but it was kind of an afterthought in Ceph rather than the forefront. And for us, that's a huge, huge problem because we have so much legacy code that has no maintainers to it anymore, but is still, blessed to produce useful scientific outputs. And we don't have, the staff to suddenly inherit and modify all those codes to work with, outside the confines of a POSIX file system.
Yeah, I would say that most of the new storage technologies that I've seen be successful are internet focused, and definitely they'll bolt on something like Fuse to support POSIX, but it's definitely not the focus.
Right,
so
and communities like
will be
mine are
terrible.
getting left behind as a function of that.
Yeah, so I don't see that likely changing. If anything, it's going to become more of a problem.
Right.
Just because of the scale of the data sets that the organizations or the problems that they're trying to solve are just getting so much larger, so much faster. Data science just as a field is just getting going. So it's only going to get more extreme, so that the support for POSIX is going to perhaps unintentionally become more and more tenuous. Yeah. So I would say that just to go back a little bit, the only companies that I know of that storage-wise that support, or I should say the projects that I know of that are focused on storage that I think that have been pretty successful, that are open source based, have a strong company or organization behind it that happen to open source the tech for because they felt like it was the right reason, but there's definitely a commercial aspect to it. So Swift has SwiftStack, and Ceph has DreamHost, which they sold the technology, or the support organization, I mean, to Red Hat. But there's always, the only reason Ceph existed, or the major reason why Ceph existed, was to support the hosting company. It wasn't built for altruistic reasons.
Well, therein lies a point. So when Peter Levine wrote his blog, he basically said the issue with open source companies, so this gets back to what we're all talking about, which is we know we've got great technology, we know we can make some things happen, but how do you make those finishing touches, how do you make that full product? And Peter Levine's point was that in his observation, he was the CEO of ZenSource, is the open source as a business model doesn't give you enough margin, it doesn't give you enough cash flow to basically fund development, sales, and support. So Red Hat is sort of the outlier of what you would think of as like a large-scale, publicly traded, company, right? But even Red Hat is, I think, market cap of 25 billion, 30 billion. I mean, Microsoft's 300 billion, Oracle 160. So the question is, if Peter Levine is correct, and I tend to believe he is, if I look at just the available evidence, it's how do we as a community, because a lot of us are either companies like Oracle, where we leverage Linux obviously in many, many products, one of which I'll be talking about shortly. You're at Ellen Salmon at NASA, we've got folks from other agencies here. How do you do want the technologies that folks, innovators like Peter Brahm can bring to the table, but how do you cooperate with him? How do we create models where we can get that last mile and everybody can win?
Yeah, so can the last mile actually be achieved without some kind of a buyout? You see, because the common theme about the sort of examples we are discussing is that they all at some point got a pretty good cash injection or support from a big company.
Yeah, and I mean, it's true, and I think that points to the fact that there's obviously a clear level of success and a clear level of utility, and it's worked, right? I mean, Luster's provided a tremendous amount of storage and Ceph and these other projects, but we're sort of making it. I think we're still kind of making it up as we go in terms of trying to make it happen, keep it consistent, and I think when folks, decision makers like Ellen and others at the agencies, they want the benefits of open source, the openness, the things they can change, but they want to manage the costs. I think that's what you're saying too. So, yeah, cool. All right. Any last comments from panel members or any final comment from folks in the audience? Go ahead. Yeah.
I'm from Pittsburgh Supercomputing Center. We do have a parallel file system.
Could you speak?
Yeah, we do have a parallel file system. So I fully echo the sentiments expressed by previous audience. So we have like 150 million files, like 5 petabyte storage. So it's very hard to test such an environment in the open source community, because we have different kind of scientist applications to all kinds of weird things. So I don't think the open source community can do that. And just because you can get the source code into the kernel doesn't mean it's going to be a lot of people.
Unless you're David Bonney,
right.
And you have.
Yeah. So that's
but you're right. Not everybody's David Bonney.
Yeah. So that's my comments.
But could somebody from the labs maybe comment whether testing with an open source product is in any way different from testing with a commercial product?
Well, it's very difficult because we have a file system called /2, because we have a large scale. We have a project called Bridges. Basically, have like 800 computer nodes, a couple of storage nodes. The user request reports, usually we have a support team. This usually comes like this. So I cannot read this file. The file cannot be read. LS is very slow, something like that. But from a development point of view, from my point of view, you have to know how to produce this bug, right? Step by step. You can never expect a regular user to do things like that. You basically have to kind of reverse engineering what has happened step by step, what has happened. So it's very hard to debug. Yeah. So my personal experience, I don't expect a lot of people have that level of file system development experience to deal with this issue. So I don't think we actually, speaking of the people who are talking about this funding for the software, we have at PSC, Pittsburgh Supercomputing, we have been lucky to get some fundings from National Archive and some DEEPS project from National Science Foundation. So we got multi-million dollars funding. we have some good people working on it. So we have been lucky to get some kind of, my view is like side money to fund this project to this point. So we have in production for 5 years now. But the experience shows us, I would say, very experienced, very hard to do this. And by the way, I used to work for a storage startup company, still running. So when I joined this PLC, they already have some project going on, like Zest used to produce this conference a while ago, 10 years ago. So my point is very hard to have an open storage solution like the Linux. Linux is good for what? Write a device driver. Anybody can write a device driver, right? Anybody in the home you have a GPU. It's not that expensive. But to play on a storage, you need hundreds of clients. Hundreds, not hundreds, several, like 10 storage nodes, and you have machine have terabytes. You cannot test that in your environment. You need a big investment to do that.
Okay, thank
That's
you.
my
So
point.
I'll let Peter and David have the last word on if you'd like.
I think I'm leaving the panel very sad. I was hoping to find an impassioned audience about open source storage software, but I'm not sure that I did. Yeah.
Well, I tried to get them to roll the beer barrels in at 5, but Ahmed is not letting me do that. Are you, Ahmed? No beer barrels. Anyway, no, we're going to have to. Okay, you want one quick observation, and then you.
I just wanted to offer one observation, and I love open source, and I love that you're up there. And my perspective is, open source in storage is young, very young. If you compare it to Linux kernel, who has been around, I think, 30 years now, so
25.
you have a lot of time to grow.
That's right. Thank you. David, any last thought?
So I would just say last words is that I think it's all level of exposure. Right, the Linux kernel's been around for 25 years, and people use it every day on their phones. No one's using exascale storage systems except for the people building them.
Yeah.
That's just where it ends.
So I would just add one small thing, just to totally give a slightly a different example, but in the same vein, that you can buy gear from Quanta, or you can buy it from Dell. But if you buy it from Dell, you're going to get a failure rate you would expect in the single digits. And also you'd be able to get it back to Dell and get a new unit very quickly. If you buy it from Quanta, you get a failure rate of somewhere in the range of 30% sometimes. So, there are going to be all kinds of different failure rates, but it's significantly cheaper. So if you want to invest in an engineering team that specialize, that can test and bring in the equipment and burn it in, you can save a hell of a lot of money, but you have to be willing to pay the price. So it's the same thing for open source.
I think that applies to software and hardware.
So this is perfect. This is a perfect seg into our next speaker, because he's going to tell you you're wrong, but that's okay. Because maybe you're right. I don't know. But yeah, your next speaker has got a different viewpoint. So let's thank our panel. Great job. Threw you into this with no planning. Thank you very much. Appreciate it. Test. Okay, so our next speaker is Michael Palmater. He is a senior director at Oracle, and he has works in our Converged Systems group, and he'll talk about the benefits of integrating hardware and software very directly.
Hello, folks. Can you hear me? Is this doing anything at all? No. What if I eat it? No?
Do you have it turned on? Did we turn it on? Oh, yeah.
Yeah, it's, I got full power. Yeah. Well, you know, the room's not that big, and I can be fairly loud if I try. Can you all hear me in the back? Okay. Oh, my goodness, there we go. Are we off?
Okay, you're good.
Oh, no, now I'm going to have to whisper. Okay, I'll put it down here. Higher? Really? Must be the monitors. I feel like I'm yelling at myself.
Put it back.
Put it back down here? Up like this. You know, I'm afraid to touch anything now. Okay. So, hello. Thank you very much for giving me the opportunity to join you today. It's been a very interesting discussion so far, at least this last panel conversation. And let me start by saying that I am not going to talk about the implementation of storage systems. I'm going to talk around storage, not about storage. Well, actually, maybe that's not quite true. I'll leave you to decide when I'm done. But I work in a product engineering organization at Oracle. I work in the systems unit. We're the folks that are responsible for doing the microprocessor design, and you had a session earlier today, I think, where you had 20 minutes of gory details. Or maybe that's not the right word. I guess it depends on how you feel about that. But you had lots of deep dive on the processor design. I think you heard a little bit about how we've optimized the new generation Spark processors for Oracle database. And I'll touch on some of that, but I'm actually going to talk a little more about why we're doing a lot of these things rather than trying to talk about what they are directly. And well, here, let me say this too. So it's late in the day, and I know that being informative is useful, but I think being interesting is more useful. So if you would rather that I danced or sang songs, I can do that, all right? But I cannot let you go to sleep, right? So, okay, so where are we now? Let me see if I can get this presentation up. So we have this big idea, there we go, at Oracle. It's this idea that you're going to have, computing systems on the other end of network connections, and those systems will be far, far away in data centers potentially owned and operated by people who aren't you. And we're thinking about calling this cloud. I don't know if that name's going to stick, but it makes sense to me. All right. Too dry, huh? All right, so there are some benchmark numbers. There's a disclaimer here. I trust you can all read it. Yeah? Okay. So I'm covered now legally, right? Okay, and by the way, nothing that I say here today can be construed to be the truth, nor can it be used in any contract. So if you really like something that I'm going to show you a picture of, you'll have to talk to somebody else about the commercial details. So, Oracle, we have this database product, very successful product. The landscape, the technological landscape that we are in today is pretty different from where we were when that technology was originally developed. In some ways, it's very fundamentally different. And part of that is because expectations around not only the implementation technologies, but the commercial models and the modes of deployment, of operation of that technology have changed dramatically. So, we went from a time when people were trying to decide whether they built their own relational database or licensed software from us to this modern era where it's all about cloud scale deployments and petabytes of data and applications that have global reach that are used by tens of millions of people, and just the scale, the pervasiveness of the technology, everything really has changed. Many of our customers today are very concerned about complexity. Complexity, by the way, is a problem you can never outrun because managing complexity is, I think, what most of us get paid to do, right? Yeah. So I'm not that old, but the very first system that I worked on, the first software I wrote was assembler for Timex Sinclair ZX81. Anybody here ever own a ZX81? See? I find that hard to believe, actually, but okay, I'll buy that. Couldn't afford one. Oh, yeah, well, I couldn't really either, but I don't know, somehow I got one. The complexity that we were confronted with at the time was pretty significant. And clearly there's been a lot of technological development. We've developed a lot of things like 4GLs, and we have much, much faster machines, and yet strangely enough, the work that I do today seems just as complex as the work that I was doing then. And what I realized some time ago is that our job is to stay ahead of complexity. We're trying to outrun an infinitely fast predator, and we just stay one step ahead. That's the best we can ever hope for. So we are dealing with complexity today. We'll always be dealing with complexity. The challenge is knowing just how far you can push things. There are a few things that have remained constant. Complexity is expensive, always has been, always will be, and complexity is not going away. Security is always important. It's always been important. It will become even more important in the future. That's likely never going to reach a limit either. Everyone is trying to optimize the investment of resources at an economic level. Just forget about commerce for the moment. By the way, I'm going to try and stay away from commerce. I'm going to talk about cost, but I mean raw kind of economic cost, right? Investment of effort, investment of time. And then agility, of course, is the ability to roll back things that we've done, the ability to make mistakes that aren't crippling for our various initiatives. So we need the ability to change our minds and sort out new things without having to write off all of our previous investments. These are all true, always have been and are today still true. So I'm going to talk a little bit about this large landscape now. I'll talk about cloud. So how many of you, offhand, do you guys know the speed of light if you measure it in miles per hour, a second? Yeah, I think 186,000 miles per second. Like infinitely fast, right? Well, I suspect you all being educated engineering people would know that that's not true, in fact. It's only about 100 kilometers per millisecond round trip through silica, which is remarkably slow. So here we have we're on the cusp of something that is transformational, right? We've got these large, these expansive, generally pretty reliable networks, and there are all these enterprises out there that are discovering the joys of connectivity at a scale with a level of ubiquitousness that we've never achieved before, right? And so we have this big conversation about cloud, and ultimately that's what cloud really comes from, right? Is this idea that I now have new tools that let me optimize locality. And locality as a pattern, by the way, is a really important pattern. I'm going to actually I'll be talking about stuff that's peripheral to locality here in a bunch of places. But it's an important thing to keep in mind is one of the central problems with cloud is moving large amounts of data over slightly unreliable, in some cases, and relatively slow networks. And again, even the best that we have are limited by the speed of light. So if you're thinking about transactional systems, for example, it's good to keep in mind that the round-trip latency best case, with no amplifiers in the path between, say, the east coast of the US and northwestern Europe is about 60 milliseconds. Okay, so for those of you that are interested in transactional systems, then that's an insurmountable barrier. And it raises the question then of, well, how do we do these large-scale cloud deployments where, in fact, the size of the world is a significant issue, and it has a big effect on where it is I actually put data, and if I need reliability, if I need something like synchronous replication. All of a sudden, I have this really interesting challenge, right? On the one hand, cloud is supposed to liberate me as a user from the location of the systems that are actually managing the data. On the other hand, that doesn't actually work because the speed of light's not enough. So anyway, Oracle has this idea that, in fact, our customers are going to look for a number of solutions to the problem of complexity. So the one that we've focused on for the last few years is taking away the problem of assembling and testing and supporting large-scale mission-critical systems. Right? Getting a very high-performance storage infrastructure is not impossible. A room full of clever people with some open-source software and some cheap hardware can, given enough time and enough motivation, develop a very large-scale, very highly reliable, high-performance storage system. The trick is that it's very difficult to support, And it's very difficult to hand that technology off to any other team. To do that, you need to productize, and you need to wrap this thing in standards for testing and the training material, and you need to create the ability to not only deploy that software and hardware, but you need to actually integrate it into the organizations that are going to be consuming and depending on it. And our feeling is that many companies probably don't want to do that anymore, and that they're a lot better off if Oracle takes on some of that heavy lifting, because those kinds of processes, that kind of work, that's what we do, that's what we exist for. So we've been focusing on integrated systems, engineered systems, Exadata as a product some of you might have heard about. That's probably the flagship storage system for Oracle Database. Best in the world, built with Oracle Database. In fact, it's tightly coupled with the Oracle Database architecture. So it's a great example of how Oracle is able to do really, really hard engineering, but to do it in a way that makes it available to companies with relatively low cost and with very consistent results. Now, cloud comes along, and now we have customers saying, well, Oracle's taken on a bunch of the hard work of putting the pieces together to give me very high performance storage, but now I don't want to buy it and own it and operate it. Now I want to just rent it. I want someone else to house it and power it and clean it and cool it and tune it up and maintain it. I don't want to touch it. I just want my SQL to magically fly over the ether, and I'm going to get my results back. And we can do that too. But again, we're constrained by the speed of light, and we're constrained by some other things too, which are security and data sovereignty. And I'm distinguishing between those because data sovereignty is often thought of as being a byproduct of security concerns, and it may or may not be. Right? So you have to think of it as a different thing. But the bottom line is that for many enterprises where there is any kind of a legal obligation between the users of the data and the people that are managing it, the state has a role in deciding where that data can be. So we have data sovereignty as one issue, and then we have security as another. And there are many organizations that ultimately rely on, as the last bastion of security, security through obscurity. And so they won't even ask you whether or not you can comply with their standards, because disclosing their standards represents a security vulnerability. It's a vector of attack. So they say, no, for security reasons, I cannot let you touch my data. So we have these engineered systems. They're very useful. We have customers that want cloud. That's fantastic. We are now offering a middle path for our customers, which is the ability to have effectively, technically, an Oracle cloud, but deployed at a locale of their choosing. They consume it as if it was a cloud service, as a subscription, but they get around the data sovereignty and the speed of light problems by being able to put the machine, the data, the storage physically where they need it to be. And we're one of the few cloud providers that can do that. Microsoft Azure has done a good job of working with hardware vendors, for example, HP and Dell as examples there, to provide standardized hardware configurations for Azure so it can logically be deployed on premises. But in Oracle's case, it truly is 100% Oracle supported, developed, maintained infrastructure. So, and I guess aside from Microsoft, frankly, there really isn't anybody else. So if you aren't in the business of rolling your own, as they say, then we have a fairly unique offering. But I want to talk a little bit about data protection. Security is a big deal for us. And for anybody that's, anybody here have issues related to the, what's the encryption attack that happened yesterday? What's it called again? WannaCry? WannaCry, WannaCrypt? Anybody have any personal experience with that? Oh yeah, well, yeah. Oh, I don't have any XP running anymore, but yeah, so security is one of those things where major organizations have a challenge. They don't like to talk about their vulnerabilities, right? They don't like to ask you questions about what you've done, because asking you the question discloses that there's something that you may or may not have done and that they don't know about it. So people don't ask you about security, and they don't tell you after they've been breached, because nobody wants to disclose that they had poor security. But let me tell you this, if you're the person who made the decision to deploy a system that is not secure, after you've been compromised, you will be held in contempt for your failure. You're never going to get a warning that you need to do it. You're only going to get told that you should have and didn't. And so we're finding many of our customers are coming to us quietly and saying, I need your help. I need you to help me. This is a career-limiting problem for me. I need to do things that aren't going to increase cost, that are going to improve security, because I just saw the person next to me get demoted. And no one ever really explained why, but we all know why. So we're very concerned about baking security into our products, and in particular into the data protection lifecycle. So when we talk about these engineered systems, we don't just optimize the performance and scalability of the systems. One of the things that we spend a lot of time on is security. And think about this. In a cloud world where capital efficiency is only possible if you have a truly software-defined infrastructure, right? Where you can no longer rely on perimeter security to protect your data and your systems. The underpinning of all strong security is pervasive encryption, right? So you heard earlier today about the Spark chip and what we're doing with crypto acceleration. Well, to give you a commercial context, think about this, that broadly speaking, your vulnerable data is going to exist in 3 places. It's going to exist on some kind of a media, and you can encrypt it there, so that's awesome. It's going to exist in transit. It's going to be sitting somewhere on the network, and you can encrypt it there too. Fantastic. The data is going to be in memory somewhere. Well, that's been a bit of a problem because you can't encrypt it, at least not with any technology we're aware of. And that's why we've concentrated on things like silicon-secured memory in the processor, right? So that we can protect all of that data that's now sitting in memory in those systems. But let me start with crypto, or actually silicon-secured memory. So I think you had the briefing on this earlier today, so I'm not going to go into it in a lot of detail. Did everybody here catch that, by the way? The session earlier where silicon-secured memory was discussed? Yeah? It's really interesting technology. It's a long conversation, potentially. So I'm just going to assume that you all have a little bit of a background there. And now I'll jump to encryption. So again, if you take the viewpoint that we have today from an architectural perspective, for cloud to work, for us to get the capital efficiency that we need from large-scale deployments, we need to encrypt everything. And that's why we have added very, very powerful encryption coprocessors, acceleration, to our processors. The advantage for us is that it improves, or at least it doesn't affect application performance, but it dramatically increases security in a very, very fundamental way across the stack. And I'll give you an example of what I mean in a large-scale deployment, cloud deployment, for example. You know, historically, we have used perimeter security to isolate customer environments. So imagine that, and many of you know this pretty well, I think. Imagine that you've got 10 tenants sharing a data center. Well, you give them all cages, that's fine, right? So they've got servers, the servers are in cages, the cages have locks on the door, that's fantastic. All of those cages are piped directly back to your core network because they shouldn't touch each other, because that represents a security limitation. Now, if you want to deploy a cloud environment where you can flexibly allocate resources, how do you do that? Well, you have to integrate them all via some kind of a networking layer that allows you to dynamically create secure environments and control which resources are exposed to each environment. That's been very challenging to do prior to fully deployed SDN. And so many customers have this challenge where, in order to satisfy security requirements for their tenants, they're forced to arbitrarily assign very large amounts of storage and compute resources, and in a very inflexible way. They can't dynamically grab those resources and put them elsewhere, which means that their capital costs are significantly increased over what they ought to be. Now, let's take a VMware environment, for example. Let's suppose that I'm a tenant in your cloud and you're using VMware or some other comparable hypervisor, type 1 hypervisor technology. If I want to be able to service the environment and I want the ability to do things like live migrate virtual machines, the only way that I can do that in a secure way, since I'm not encrypting those virtual machines or encrypting that data as I move it, the only way to do it in a secure way is to rely on perimeter security. If I have an inflexible network layer, then I have this arbitrary boundary around this giant pool of resources, and a whole bunch of it goes underutilized. If you can do something like fully encrypt all of that data as you move those virtual machine images from host to host, then you have the opportunity to no longer be dependent on strong perimeter security implemented in the SDN layer in the infrastructure. Now you have strong security that is totally decoupled from your networking layer because you can encrypt and move virtual machines on the fly at wire speed. And that's one of the advantages that comes from Oracle developing its own processors. It effectively gives us an enormous architectural advantage in the design of our cloud infrastructure. This is something that also shows up, of course, in our engineered systems. Now, security, runtime, I would call runtime security, right? Things like encryption and memory protection is very important. For many of our customers, being secure isn't enough. They need to be compliant. And so another important thing that we're dealing with here is how do we automate compliance? First of all, how do we build systems that are guaranteed to be compliant? And then how do we automate the compliance? And there's quite a lot of work involved in doing that. And to be honest, one of the ways that we have addressed security and compliance is through limiting the scope of the effort. So for example, for applications that require very high levels of security, like ERP systems or core banking or systems used by the military defense department, for example, we create essentially data centers that are self-contained, where the application tier, the database tier, the networking, it's all inside the system. And then we design compliance tools, security tools that go with it. So we deliver not only the runtime security advantages like the silicon secured memory and the crypto acceleration, we also deliver systems that have been pre-tested to be compliant with all the relevant standards. And then we deliver automated security tools that will let customers create security environments without having to be security experts or know the implementation details of the systems. And then finally, we deliver automated compliance reporting. Now, we're in the process right now of trying to figure out how to scale this up, because to solve the security problem required that we get that we take a very controlled view of what it is we're trying to secure, right? We made the problem smaller in order to solve it. Okay, now we're trying to figure out how we can solve the same problem from the customer's perspective, but at cloud scale. Okay, this is one of the areas where Oracle is investing an enormous amount of money, and some of the most brilliant people I've ever worked with right now are working on this particular problem. But this is an example of a screenshot of something we call Security and Compliance Virtual Assistant. This is something that we're in the process of trying to scale up to our cloud right now. We can do this today with systems like the supercluster and this mini cluster system, which are small-scale integrated compute storage converged infrastructure systems. But this technology, as I said, is something that we're trying to bring to cloud scale. And essentially what you see here in this screenshot, I guess it's a bit far away for most of you back there, but if you could read it, what you would see is essentially a simple screen that presents the interface for the creation of VMs for a database or applications. And it provides a simple drop-down menu that offers PCI DSS compliance, CIS equivalent, or DISA-STIG, which is the Defense Information Systems Agency Secure Technical Implementation Guide scored standard, that's the most complete set of security standards that I'm aware of, is the DISA-STIG. And that means that a DBA or a developer that doesn't really know anything about the infrastructure can simply choose the right option and hit go and create an environment that's fully secure. They can see the score for the DISA-STIG. If you know something about DISA-STIG, it actually has a scoring mechanism built into it. And then in addition to creating the secure environment, we have the audit policies, things like key management and scheduling automated compliance reports, and this is an example of doing that here. So the goal is, again, to take away that not only the security complexity, but the compliance complexity as well, and generating automatic reports. So now very quickly, I'm going to talk about performance. Again, I'm glad you've seen a lot of this material already, so I don't have to talk too much about the chip. But the acceleration that we have built into the processor, that we've engineered into both Oracle Database, frankly, and this Spark processor, is quite dramatic for in-memory database. And not just Oracle Database. In fact, that technology is suitable for other workloads too, and I think you'll be hearing some third parties talking about that very soon. Apache Spark, for example, or Quartet file system and other technologies, Java Streams optimization. An Oracle database 12.2, of course, has some new features. There's a hand-in-hand code development of the processor and the database, so it's very iterative. They both continue to work together to get better from generation to generation. And we're doing the same thing for Java. So filling a data center with hardware is very expensive, very expensive. And here's the thing is, if we think about the kinds of workloads and the kinds of customer use cases that we're dealing with today, right? It's the tip of the iceberg. So I remember a time when only about 10% of the population had access to the internet, and that was dial-up. They were only on it when they were explicitly on it. They had to do it. It was a thing you did. I'm going to go home in AOL. Now, 20 years later, connectivity is pervasive. We went from having a single device that could access the internet, that could access any kind of a data service, and now most of us walk around with 3. Typically a watch and a phone and a laptop or something in your bag, and you've got one in your car, and you've got a tablet, and this is just the very, very beginning. So we're in the process now of trying to figure out how we can accommodate the kind of scale that is already commonplace today. But the truth is that this technology is going to drive us to a whole new place. The scale of the systems that we're going to be deploying in 10 years is going to be 2 orders of magnitude greater than what we're trying to deal with today. So we're very concerned with things like power consumption, square footage, which is why we continue to design our own processors, because when you're deploying 2 or 3 million cores, you need to do everything you can to optimize your use of space and power and so forth. So we're very concerned about performance, and in particular for in-memory workloads. So again, securing the data, making sure that the data can be secure no matter how it's deployed, whether it's in our cloud or on the customer's premises or wherever. Making sure that we are optimizing in-memory query processing so that we can have real-time performance from applications for doing things like sentiment analysis or fraud detection or user interaction for services that may be, for example, monitoring social media feeds, looking for information about what a particular user is doing or thinking at a particular moment, which would create potentially a commercial opportunity or which would give us an opportunity to do something to help them, right? These are all new challenges, so it's this combination of the performance, the scale, the security. And from Oracle's perspective, engineering processors is a small price to pay to obtain a very significant competitive advantage. It's one of the reasons we're not the only major cloud provider that's doing this, by the way. And then, of course, in the current generation of the Oracle Cloud, we are in the process of rolling out an end-to-end software-defined network architecture, something we call bare metal, and that's, if you're interested in reading about that, there's a lot of material online. And bare metal is really all about having a massive scale flat network topology that allows us to dynamically carve paths from any network-connected endpoint in that cloud to any other network-connected endpoint that is secure, and set those up in a matter of seconds and tear them down in a matter of seconds. This is an important part of getting capital efficiency and preserving application performance, and also ultimately the performance of the large-scale shared storage that is the underpinning of the Oracle Cloud. Now that was a bit of a kind of wander through a whole bunch of sort of related topics. These are all things that I find just really fascinating. But anyway, locality for me is a pattern that is super important for us today, and it's going to get more and more important in the future. And then the other thing that I really enjoy is just thinking about how the speed of light's not really that fast. That was really an eye-opener for me, frankly, thinking about how do you do large-scale distributed systems, and how do you get around the constraints of the speed of light through silicon. So anyway, thank you very much. And if there's anything that I might have talked about today that's interesting enough to warrant a follow-up, please talk to this guy right here. Thanks. Oh yeah, any questions? building storage, is that your primary interest, by the way? How many of you are really concerned with the challenges of building storage systems? Hands? Yeah? And how many of you would be willing to step away from that complexity if a vendor could just kind of do it for you? Yeah? See, but not everybody put their hand up. It's all different communities. I think that's very fascinating, by the way, because I like building stuff too, right? It was a great hobby, but it's really interesting to see how many folks just enjoy it. Do you enjoy it? Is it you do it because you just like the problems? It's like playing a game. You know, you're looking for a technical challenge and you're going to try and find a solution, and it feels good because you can measure the result, right? You can test it. You can test yourself. You can actually give yourself a score. How long did it take me and how elegant is my code, right? I like that too. And I got to say, I'm trying to sell many people, I'm trying to sell them an Oracle solution because it makes business sense. But the reality is a lot of us just aren't, it's not why we do these things, right? And I'm cool with that, by the way. So enjoy your technology, right? I wouldn't be here if I didn't love it. Thanks.
show it in Slideshow? Like, it's not on there? I'm so confused.
Got it? Okay. Okay, great. Test. Okay. Test. 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 Okay, let's start in about a minute or so. Okay. Could we do the, turn the hanging mic on, please? Support, thanks a lot, man. Appreciate it. Test, test, test. Okay, there it is. All right, so we've got the final session. We're going to finish the session on, basically, Michael started it off. The title, we forgot to mention the title of the session is kind of comparing SQL and NoSQL type environment, so trying to drive workloads related to processing data. So historically at this conference, processing data has been primarily kind of raw HPC types of data or HPC structured data. So this session we're talking a little bit, we're focusing a bit on business type databases, but also just very large scale systems to manage small files and how to analyze the data. So this is the first time I've presented these particular slides. I'm working in cloud infrastructure. These slides are from PM, so I stole them from the folks mentioned there. There's a couple of, I'll just throw in whatever, so Oracle, we do cloud. It's a bunch of great things about it. We have a big cloud and lots of data centers, lots of people are using it. It's growing fast. Okay. All right, so let's get to technology. So the technology is, that I'm going to talk about in this session is, in my talk is Exadata. Somewhere somebody cloud washed the Exadata, so all the discussion of Exadata here will say cloud, but it's actually correct because Oracle's database in the cloud is essentially driven by Exadata. So Exadata is basically a database appliance. So it runs the exact same database software that you can run on IBM, HP, or whatever generic hardware you've always been able to run Oracle on. So what does it look like? Well, it's very interesting. It's one of the coolest things, technologies that I've seen at Oracle, and there's a lot of good ones, as you've heard already, and that's really why I'm at Oracle, because there's a lot of great technologies that help solve real problems. So I wonder if does this have a pointer? Does that pointer work? A little bit, okay. So basically it's sort of a two-tier architecture. You've got a tier of servers that run the actual Oracle database. Those others are database servers. Each server can have multiple instances. The latest release of Oracle is multi-tenant. So one can have a single sort of basic, sort of database infrastructure and then have multiple Oracle databases live within that single infrastructure. So you get essentially a virtualized database sort of infrastructure. You can run those virtualized databases as a pool across all these database servers. There's something called ASM. ASM is essentially the storage management layer. So it's kind of like a combined volume manager file system, except it doesn't really work that way. It thinks more at kind of the database level and the database block level. But what it does is it sort of virtualizes from the database server perspective what's going on down here at this bottom tier. So the bottom tier are a bunch of components called storage cells. So, and that's exactly what they are. They hold all the actual storage where the database itself resides. But they're more than that. They actually have, Oracle implemented something called function shipping. So if you were back in the day in the 90s, late 80s, early through the 90s, there was a big discussion in databases about how do you make databases scale? Do you do shared nothing? Do you do shared everything? Oracle's approach is more of shared everything, but tiered like this. And one of the ways to make things really scale well is to move the workload of doing queries and scans and joins and all that other sorts of stuff directly into the storage server. So what do you think the advantages of doing that are? So if I have a database request up here at the database server layer, what if I package it and send it down to the storage cell layer? Why is that helpful? Can you think of any reasons?
You don't have to pull all data back across the net.
Exactly. So I can basically do that database processing directly in the storage cell, and then I don't have to push it across this network. That's exactly right. So in addition to that, it turns out we use InfiniBand and we use RDMA pretty much at every point that you can possibly use RDMA. And there's a couple of protocols. I'm still learning Exadata, to be honest. I've learned it to a certain level of technical detail. But bottom line is we run our own protocols right directly across the InfiniBand. So they're low latency, very high bandwidth, lots of other cool features you can. And then as you'd expect with this kind of systems, you can scale out, more or less you can scale up the server tier layer as you wish, and storage cell layer as well. So up until recently, they were sort of fixed configurations, but if you have a heavier compute load, you can go with more database servers, fewer storage, and then vice versa, more storage. You can add, if your workload is more storage or query intensive, you can add more storage cells. Okay, so that's the basic architecture. Any questions about that? Is that helpful? Makes sense? Okay. All right, so this database cloud platform, you really want something, so let's talk about databases in the cloud. So really that's where scale is happening these days. Most places, There are a few customers that have very, very large-scale Exadata systems. One is Customs and Border Protection. It turns out whenever you enter the U.S. or leave, be you a U.S. citizen or not, it's tracked by the Customs and Border Protection. If you're shipping something in and you have to pay duty, all this is tracked in a giant system of something like 60 of these, of the largest. So go back to the previous slide, the largest system you could have, which is a full rack, and then there's 60 racks, some enormous numbers of racks. And then there's apparently another government agency that has an even larger system. Most banks have this that use Exadata. It's how they run most banks, really large companies. So it's kind of it's something you probably haven't heard of, but but it's pretty much running the enterprise. What's kind of cool is stuff we've talked about in this conference for years. It's this community, large-scale parallelism, et cetera. I'm telling you, it's used every single day by the biggest companies with technology. Not just this, but there's others, but this is one that it is. So people are now going to the cloud to get even more scale. They want to get the same or better performance. They want extreme availability. They want to maintain the quality of service for all their tenants, and they want it to be fully secure. So how do we do that? I think it's another marketing slide. So this is the usual Oracle. So one of the cool things about Oracle is, Larry Ellison runs a company, and he just loves to bash competitors. So we get to actually bash competitors. It's a lot of fun. But I'm serious. He actually, if you read, I read a history of Larry. He he talks about picking a fight with Microsoft over the network computer. And, the network computer was kind of like you remember that back in the late 90s? So it created all this press. He could care less about the network computer and even said so. What he wanted was, to get in a fight with Microsoft because he knew they were going to start building databases and they were going to start building all sorts of stuff to compete with Oracle. So anyway, we have to beat up the other guys. So what our viewpoint is the new cloud databases are quite primitive. They're really 30 years behind the state of the art in terms of SQL, full support for SQL, transactions, analytics, all this other stuff. Now, there's some mature databases that are deployed in the cloud you're seeing from companies like IBM, et cetera. But again, they're really not fully caught up with where we're at. So we think we're pretty awesome, So where does all this awesomeness come from? So let's go into the technical bits. So if we're going to run database workloads in these hardware-oriented systems, I'll say cloud, but it's really Exadata. There's sort of two kinds of workloads you typically have here. One is online transactional processing workloads. That's lots of small random IOs, low latency, predictable response times. That's what you're looking for. Data warehouse, a little bit different. This is lots of data to load and process at once. And you ultimately want succinct results in a reasonable amount of time, but you don't necessarily have to have the absolute lowest latency. And then test dev workloads, you want to quickly provision stuff. You want it to be simple to manage them. And then similar performance characteristics as production. So again, OLTPs, lots of users, lots of messages between these servers, lots of small updates and deletes. Consistent response times are very critical. These are typically driving a business. If you're Customs and Border Protection, if you can't do a check if this person's on a terrorist watch list very, very quickly, they're going to sit there. And then they're going to back up all the other people behind them. If you're a bank, you want to, typical things. So constant uptime is very important. So to make that happen, with traditional systems, like the ones I used to build GFS on and what you see a lot of cluster file systems built on, they're using traditional components. They've got a server layer, classic SAN, storage area network, maybe some kind of faster Ethernet, storage controllers with their RAID controllers, all that sort of stuff, and then within that sort of proprietary protocols is SCSI. So the IO sort of path has always had many, many layers of translation virtualization. It's sort of been fun, it makes our life interesting, but it also means that the software stack is pretty onerous. You've got everything, you start at the database, you go to the OS and the network stack, device drivers, the HBA, switch fabric, storage controller software, and then whatever's happening down on the drive. Drive has its own set of things. So it's a lot of stuff, and what that means is if you're trying to drive things low latency fast, bad things start to happen. For one thing, if you're building out one of these database clusters, the database to day server communication happens on slow 10 gigabit per second Ethernet. So Ethernet is hugely popular, we all love it, but it has high latency and low throughput compared to other networking technologies like InfiniBand, which is a 40 gig per second network. It's coming, and 100 gigs per second is coming. It's got lower latency, you can do zero copy, RDMA through it, higher throughput. So traditionally, things like RAC, this database to storage communication, so this part of the path is traditionally done over fiber channel. I love fiber channel, it's always been a pretty cool technology, but It's shared storage, so it's unable to take care of this higher bandwidth and lower latency types of networks. The number of HBs on the database server limits performance. And then compared to InfiniBand, which enables a lot lower latency and then higher IOPS for OLTP. So InfiniBand's critical to really driving this. So if you kind of build a big picture here, this traditional networking stacks delay the ability to communicate across multiple servers doing the, running the database protocols. And then this really makes it difficult when you're doing OLTP. The messages are small, they're relatively simple. They don't really require a lot of time to go through the network and execute on a destination. So really, what really drives most of the latency there is going right through that stack, going through the CPU and OS, and then traversing that big layer. So the network stack's pretty significant there. If you go with a InfiniBand kind of network, a bunch of good things happen. You can enable low latency, higher bandwidth. You can basically use a specific protocol that we do to basically drive things, and it's custom designed for critical OLTP workloads and specifically bypasses this OS and networking stack. Also, the InfiniBand hardware primitives are called directly from the Oracle software, and so ultimately what you end up with is just huge amounts of that networking stack or overhead are taken out. And then you can start layering this and start doing even more interesting things. And an important thing with online transaction processing is you love Flash because you get the performance, but we hate Flash because every once in a while it decides to do garbage collection or it has some kind of error correction it has to do. So it has these spikes in response time, which are bad. Again, we're trying to serve very low latency very consistently. So we want to use Flash, but we want to hide that. So flash arrays try to hide it with a DRAM cache with a UPS backup. But these tend to fail when you've got a big surge in I/O load. Tends to be an issue. So even with the DRAM cache, the workload it doesn't fit in that cache, and you're still exposed to some of these outlier response times from the flash. And it's particular in databases, you typically keep the thing consistent by writing through a log. The log contains all the changes to the database. That can be a lot of stuff, especially if you're logging data as well as metadata. So log writes can really be a key bottleneck. So what happens is a small change in this log response time based on Flash, doing garbage collection or something like that can lead to large slowdowns in the commit latency and then OLTP throughput. So you see that here, these spikes that occasionally happen. So what you can do, though, is very simple process. Go ahead and write to 2 log devices in parallel. And so as soon as the first one completes, then you can respond that you're done with the process. So if one of the flash devices starts to go into one of these modes that increases response time, you can use the other one, and the result is the spikes go away and the overall latency drops by about 1/3, 3 times. Okay. All right, there's some more examples here, but I don't have enough time. Here's another challenge. So again, the theme here, I'm covering a lot of room and ground in a short period of time. We want to integrate the hardware and software very tightly. We want the database software, the OS, to understand the hardware very deeply. And then we want to take the benefits of that convergence and feed it back to the workloads. So big problem in databases is, well, everybody loves, going back to their data and running big queries on it and trying to analyze what the heck's going on. Traditionally, you'd have to take your existing kind of online OLTP database and you'd create sort of a cube and something you would put into a separate data warehouse and start analyzing it there. Well, what if you could do the same? What if you could basically run data warehouse queries on your data live? So you're still serving out OLTP, this transactional stuff to keep your production workload going, but you could be analyzing the data in real time. The problem there is this mixing of workloads degrades response time. So typically, if you just run OLTP, you're fine. You've got the whole machine to yourself, and you're getting mostly these small lookups and updates, et cetera. But when you do all this classic workload, you've got to maybe consolidate databases. Well, it's not just the data warehousing, it's just the usual work. You've got to back up the database, you've got to do reporting, real-time analytics. So all those workloads come in and they start to affect the response time. So within the context of this cloud Exadata platform, What we do is basically the database tags messages that require low latency, log writes, cache fusion messages, locks, etc. And then these particular messages bypass all the other messages, stuff like reporting backup that can finish later, it's no big deal. The key thing is you have to accelerate these low latency messages in all the layers. If you just do it, I mean, you've got to do it in the database, and the network cards, the switches, and the storage. Otherwise, the bottleneck just moves. If you fix in the database but not the other layers, and the things get clogged up at the lower layers. So with that approach, life is good. You can mix both workloads. I'm going to skip this because I want to. Okay, this is one I want to. Okay. So the last piece of kind of infrastructure-y stuff, a big issue with this, so this architecture works pretty well. We can converge everything, so from the database down to the storage, there's sort of a holistic view of what's happening, but things change. We've gone from, the system was built primarily with disk storage, although flash was available even in the early systems 7 or 8 years ago. Whereas a lot of times we're pretty much using flash 100%. So a lot of these systems just ship with all flash. If you think about it, the issue with flash is it's so fast that this model of shared storage starts to break. So shared storage, we love it because it helps us efficiently share capacity. It's one of the reasons Fibre Channel took off and is still used. It lets you efficiently share capacity, but it doesn't share performance very easily. And in the meantime, look at Fibre Channel cards. Latest PCIe flash is around 5.5 to 6 gigabytes per second. The speed of one flash card is now similar to the fastest SAN link. So a few flash cards deliver more throughput than a storage array can output. A SAN array, a SAN or LAN can transfer, a server can input. So bottom line is you got this problem is the storage is now too fast. So what this really shows is you can now leverage that advantage I talked to you about with storage servers. You can basically move the request from the database server right down to the storage server. It's processed there. It happens within the storage server side. And what would otherwise have been a huge amount of data that would have to be pumped back to the database server gets processed there. You can also start to do all the cool stuff that Michael mentioned and Stephen around decryption, decompression, compression, et cetera. All right, and with that, I think let's see what time is it. I want to wrap up because bottom line is I could just sort of kind of keep going through examples of how this is pretty cool. But the net of it is what you can do is, again, once you kind of have that vertically integrated understanding of all the layers, you can just start optimizing performance. You can handle failures better. And I could continue to bore you with another 5 or 6 examples of that. But we're going to get to our next speaker. Any questions for me before we go to our next speaker? Boy, it's getting to be the end of the day, but go ahead, yeah. You can either shout it or you can go to the, your choice.
So my question is simple. In all flash systems, so bottleneck is the communication networks. That's true?
I'm sorry, could you repeat that?
In all flash system, the bottleneck is just network, communication network?
Yeah, so exactly. We can basically add many more storage servers, and generally for really large queries, like typical of say a huge scan if you're doing some kind of warehouse or analytics workload. So what we do is we essentially do it on the storage server that has the flash cards. It sort of it does the fast transfers, but on its own internal buses, and then once you've kind of got that final result, more compressed result, that gets sent back across the network.
In that case, if we have some mechanisms, for example, in the flash, the device has an in-device computation, like the compression, the response packet or something else. In the case, we can get some advantage in there.
Yeah, but you can, but it sort of happens at typically a lower layer, like at a block layer or a file, kind of a file level. So we're talking like way up we're doing it really at the database level. So at the very highest, sort of literally like the application layer.
Thank you.
Okay, cool. All right, any other questions? Okay, great. Let's see here. I'm trying to get your, are you PowerPoint or did you do PDF? Okay, that's right. Yeah, that's fine, but 20 minutes is fine. Can you, I'm trying to find the, where do we put that?
Should be somewhere in.
Because we already opened it, right?
I don't think so, or I didn't see anyone open it. Might just be in Finder somewhere.
Is it this one? Can't thread or GA?
Nope. We still have the little USB drive that it was transferred to. I don't remember transferring it onto here.
Oh.
Maybe she did, maybe she didn't.
Okay, do you have it? Oh, I thought we did transfer it already. Okay. Okay, so, I thought we already had this on. So we're gonna have to take a minute and just transfer. We already did. Is that the right one?
I think so. Looks like it.
It should come up though. Sorry?
I can just bring up, I can just copy it again.
Yeah, why don't we do that?
Okay.
Okay, so you'll copy it again?
Yeah.
Why don't,
Is it ready to pull? There it
Oh,
goes.
okay. It's easiest to like switch over USB because these things are just.
Oh, yeah, totally. Storage.
Yeah, it doesn't. Okay, great.
No worries.
All right, so our next speaker is Aaron Cordova. Do you want to pass this?
Sure.
Okay, great. Just have to click that. So our next speaker is Aaron Cordova of Covers, and he is going to be talking about Accumulo, which is a NoSQL architecture that is used for very large-scale storage and analysis. And so over to you, Aaron.
Cool. All right, can everyone hear me okay? I'm trying not to cough too much. So has anybody heard of Accumulo before just now? A couple people. Well, that's great. So I'm going to move over here. So I'm going to talk about what we were thinking when we designed Accumulo and why it is the way it is. And it's great that we just heard all about Exadata, and actually we've heard a lot of interesting design thinking around how people are building these storage systems and integrating them and why. And so I think this will offer us just another view into that space, but hopefully a slightly different perspective. So when I am talking about design, I'm talking about it in the Steve Jobs sense, which is, why is it the way it is? Another good quote that'll help us out during this talk is that there's no such thing as a free lunch. So there's lots of trade-offs that you have to make. And really, when somebody talks to me about a system, what I want to know is just what are the trade-offs you made and why? Because there's, you know, sometimes either side of a choice is equally good. It just depends on what you care about. So what I really wanted to understand, you know, about like Exadata or any other system that I'm learning about is what do the people who designed it care about, and do I care about those same things? So I'll tell you what the people who designed Accumulo cared about, and then of course it's up to all of us to just figure out where that might fit in our own worlds. So in 2003, at Google, they published a paper about their search architecture. And I don't know, does anyone remember reading this? This is like, and they described the system, and it was like incredibly parallelized. It was distributed, and I believe it was also almost entirely in memory. Does that sound right? Maybe. And what they said was that the thing that they cared about was efficiency, energy efficiency, and price, the price performance ratio. So how much compute do you get for your dollar? There's a lot of things you could care about, I guess, but what Google really cared about was performance per dollar. And that's interesting because right now they're one of the companies that has like gobs of money. And it's interesting for a company like that to care so much about what they spend. But then on the other hand, maybe the reason they have so much money is because they do care about this stuff. So they said that the choice to focus on performance for price pushed them into this space where they decided to use the cheapest hardware they could find and then just make the software deal with it. And this may be like totally old hat to a bunch of you, but I just want to make sure that we're coming at it and we keep this in mind because it's going to drive all the decisions that we make later on. And so they said, this is what the system looks like, and by the way, this is not like a NoSQL database or anything. This is just their indexing system. Different queries go to different machines. The whole index is partitioned. Even a single query can use multiple processors. And it's in the tens of thousands. And the fault tolerance is built into the software. The hardware is pretty bad. It fails all the time. But performance is good because the software can handle it. So they achieved their goal of getting good performance for not a lot of money. Then in 2005, one of the Google engineers, Jeffrey Dean, gave a talk at University of Washington. And this was before they published a paper on a system called Bigtable. So he introduced this thing they called Bigtable. Who's heard of Bigtable? Everybody's heard of Bigtable, cool. So very briefly, it's interesting. It's always interesting for me to go back and see what the world looked like kind of before we knew about all these things. So at that time, not only did they have this success in building out their search engine, but they had a lot of semi-structured data. They had lots of versions of data. They were crawling the web every day or every so often. They had lots of information about their users that they needed to update. And then they had all this kind of weird data they were getting from satellites and geographical data that was a little different than what they had been dealing with before. And then, of course, they had tons of people using the applications that they built all day, every day, hundreds of millions of users. And this is what they said at the time. There's no way we can use a commercial database for this. But they said, scale is too much for most commercial databases. And the second thing they said was, even if that's not a problem, even if we admit that there's some databases at scale, the cost would be very high. Now, cost can be measured either in like upfront costs, but there's also a cost of building and owning your own infrastructure. Google chose to build their own infrastructure in the same way they built the web index, right? So they said, we're already invested in this commodity class, cheap hardware. We don't want to have to buy really high-end hardware and have kind of two types of hardware in our infrastructure. And they're focused on what a lot of us have been talking about today, which is there's all these advantages to integrating vertically. They already had a file system called GFS. They had a couple other components that they controlled, and they said, it's okay if we build a new layer on top of these for handling structured data and handling kind of incremental updates and very fast, low latency lookups, because we have these other components that we control. And if we need to make changes to those, we can. And they said, it'd be very difficult, it's easy for us to optimize. It'd be very difficult, though, to have some other system that we don't control sitting underneath a bunch of applications that we're designing, which, by the way, we don't know if they're going to work, because nobody's, built them. At that time, nobody had built the kind of apps Google was wanting to build at the scale they wanted to go to. So they didn't even know what design challenges they were going to have. They just knew if we had a certain level of control over the stack, we're going to be much better off. And also, to Michael's point earlier, they wanted to do it. But then even as late as 2010, another paper came out where they described a system called Percolator, which is, has anyone heard of Percolator? It's much less common. So it's a system for doing multi-row transactions on top of Bigtable and incremental updates. They built that because at that time they were actually moving Google's primary web search on top of Bigtable. And it was served out of it, at least for a while. I don't know if it still is or not. But that time they said the same thing. They're like, well, we could do this in a database, right? We could try this. But they said, we just don't know how it's going to scale. There's tens of petabytes and thousands of machines. So that was the motivation. That was their motivation. And then when it came to what is this system going to look like, they said, well, we're imagining there's going to be all these processes that are going to be serving user requests, and they're going to need to update just their portion of the world. So for example, I go and I update my user preferences in Google. All it needs to do is just change my settings. It doesn't need to change anything else. They wanted access to the most current data. They need, of course, high read-write rates. They wanted efficient scans, which not all NoSQL databases emphasize. By efficient scans, they mean sometimes I want to just look up one thing, but sometimes I want to look up like 10 or 100 things all at once. And that needs to be fast. And then they wanted to be able to scan over subsets of the data. And this one's interesting. They said efficient joins of large one-to-one and one-to-many data sets. And what they're talking about is not doing joins on the fly. They're talking about pre-joining a bunch of data into a big table. And if there's a common key, they're just going to store it all together. And then there's also things that they want to look at over time. So that's how they knew they had built the right thing if it delivered those objectives. So that forced them to make the following decisions. It was a highly consistent. They wanted to use consistency. They wanted high consistency over eventual consistency. So how many folks have heard eventual consistency, where it's like, oh, don't use NoSQL because it's eventually consistent? Well, and it's like, well, is eventual consistency even a bad thing, or is it a good thing? But what we've learned, I think, over the years is that eventual consistency is the best you can say about it is it's very difficult to develop applications on systems that are eventually consistent. So if your database is consistent, that makes your life a lot easier. Also, it wasn't designed to span multiple data centers. Now, they've since come out with other things that do that, but Bigtable is not one of them. The keys are sorted rather than hashed. So you could build a distributed database by hashing a set of key value pairs, and then that's how you decide what server they live on. Bigtable doesn't do that. It sorts the key space and then it assigns ranges to servers, which is a lot harder. Also, the servers serving a particular key space, they don't necessarily store the data that they're in charge of. And there's only support for single row transactions. So like I said, later they went on and built something like Percolator for the folks that said they needed multi-row transactions, but those are their designs. Those are their decisions. So that means they decided to build it basically as a big map. So it's key value pairs, but the keys are going to be a little more interesting than just a single value. And we'll get into that. It needs to be fault tolerant, persistent. It's got to scale. And this is what they said back then. It's funny because I think Exadata came out in 2008. And I think at that time, you could correct me if I'm wrong, a single rack could scale to a petabyte. Pretty big, okay. But anyway, it's in the same range. So yeah, and like they said, they were looking at all the commercial database and they're saying, well, we don't, most of them don't scale to this. But this was their target, and then since then they've of course gone beyond it. And then perhaps most important, the system had to be self-managing. Because remember, they're building on this super unreliable hardware. It's going to be falling over all the time. And you can't have people running around with their hair on fire in the data center trying to keep stuff running. It's got to be able to handle a huge amount of failure and just keep running with not a lot of humans in the mix. And that's another big difference between Bigtable and some other NoSQL databases. Some NoSQL databases make you go find the server that failed, tell its buddies that, hey, this guy's down, because they're still trying to talk to him, and then put another server right back in his place, and even then, they don't quite get it right. So Bigtable had to be smarter than that. So I'm going to quickly go through the key value, or through the data model. It starts as a basic key value pair. The keys are sorted, the values are not. The values can be anything, by the way, so you can store like a chunk of a satellite picture in there, or whatever. The key is actually broken up, though, into multiple components. So there's a row ID, a column, and a timestamp. And so you can think of it as like a table, but it's also got this like time dimension. So you can have versions of things over time, which makes sense because they're doing things like crawling the internet every so often. Also notice there's like missing values. So sparse data is not a problem. And the columns can be created dynamically. So if this is a record of the things people have bought, and no one yet has purchased, some sunglasses, then that's okay. The next time you do an insert, a new column would show up called glasses, and it would have the price of whatever that person paid. So it's extremely dynamic. This is what it looks like if you just list the key value pairs. So you got the row ID, the column, the timestamp, and the value. So you can see how you don't pay a penalty for having really sparse or dynamic data. You can just start inserting a whole bunch of stuff, and it's going to store it, and it's going to sort it, and it's going to let you scan over it, and you don't have to supervise it very much. Now, there's a cost to pay for that, which means that your applications have to be able to handle whatever columns come back if you're scanning everything in a row. But Bigtable lets you scan just specific rows or specific columns across rows, specific columns within a row. So you won't come across something you're not expecting. But on the other hand, it can be incredibly powerful to be able to scan a row and just say, what do we know? What do we know about this customer? We may know a lot more about Bill than we know about George, but just tell me everything. So that's kind of interesting. The other thing that's interesting about this model is the way you read that table is designed to minimize disk seeks. And again, this was back before kind of Flash came along, where Flash is super good at disk seeks. Spinning disk is, the seek performance of spinning disk was just not improving the way throughput was. So this system, just like GFS underneath it and MapReduce, was designed to take advantage of all the improvements in disk that relate to throughput and avoid seeks at all costs. So at worst, you're going to do a lookup to find the key you want, the first key you want, and you're going to have to do a disk seek to grab a block of those key value pairs off a disk, and then you can bring back just one of those, or you can bring back like 100 of them, or whatever. But most user requests in your application are encouraged to be of that design. So try to make it so your table's already organized. The data you need for your user requests can be answered with a single search. What's cool about that is that you get sub-second query latency, no matter how much data you have, without putting all the data in memory. That's still when the data is just sitting on disk, super cold, right? So that's really cool. And that works when you have trillions of key value pairs in a single table. Now, of course, it will also do the typical types of caching. So when you read a block of key value pairs off a disk, you don't just read one, you read like a block of them. And then recently read things can just stay in memory. So if you have temporal or spatial locality hotspots, you can serve that stuff out of memory. So one other thing, the columns actually in Bigtable is split into two components. There's a family and a qualifier. The families you have to declare up front, but the qualifiers can be dynamic. It's just whatever you insert into the table. And then you can mark, and the thing about families is you can group them together in locality groups and they're stored together on disk, which means if all you're doing is scanning some of the columns and not all the columns, the database can avoid reading all the columns off a disk across multiple rows. So it can behave like a columnar database if you want it to. Now, if you don't do that, it's going to order things on disk in row order. So it has these properties where it can kind of switch back and forth between a row-oriented versus column-oriented database. And you can mark certain locality groups to be served from memory lazily. The rows can be really, really large. So you could have a single row with 1 million columns or more, which is weird, but it actually comes in handy later. And then, like I said, tables, the rows within a table don't need to have the same set of columns. You pay no penalty for sparseness. And then, so Google had all these components. This is how it worked. Bigtable was built on top of GFS, which is a file system, and then a lock service called Chubby. They made it so you could run MapReduce jobs over it, and you could build applications directly on their API. A couple things about how the system actually works. So there's a single master and a bunch of tablet servers. Tables are broken up, partitioned. Well, first, think of a table as a big set of sorted key value pairs. That's partitioned and then assigned. Each partition or tablet is assigned to exactly one tablet server. And that's where you get the consistency. So when you split, though, you always do it on a row boundary. And if you keep inserting data into a tablet, it's going to get big, and at some point, the tablet server is going to split it. It's going to find a good split point, split it, and then the master is going to migrate it. There's an interesting way that Bigtable keeps track of all of its tablets and which tablet servers are currently serving them. It uses a hierarchical metadata table to do that. And then when clients need to do a read, they go to, well, here it says Zookeeper, and I've switched the word Bigtable for Accumulo, but punchline is Accumulo is based on Bigtable. So a client goes to Zookeeper, which is like the lock service, finds the root tablet, reads the metadata table, and then is able to directly read from tablet servers the data it needs. So notice, no data ever goes through the master. And you only go to the Zookeeper if you don't know where any of the other tablet servers live. And clients aggressively cache the metadata table information. Failure, so tablet servers don't have to, so if these little squares that are vertically aligned, that's like a single physical server. Usually each server runs a tablet server process and a data node process, which is just a storage process like GFS or HDFS. Those are typically co-located, but they don't have to be. So notice here we have more tablet servers than we have data nodes. If you lose a physical machine, the data in HDFS or GFS underneath is replicated, so it's okay. The master of Bigtable master will automatically reassign the responsibility for the tablets that were on the machine that failed to remaining tablet servers. They read data from the remaining replicas and replay whatever recent mutations were written. And then the storage layer automatically re-replicates stuff underneath. So that's a tremendous advantage when it comes to doing system administration, because you don't have to move data to rebalance the responsibility for serving. Bigtable worked out great. Tons of people use it, hundreds of applications. It's still in heavy, heavy use today at Google. The trade-off is people don't really understand intuitively how to create tables necessarily. So it's like, how do I order my data? What do I put in the row ID? What do I put in the column? What do I store as the value? And people are used to general purpose transactions too. But they say the flexibility is worth it. We have a huge amount of control over our stack. Okay, fast forward to 2008, National Security Agency. I was going to ask if anybody here is from the National Security Agency. That'd be funny. So a team of computer science and scientists and mathematicians, myself included, we're looking at all these technologies. We're reading the Google papers. We're looking at Hadoop. By the way, Hadoop is the open source implementation of GFS and MapReduce. We're looking at HBase, which was an attempt to build Bigtable. It's an open source implementation of Bigtable. And we looked at all this stuff, and we were concerned about storing large amounts of data of different sensitivity levels all in the same place. We looked at all that stuff, and we said, well, we don't think HBase is going to be the right thing for us. We're going to have to build our own, which is a huge undertaking. So we built that, and we extended the design a little bit. We added something called column visibilities to the data model, and there's a back-end processing component called iterators. It was released as an open source project in 2011, and it's still around, it's still out there. The change we made was we added this component to the column called the column visibility, and that lets you control what clearances are required to access that key value pair. So it's extremely fine-grained. And so imagine like that Bill's phone number for some reason is private, but his age is public. You can do things like that. And you don't just have to use simple labels like private, public. You can use complex expressions. So this is what it looks like if you look at all the key value pairs. There's a couple other advantages. Column families don't have to be declared up front. They're also dynamic. So the whole system just ingests whatever you give it. And then there's something else called a batch scanner, which lets you scan in parallel, which is really nice for using secondary indexes to identify records you want and then fetching the records, just like a regular database. So, and this all enabled what we were really after, which I'm coining the archaeologist's approach to data. So imagine you're an archaeologist and you're uncovering bones in the dirt, and for a while you're not sure what's bone and what's dirt, right? And so you're very delicately brushing, but you don't want to like go in there with a chisel and say, well, I think it's a femur, so I'm going to chip off everything that doesn't look like a femur, right? That would be a mistake, because you don't know. You don't even know what kind of animal it is. Maybe it's not a femur. So you have to just take the data kind of as it is, which Cumulo can do. Avoid making assumptions, avoid cleaning it up. Just take it in, but make it useful. So what Cumulo does is it sorts it, makes it accessible. You can discover things, and you can run processes like MapReduce or Spark over it to do things like clean it up or summarize it or ask questions or do really advanced analytics. So all these components are now open source. Cumulo sits on top of HDFS and Zookeeper. You can build applications directly on it, and you run MapReduce and Spark jobs. Couple benchmarks, and I don't have a disclaimer for these benchmarks, but they're not my benchmarks. So maybe that's an out, maybe not. I'm pretty sure these are accurately reflecting what they're saying in the paper, though. Anyway, Cumulo can do things like run on 1,000 machines and ingest 100 million entries per second, and then store like all of it in like a 7.5 trillion entry table. Like that's one table. And the access time of querying that table, of doing simple scans on that table is still sub-second. That's what the ingest scale is like. So as you go from 0 to 1,000, you go from, as you go from 300 to 1,000, you go from about 30 million per second up to 100 million per second inserts. That's one benchmark on AWS. The average scan latency, and this is a little bit weird, they were scanning the data the entire time they were ingesting, and they just divided the number of scans they did by how long it took all the data to return. So an individual scan wasn't sub-millisecond, but overall they were able to answer a huge number of requests on average less than a millisecond. But if you go and just query in a Cumulo table, you'll get the answer back in like tens to hundreds of milliseconds usually. Now the administrative overhead, this is really important. while they were scaling from 300 to 1,000 machines, they experienced anywhere from 4 to 9 to 11 failures, right? Just in the short time they were doing these like benchmarks. But the amount of time they had to stop and restart the benchmark and change something, and an administrator had to get involved, was 0 all throughout that. And the way it works is you just run your system for a while, things are falling over left and right, and then about once a week or whatever, you go through, you find all the like dead hard drives and you just yank them out and you replace them. But the system's designed to just keep going, and it can even shrink to a significant, like, you could lose like 30% of your cluster, maybe not all at once, but gradually, and it's going to degrade very gracefully. Another proof point was a graph processing benchmark, 1,200 machines, 4 trillion vertices, 70 trillion edges in that graph. It's about a petabyte on disk. They were doing graph traversals, and they could process about 149 million edges per second. Another one, these guys used some really beefy machines, so they had, I want to say they had like 32 cores per machine, which I guess in my mind is beefy. So I had 216 of those, and they could do 115 million inserts per second on that system. But they were not using the write-ahead log when they did that. And they said, it's okay, because we're going to checkpoint the system after every insert, every batch of inserts or whatever. So Accumulo is so scalable that some Accumulo instances have to span multiple deployments of HDFS. So HDFS will become a bottleneck at some point, even though it's really scalable. And Accumulo has the ability to span multiple HDFS instances to get beyond that. Last few things to say, Accumulo in the enterprise. Okay. You know, that was all kind of coming out of the government, right? A lot of those benchmarks are run by folks in the Intel space. So besides the Intel space, everyone in highly regulated industries finds Accumulo interesting. Usually when people approach us about doing a project, they say, well, we read about Accumulo, we heard it had some really interesting security features. And I think that just means that a lot of people are finding that security is kind of holding them back, and if they could just kind of get that out of the way, then they could do a lot of really interesting stuff. Accumulo is also supported, speaking of that open source discussion that was happening earlier, we are very fortunate because, well, in some ways, because we insisted before we got started that, look, if we're going to build this, we're going to make it open source. And the reason why is we didn't want to put forth all that effort and then have it just die on the vine in a government agency and never see the light of day. And there were no guarantees that the funding or whatever to keep that going would continue, because it is tremendously costly to build software like that. So we said, we'll do it, but it's in our best interest and yours, Uncle Sam, to open source this. It helps with recruiting. It just builds goodwill. Like, people are like, wow, government builds stuff and just gives it to the world? That's awesome. But we were lucky in that the Hadoop vendors were waiting to just take it. So they hired a lot of the committers, and they could keep doing the development in a much broader group of people. So that was very fortunate. Enterprises have so much data that they kind of end up being like intelligence communities in a way, where they're coming across data in the wild, even in their own enterprise, and they don't know what it is. Or they don't know when it's going to change, because communication across a large enterprise is really difficult, right? So you might be ingesting a data source, all of a sudden there's 3 new fields. Typically that will break a typical ETL pipeline, but Accumulo, if you set it up and you have it just bringing all the data in as is, can be flexible enough to handle that. And what's interesting is people view Accumulo as a way to bring all the data together physically. And why would you want to do that? Because you might want to run a MapReduce job or join that data or summarize it and analyze it in some way. So you have to bring it together physically first, but then protect it logically. So, and Accumulo is such that if you don't have the access to see something, you won't even know it exists. And we're finding that people like having those guarantees. It makes them feel confident enough to contribute their data to a very large shared system. And of course, it has to scale. It's got to be flexible. And The fine-grained access control just makes it so you can choose how and when and to whom you're going to share your data. Now, this is not, Accumulo is not the only thing that has security, but because it had security built in from the beginning and it has such an emphasis, it really gives people that confidence. One other thing, so Accumulo has good support for secondary indexing, which of course all databases have, and you can run MapReduce on it directly, so you don't have to move the data. It's actually anathema in this architecture to move data around, and it's interesting to hear that there's such a wide spectrum of systems when it comes to that. The challenges, though, are it's still a challenge. Like, unlike Google, a lot of enterprises don't have experts in distributed file systems. So even though the distributed file system underneath Accumulo is open source, you have anybody that can go fix bugs in it. So that's a little bit of a challenge. That's where commercialization and vendors come in. And then making sure Accumulo is doing the right thing for your enterprise security-wise is a challenge. That's kind of where my company plays. We live right on top of Accumulo, and we provide a little bit of more tools that help people adopt and integrate Accumulo and these other components into their architecture and do something useful without doing a lot of engineering up front. There's a couple of resources for you to look up if you're interested in learning more about Accumulo. There's an O'Reilly book. Check out the website. And that is it. So thank you. Okay. Thanks a lot.
Yes, thank you.
All right, so we're going to just go right into our short talk session, and Donna, is it Shahan?
Yes.
Is that right? Yep.
Yeah.
Is going to be telling us about large archives. So, Donna?
All right, does
She's
this...
also, Donna Harlan is helping her, even though she's under the weather, so thanks for coming again. Donna's been participating and helping out here for years, so thank you.
All right, thanks everyone. So I'm Donna Shahan. I'm a product manager at Oracle. I work in the systems team on the Oracle Storage Tech Archive Solutions team, working very closely with Donna Harlan, whose job it is to make our hardware, software, and cloud work together in an optimized solution. The talk today, it'll be a short talk because I know we're at the end of the day, but it's all about helping you design and manage your long-lived archives efficiently. We'll walk through the key components and features of an archive. And then I also just will show various architectures that you can do when building an archive. And then we'll get started with the value of an efficiently designed archive. So an archive that is designed well can help you lower your costs because it takes advantage of your existing storage that you might have on site and helps you adapt and add additional storage at lower price points. It helps you improve efficiencies by being able to adapt user-defined policies to manage your data across all of those different tiers of storage. So it's taking away that complexity of managing your data. And then lastly, ensuring access, making sure that you can get to your data as you're keeping it for 10, 20, or 30 years. Or sometimes your case could be you're keeping it forever, and we've heard about the importance if you don't want to lose your large-scale data projects. So there are features within an archive that's designed well that can help protect your data throughout its entire life cycle. And then also, I want to talk about the cloud. We've heard about it a little bit today. It's definitely impacting how you design your archives going forward. So these are just a few stats about companies who are curious about cloud. They see their business shifting to the cloud, as well as traditional purchasing of on-premise hardware is declining. So having an archive that very seamlessly integrates cloud will be important as you're thinking about keeping your data for the long term. So you can build an archive that integrates with the cloud, and at Oracle we have a software that does that. It manages your data on-premise, whether it's on disk, tape, or now directly to the cloud. So we're giving you that flexibility to put your data where you need it, whether that's on-premise or a combination of on-prem and in the cloud. So very much giving you that capability to control where you're keeping your data. You can easily tier up and add additional storage resources as you need to, so you can put data on the object tier of storage as well as to the archive tier of storage of the cloud, and it will reduce your costs. So you can automatically set policies to move your data between those different tiers. So you can choose your mix of storage based on your objectives. Whether it's cost objectives, you have to switch from the CapEx model to the OpEx model, or you're out of storage resources on site and you need to be able to grow quickly and add additional storage. You can put your data into the cloud. If you need to reduce your costs, you can go to the archive cloud, which at Oracle, that's the lowest cost of cloud in the industry. So as I mentioned, Oracle HSM, it's an on-premise application that can put your data into the cloud and gives you access to that 1/10 of a penny per gigabyte per month. So when you're thinking about your archives and they're growing, you can store your data very inexpensively. So for a year, it's $12,000 per petabyte per year. All right, now that we've talked about the value and importance of an archive that also includes cloud and addresses today's challenges, we'll walk through the components of an archive. So you have your end user applications. They need to talk to the different tiers of storage. So you have that abstraction software. So that's Oracle HSM. And then you can have your primary disk tier where you store your metadata. And then you also have you can store a copy on disk as well as tape, or also in the cloud. This is just one example of a solution with Oracle HSM. So you can access it, your applications through the standard POSIX interface, so CIFS or NFS. We have two servers here with Oracle HSM on them for high availability, as well as using QFS clients, so the quick file system clients, to efficiently move your data to tape. Again, you can have your data on disk or tape, and that's what's shown in this example. But we have many ways that you can do that. So just to give you a little view of the flexibility with this, so you can have your on-premise archive and keep 2 copies for your data protection. You can also have the hybrid archive. So you can have 1 copy on-premise and your 2nd copy in the cloud as your data protection tier. If you have only disk on site, you can then put the rest of your data into the cloud, so that you're all cloud archive model. A few more examples. You can use OpenStack Swift on the front end to create private clouds. So if you can't take your data to offsite, you can use that to build object stores. You can also have Oracle HSM hosted on site and you can keep your data on disk for fast access, as well as data in the cloud that you would be archiving for beyond 2 years that you don't need quick access to. It might take a little longer to restore, but you're keeping data there. Lastly, you can have on-premise Oracle HSM with a small disk cache, and then storing data in both the object and archive storage tiers of the cloud. So we've talked about the components. Let's talk a little bit about the features that help you ensure access. Sure. So 3 important features. Automated file fixity, so you can use industry standard checksums such as MD5, SHA-1, SHA-256, 384, 512, and that's maintaining assurance that your file is unchanged when sent from your application to storage. Automated data integrity validation, so that's assuring that the data hasn't changed after it's been stored for data at rest. And you can set policy-based audits to do that and self-heal automatically. So if you have an error, you can correct from your second copy. Also, keeping data in open formats, ensuring that you can access the data for years to come and share it across systems. This is just an example of how this works together to protect your data and ensure access throughout its entire life cycle. You can do it on each read or write, or set policies to periodically validate it. This is a case study of one of our customers and their architecture. So they're using Rosetta in front of Oracle HSM, submitting their own checksum, and then storing the data on flash, as well as 2 tape archives, and are set up to go to cloud. So for data in transit, they're using file fixity, data at rest, data integrity validation. And then lastly, just in summary, you can manage your archives very efficiently with a software like Oracle HSM. It helps you improve efficiencies with your user-based policies, lower your costs by seamlessly integrating to the lowest cost archive cloud, and also ensure access with its robust features for data integrity validation. Thank you.
So obviously the cost of storing the data is $12,000 a year, but per petabyte a year. What would be the restore cost to store that and retrieve?
Sure. So there's standard recall costs, and those are made publicly available. So I think it's 0.005 cents per retrieval. One of the benefits to having the hybrid model that I didn't point out is you can recall your data from your local copy, and then you don't have any retrieval cost. So that's a really important component, to have the ability to have a hybrid solution.
Okay. Any other questions? Okay, very good. Thank you again, Don. So we have Igor Sviligoy, got it that right, with General Atomics, and he will be our last talk of the day. So
Can you hear me? No? Oops. How about now?
Yep,
Yeah.
perfect.
Okay, so I'm from General Atomics, and yeah, I'm here to talk about 2 things. What we call a virtual object store, and why we decided to make yet another HSM, which sort of flows well from what we had before. So just some background, General Atomics have been involved in storage for a long time, and we for a long time have been developing something called Nirvana, which is an object store, which the usual storage abstraction, federation, metadata repository, policy engine, audits, anything that you would expect. And I would just like to stress out that we really see it as a virtual object store. We don't want to reinvent the way you store files. There are so many systems out there that already do it. So we just layer on top of them. So you store your data in the file system you like, and we will just federate them, replicate them, manage them for you. And we will not be responsible for keeping your data around. That's for somebody else. And we will do it on anything, pretty much the support that has a file path, some basic permissions, and you can ingest data and get them back. Of course, we cannot support everything under the sun, but in theory we could. Now, Nirvana actually works pretty well, but I must admit it was not a real big success. And most of it, we believe, is due to we never took the time to implement standard APIs. We decided to make our own, obviously. And not many people bought into it. So what we decided to do in the last year is, well, let's change that. So we went for two legs. One, let's make an object storage API based on S3, and let's see if we can make a POSIX interface to it too, because a lot of people like POSIX. Now, adding S3, as I said, Nirvana is essentially an object store by itself. It doesn't actually own the storage, but it really presents an object view to a federated storage underneath. So adding it on top of it was not hard. We have it there. It works. Great. Finally, you can talk to Nirvana, to something like Cloudberry Explorer, and it just works. Any library would work. Not rocket science, but we finally got there. The most interesting part was adding the POSIX interface. So Nirvana natively does not provide a full POSIX experience, and this is due to the fact that we support pretty much anything under the sun. So if your data is stored in the cloud, they don't provide POSIX, so we would need to provide it. And we didn't really want to do it because you would need to do some kind of caching file system in front of it in order to get there. So instead, we decided, let's see if we can leverage something else. We looked around, and we found GPFS. It's actually something that looks really, really promising for that. Why? Well, it's very mature and very reliable, highly scalable. It has multiple access protocols, native clients that are fully POSIX compliant, NFS and Samba. It even has an S3 interface. And it's natively HSM enabled through the MAPI, and it has rich ILM capabilities. So perfect, exactly what you want. So we went ahead and created this product that we called Easy HSM, which is essentially an HSM solution on top of GPFS, and it can talk to Nirvana. So you use GPFS that provides all the namespace management that you need, full POSIX compliant, all the hot data is managed by GPFS, and Easy HSM will move data in and out of GPFS into Nirvana as needed, as any decent HSM would. Perfect. We now have a great POSIX front end for Nirvana. Yay. Now, why did you decide to go for a completely new system? Well, first of all, nobody else, the existing system talked Nirvana, but most of anything else, all the other commercial software are really, really expensive. Most of them have capacity-based licensing, so the more you store, the more you pay. And we didn't think this was really something our customers would want. So we are not free either, we are not open source, but we have fixed pricing, which we think it's more fair. So you pay for the software that does the job for you. It doesn't matter if you're storing the hundreds of petabytes or 10 gigabytes on the other side. We do exactly the same work. Yes, you need more hardware, but the software should not cost more. Once we get there, we looked at what we did, and we said, you know what? There's really not much that is Nirvana specific in what we do. So how about we make it later more generic? And we did. So essentially, we modularized it, and the upcoming version, it's not yet out yet, but we are getting there fast, supports, apart from Nirvana itself, it supports POSIX and S3, just like Nirvana did before. So we can go, Easy HSM becomes a generic HSM solution for GPFS that can go
directly to stuff like Isilon or NetApp or S3 or HGST or the Black Pearl, if you want to go to tape. And it just becomes an easy HSM, and we are marketing it that way too. So if you have a GPFS system and you just want to tier, and you don't care about Nirvana, you can go this route. Of course, we are still very happy if you want to use Nirvana because we think there is value in it. So essentially, my final slide is, why do we think EasyHSM has a chance in the world? Well, it's pretty much the only solution that really provides any protocol under the sun you can think. And it's mostly POSIX and object, but we could easily extend it to other things. It's meant to be that way. One design approach we took is we don't want to hide what we migrate. So the file path that you have in the external storage is pretty much the same file path that you have in GPFS. So you can go straight into the external storage and find your file without trying to figure out where the heck is my file. What is this object 1234 really? It really maps to something that you had already in GPFS. It's very scalable and not low overhead, scales linearly with the number of hardware nodes. We took great path not to be in the path of hot data, so we only manage files that are on external storage. Anything that is already in GPFS, we don't touch it, we are not aware of, at least until you want to move it out. It's a pure software solution, so we don't sell hardware. We run on any hardware that can install GPFS, essentially anything that runs Linux on x86 these days. And as I mentioned before, we have fixed price licensing. And that's my talk, essentially. This will be posted. There are links how to get it. Just a quick final slide. What else happened in Nirvana for those who know Nirvana from before. We drastically speed it up, and we have a new administrator interface. But that's about it.
Just a reminder for the speakers, if you are willing to share your slides, please do make sure they are copied to the USB drive, and we'll try to make them available on the webpage. Thank you.
Okay, great. And then just quickly for tomorrow, we'll start at 8:30. There'll be registration starting at 7:30 and breakfast and coffee, et cetera, available. I would like to invite people who are interested. If you've stayed right to the bitter end of the conference today, that means you're pretty dedicated. So we are looking for program committee members. And so if you're interested, please talk to me right after this. Maybe give me a business card. We usually start ramping up about 4 months before the conference. We do have some calls before then. It's not, my goal is to kind of, is really to increase the size significantly and thereby divide the workload significantly as well. So a lot of what the program committee does really is bird dog interesting topics and leads. So in terms of presenters, so for example, Gary Greider and I do a lot of it. So we get folks like David Bonney here. Per Simonson from MemoScale had met with Gary, for example, so we were able to meet him. So you have the advantage of, you can help us if you're interested in the topic, large scale, extreme scale systems, maintaining them, running them, installing them in the enterprise cloud or HPC. That's really what we're about, and long-term archives, as you just heard. So if you're interested, send me an email or stop by, and certainly tomorrow as well. All right? Otherwise, that concludes the first day, and we'll see you tomorrow morning. Thank you.